So hello and welcome back to the fourth day of the Galileo Teacher Training Program. Many thanks for joining again. It started getting a little bit harder on the fourth day. So I see numbers of participants are going up. So before we start, I think Rosa can tell us some very exciting news about the participants. Rosa?
Yeah, can you hear? I was mute, sorry. You can hear me, right?
Yes.
Good. Okay, yes, I think that we give some more moments for the participants to enter, and I'll make you all happy to see. Okay, let me share my screen and wish that it will work. Okay, you can see my screen. You can see grasp the back office, Michael?
Yes.
Okay, so they have now created this very nice tool, actually for the teachers that are here. You can also use this to see what your students are using. But you know, when this was created, the team from EPFL called me and said, we have a new feature that will make you really very happy. So we can even download this. So here you see the actions by day. Actions can be entering, downloading, working on an app, or doing anything. It's not specific, and we don't have the small information. But if I select everyone, I see that we have 205 people that have already accessed it. These are different people coming to the software, and to make sure that I'm not saying any lies, you can see this again is collection of actions, okay? And you see that there's a lot of things going on in Europe. In Africa, we have lots of people from Africa doing things. We have actions coming from South America. Look at this. From Peru, Colombia, Nicaragua. Well, I think this is a little bit dislocated because I might not have the proper size of the map. And we have people from North America. And let's take a look at Asia to see how well we are doing. Yeah, we have people from India, Philippines, Indonesia, Australia. So I think we went global, Michael. What do you say?
Yeah, it looks really good. Very exciting.
Yeah, this is really good. So, and here, yeah, as I said, the people can see the type of action, the people are navigating. Of course, this is not counting what people are doing. This is just our campus, right? This is where you find all the goodies. So people come here, download, or just watch. So it's just purely navigation. We don't expect to see anything else. So I think this is actually very encouraging. People are active in doing things. And look, today we just started, and we already have lots of actions coming here. We have 167 actions. This is probably people coming in. Remember that it's teachers, not all the teachers. We know that some of you are very brave and you can be here with us, but some teachers are in classes, especially in Europe. So this is very, very good. Okay, I will stop sharing my screen. I think I'm very happy this morning.
Yes, me too. Many thanks, Rosa. Looks really good. So we're going the next step. What started as a more or less local event and became a European one, and now it's a worldwide course. And so with this, we come to our first talk of this morning. You can see him already there, Markus Kisler-Batik. He is the department head of the Science Operations Missions of ESA here at the European Space Astronomy Center. So in the end, he's responsible for all the spacecrafts, all the nice spacecrafts that are investigating the universe. And while we had already a small glimpse on the science program by our director in the introduction, he will now really go into more depth and tell us everything about the scientific missions of the European Space Agency. So please, Markus.
Good morning, everybody. Good morning, Michel. I'm not sure I will tell you everything about all the space missions, but I'll try to make a good summary in 1 hour. So thank you very much for joining us this morning, and it's my pleasure to actually introduce to you the ESA missions. I'm going to share my screen and launch my presentation here. Are you now seeing my full slides?
Yes.
Okay, perfect. So yes, Mission introduced me. I'm the head of science and operations, which essentially means that in the European Space Agency, in the Directorate for Science, and I'll tell you a little bit more about that. I am actually leading the definition of the science with all the project scientists in my department, but then also all the operations. So we're not building in my department the missions, but once they are actually flying, we operate them. And we, of course, we prepare all the operations for this. You had, I think, very good introductions in the last days to ESA. I'm just going to flash this map up again. You might have seen it before. This is the European Space Agency, 22 member states, and the green dots mark where in Europe we have centers. And I wanted to actually flag here with the yellow dots where the science missions are done. So you've seen all the variety of what the European Space Agency does. I think the yellow circle here mark what is really relevant for the science missions. And maybe let me start with the circle in the Netherlands there. That's ESTEC. That's where actually the science missions are being studied, the concepts are being developed, research and development is being done, and we're actually looking at the technology of the space missions. Then the dot in Spain is where I'm located, and the European Space Astronomy Center is located. So that's where really we actually operate the missions, where we get the science out, and where at the end we archive also the data. So it has a huge data archive of all the missions we have ever flown there. Eventually, while they're flying, actually the missions are operated from Darmstadt. So you see this yellow dot in Germany, and that's where the mission operations are. So these are the people to which we send commands, and they actually send through the antenna the commands to the spacecraft. And then there's a yellow dot also around Kourou, French Guiana, because of course that's from where many of our missions are launched, not exclusively, but a lot. This is a little bit of the picture of what ESA does. I wanted to actually situate you where the ESA missions are. So the ESA science missions are here in the science and exploration pillar of ESA. But before I start talking about them, I would like to show you what it takes to actually get a science mission done. And essentially, we really need to start here in another branch of ESA, not under our responsibility, but these are the people who actually procure the launches. And you see that we are very much relying on them. Here you hear behind me the countdown of an Ariane 5 starting. And the well-developed rockets and these very massive rockets. You see on the right-hand side an Ariane 5, but then also the Ariane 6 with 2 boosters, with 4 boosters, so what we call the Ariane 6-2, the Ariane 6-4. And a lot of the commercial satellites these days are actually relatively lightweight. The trend is to go to actually lighter weight satellites. And these very heavy launchers that we have still here are the ones which mostly carry our heavy satellites, the satellites which actually don't only orbit the Earth, but actually fly through the entire solar system. So obviously, if you orbit the Earth, you can be a 10 by 10 by 10 centimeter satellite. When you want to actually fly further, typically you need a larger spacecraft. So that's the one branch which helps us. The other branch which helps us a lot are the tracking stations. So these are the people that I mentioned under the responsibility of ESOC, the European Space Operations Center in Darmstadt, and we have tracking stations all over the planet. I think if you look at the right-hand side of the slide, the Earth is turning, of course. If you now imagine that you are a satellite and say you are close to Mars and you look back on Earth as Earth is rotating, if you want to communicate with us, send down science data, obviously if we had only one antenna on Earth, you would see it only at most 12 hours a day. And that's why we rebuild a huge network of antennas around the globe. And these are all these little green, red, and blue dots that you can see on the world map. We try to actually be close to the equator because most of our satellites are actually in the ecliptic plane. So we want to actually be able to communicate with them. We have antennas of different sizes. For satellites which are nearby, we don't need so much communication power. We can live with small satellites, so small being 15-meter antennas typically is what we use. But then for science missions, which are very far out in the solar system, where we really need a lot of communication power to communicate, we have this massive 30-meter antennas. And I'm just going to fly into one, which is the Cerebros antenna, which you see here. So that's the antenna we have actually located near Madrid. It's one of our 3 antennas for deep space communication. We have one near Madrid, we have one in Argentina, Maghreb, and we have one in Australia that you can see they're both marked with yellow bars on the map. And so these 3 big antennas are distributed around the globe, and hence when the Earth rotates and the spacecraft is far away, we can actually have 3 points of communication per day with that spacecraft. So that's the infrastructure that it takes to run a science mission. Of course, we as a science directorate, we are not the only ones to do science as such at ESA. I wanted to actually just flash up quickly the Earth observations. You had a day, I think, you had a good introduction on the first day about that. ESA is doing, of course, a lot of Earth science, so that's looking down on Earth and to study all kind of extremely important phenomena like and so on. But we are the ones who actually look up typically, so away from Earth, or when we look down, it's because we are close to another planet. So that's what the science missions are. But we have also, of course, colleagues. In ESA, we define this as one pillar, the science and exploration. And the exploration part is technically not part of the Directorate for Science. These are the people who actually do all of this. So essentially, it's the branch which does science everywhere where you can still reach it with humans. And being optimistic, of course, that's the ISS, almost permanently manned International Space Station. The Moon, where we intend to actually return and this time to actually settle. And we included also in there Mars, Mars being a place where we are projecting to actually send humans to. So that part of ESA is a very exciting one. We work in very close collaborations with them. We have actually scientists which are in my department, which are shared on many of the projects which go across the 2 boundaries. And eventually on Mars, that's where our 2 branches overlap. So we have for Mars, most of the Mars missions are shared between the 2 of us. When you go further than Mars, where humans can't reach anymore, then it becomes our domain, the ESA Science Mission domain. So that's what I want to talk to you about today after this short introduction. So to give you a picture of where we are, ESA does a lot of things. We rely for the science missions on a lot of things that ESA does on the launches, on the communication networks, etc. I didn't mention other space agencies, but of course we're using also the infrastructure of other space agencies, and I'll talk a little bit of that later. And of course also we also use other launches when we do collaborations. We just use Soyuz rockets and but also American Atlas rockets to launch our satellites. But we try to rely on European launches most of the time. So now I think the a fundamental question that which you might have talked in the last days about or not, but I think it's important to understand why at all we do space missions. Of course, they're exciting and it's fantastic science, so no question. But the question is really, why do this science from space? Why wouldn't you be able to do that from the ground? And I wanted to actually just list you a few reasons why we spend this mission in space. Because space missions typically, compared to a ground project, which would do similar science, is probably 10 times more expensive, as a rule of thumb. So before you decide to spend 10 times more money to get the same science, why would you do that? And I try to list here the reasons. Really, we have 3 big branches in space science, which so all of these are addressed by the ESA Science Missions. We have Helio Science Missions, we have Planetary Science Missions, we have Astronomy Missions. And for each of these, the reasons to go to space are similar, but maybe a little bit different. So for helioscience, for example, when we want to study the sun, obviously you can see the sun from Earth, right? But the closer you are, the better view of the details you have, of course. The sharper, the higher the resolution, the physical resolution is on the sun. The other thing, which is another interesting point, especially made by Solar Orbiter, that you probably heard enough yesterday of, is that we view the sun in the equatorial plane, and if we want to see the poles, we need to actually fly a spacecraft on an orbit which actually would see the poles. The other thing also is that beyond the Earth's magnetosphere, you can study the solar wind before it actually interacts with Earth, and you can actually study it also in many other phenomena. So there are lots of reasons why you want to go to space to study the sun. Now, on planetary science, when you want to study the other planets in our solar system, obviously you can see them, but with a very bad resolution from Earth. The closer you're to the planet, again, the more details you see. If you actually get all the way to the planet, you can start orbiting it and start actually studying remotely the atmosphere and the geology. So you can get a very good understanding of what that planet, if it has an atmosphere, is composed of, and also what's happening on the surface with all kind of radar techniques or others. And then finally, if you actually even go as far as landing on the planet, you can of course study all the composition all the way to the ground, but also start collecting sample compositions. And that's of course what we do for Mars, but not only for Mars. We have other ideas as well, and I'll show you an example there. And finally, astronomy. There are lots of telescopes, of course, on Earth which look up. There are two main reasons why we actually go beyond or in space for astronomy. Is to study all the wavelengths that the Earth's atmosphere blocks. So you know that the Earth's atmosphere lets through visible light, but as soon as you are on the more energetic side, so if you're in the UV light and then the X-rays, the gamma rays, etc., all of that radiation is blocked by the Earth's atmosphere. So if you want to study that, you have to actually go above the atmosphere. Or on the other side, if you go to the infrared light and longer wavelengths, there a lot of the water in our atmosphere blocks this radiation, and it only reopens in the radio domain. So if radio waves come all the way to the ground, but if you want to actually be in between this infrared and the radio domain, there being in space is extremely helpful. And of course, the other thing that the Earth's atmosphere does is it's turbulent. So if you look at the stars, they twinkle and they're smeared on your telescope. If you want an extremely sharp view and you want to actually escape the blurring of the Earth's atmosphere, like the Hubble Space Telescope, for example, going just above it, and a few hundred kilometers is enough orbiting the Earth, then you have a much clearer view. So these are essentially the key reasons why we invest all that money to actually go beyond the Earth. So let me tell you a little bit about our program, about the space missions that the European Space Agency is flying. We have a whole suite of them. We have actually at the moment 13 missions in operations, so a whole lot. And we have another 15 missions in preparation for the next decade. So some of the older ones will stop working, although the missions, we tend to operate them as long as we can, very often much longer than planned. A nice example is are two of the longest lived telescopes so far, the Hubble Space Telescope, which just celebrated its 30th birthday. It was never planned to operate for that long. It was originally planned to operate for 5, maybe another 5 years after that. And XMM, which also celebrated its 20th birthday, and which has been operated since then and might actually operate much longer. So I'm going to give you a short overview of these missions and talk about some of them. Not all of them. If I were to go into details for these 13 missions, it would take us longer than you might want to listen to me. Although I could talk for them forever. But maybe showing you here an overview. Essentially, in terms of helioscience, we are leading or participating in 5 of them at the moment. In Solar Orbiter, that I'm sure you have heard about yesterday, SOHO, Hinode, and IRIS as 3 more, which are a little bit older. Cluster, which is actually looking at the interaction between the solar wind and the Earth's magnetosphere. We have a couple of more in preparation, and there are also some in legacy, and I'll show you in a second what that means. In planetary science at the moment, we're operating 3 missions. We have Bepicolombo, which launched a couple of years ago and is flying towards Mercury. Still needs a few years to actually get there, and then we'll study Mercury in detail. And we have 2 missions which are orbiting Mars at the moment, Mars Express and ExoMars, the trace gas orbiter. We have a number of missions in preparation. We have JUICE, which will go to Jupiter. We have Comet Interceptor, which is interesting. It's going to be parked near Earth and wait for a comet to actually then just fly there and study it. We're participating also in this Mars Moon exploration mission from the Japanese MMX, and also into ExoMars, which I'll talk a little bit about in a second. And you might have heard about it yesterday already. Finally, in astronomy, we have missions which have that I'm sure you've heard about, like Hubble and Gaia, and recently we also launched Cheops, a mission to study exoplanets, and then we have missions in the high energy domain, like XMM-NEWTON, an X-ray mission, and Integral, which is looking at gamma rays. And in preparation, we are collaborating again with NASA on the Webb Space Telescope, and then we have missions like Ariel to continue to study exoplanets, and Plato, and then Roman, Euclid, and PRISM. These are all missions which are coming, Einstein Probe, Athena, LISA. So a whole suite of astronomy missions planned for the next decade. And I'm not listing even all the missions in Legacy because we have 13 of them there. So this is the picture we like to show when we present our missions. That's one half of them, and I'll show you the other half in a second. So that's the half which is either doing helioscience or planetary science. So you see the solar system here, the sun on the left, the planets. At the top, these are the missions we are preparing. So these are the missions for which we are planning the cruise and the arrival at the destination, on which sequence we would actually then execute the observations, what we want to study with. In the middle row there is all the missions that are currently being operated. So these are all the ones we have on our hands at the moment, for which we're getting data every day. And at the very bottom, you have the missions that we did fly that have ended their mission, and for which we're actually hosting the data, because that's a very important activity of what we're doing as well. I told you that at ESAC we have this huge, so in Madrid we have this huge archive, and we have the data for all of these missions. You can access them. If you haven't been introduced to the tool ESASky, that's one of the ways to access the data to our missions. So these are the planetary missions. These are all the ones which are operating at the moment. I'm going to talk about some of them. In yellow, the ones which are for helioscience. In turquoise, the ones for planetary science. And these are then the missions, the other half of our missions, the missions in astronomy and astrophysics. And again, at the top, the missions that we're preparing. Some are close to launch, like the James Webb Space Telescope will be launched next year. And then Euclid and will be launched the year after, and a few more which are coming in the next decade. The middle row is the ones which are operating at the moment. So these are all of the missions that we are getting data every day for. And at the bottom again, all the past missions we have flown. So it gives you a good overview of this very large program of science missions that the European Space Agency is flying. And here the astronomy missions are sorted a little bit by the wavelength domain in which we are looking. So you see that we have a number of missions looking in the infrared or even sub-millimeter, but all the way to optical light. That's when we want to escape the blurring of the atmosphere. And then on the right, all the missions that in high energy, where we study the most energetic phenomena of the universe. And at the very right there, at the top, you see LISA. LISA is a mission to study the gravitational waves, so going even beyond electromagnetic radiation and trying to get all possible signals we can collect from the universe to understand the universe. So we're really trying to actually have this very broad suite of missions to study the universe in all its colors, wavelengths, and energy domains. So one thing I wanted to mention is how do we go about to select them? So who makes a choice of what missions we would fly, and how do we get to decide this? Of course, we're trying to keep a balanced suite of missions. We try to actually balance our program fairly between the helioscience community, the planetary science community, and the astrophysics community. Essentially, ESA is serving its member states. So we are really serving the scientific community. We have maybe 100 astronomers or planetary scientists which are working at ESA to help us develop these. But really, what we are serving is about 20,000 or so scientists in the member states and worldwide. And these are the people that we consult when we want to actually understand what we should do next. So our member states give us a certain budget. Our budget is about 500 million per year. And we need, with that budget, to actually get the most science out and to offer the most attractive possible program to the European scientists. So we want to actually provide very broad science schemes. We want to actually offer everything you can do from space. Of course, we don't have an infinite amount of money, so we cannot offer everything, but try to actually rotate through missions which are interesting to all communities. And so the community provides us the broad science schemes, and then they are also engaged into selecting individual missions. We typically have a competitive phase when we say, okay, we would like to explore, for example, star formation or as a broad scheme. Then we might have 2 or 3 actually proposals on how to do that. And again, the community would come and tell us, okay, this is the one which is the most promising, move ahead with this one. And if you look at a little bit of how this is structured, we try typically to have 3 sizes of missions. And I put you a little bit for an estimate of the cost of such a mission there. We have at any given moment maybe a couple of very large cornerstone missions, and these we're talking about 1,000 million euros, so a billion euros of cost typically for these type of missions. So of course that money is spent over 10, 20 years, not at once. But we typically have a few of these either in planning or flying, and these are really our flagships. And then we have a number of medium-sized missions, and can be very often collaborations with other space agencies. We have some fast, smaller missions, and they're still not cheap, but compared to the other categories, they're typically 150 million or so. And we also have always funding for missions of opportunity. So that's when we want to participate in missions from other agencies. I think one of the nice things that might have been mentioned to you yesterday is that the Europeans are very unbiased when it comes to collaborations. So we are probably the only space agencies which has collaborations with really everybody else, because we have missions where we collaborate with the Japanese, with the Chinese. We collaborate a lot, of course, with Roscosmos, with the Russians, but also on many missions, of course, with NASA, which is the other big player in space science. So that's one of the things that I like a lot about ESA, is that we are very open to worldwide collaborations. I wanted to walk you through a little bit to give you a feel of what does it take to build space missions. Did we start yesterday and decided that today we would fly a major mission? Not at all, right? So most of the missions that are flying today, SOHO, Cluster, XMM, are missions which are still operating. Rosetta is just finishing. Herschel finished a few years ago. But you see also there Huygens Cassini that ended, but Integral and Planck. These missions were actually selected and decided upon by the community in the 80s. So I don't know what the age distribution today is of all of you listening. I was still at school in the 80s. And that's now the missions that we're operating. We had then 10 years later, we went back and selected some more missions. Gaia, which is flying, LISA Pathfinder, which ended, Bepi Colombo, which is now underway. So you see that it's up to 25 years between the moment you decide, okay, we should do a mission of that type, then going through actually assembling the groups which will build the instrumentation, understanding how to best build a spacecraft, and then getting everything assembled and built, and then launching it and operating it. Typically takes 10 to 20 years from the moment you have the idea. Then the missions we are currently preparing and will be launching or start launching, like Solar Orbiter just launched, Cheops just launched, Euclid and JUICE in the next 1-2 years. These were selected in the early 2000s, so with an exercise which we called Cosmic Vision. So in 2005, in fact, we selected missions like Athena and Lisa, which are now going to fly in 2030 plus, right? So 20 years, 5 years ahead. So it's a long process to define a program, such a big program as we have, and to continuously bring new missions in and decide, okay, what are the important science questions to answer, and how we are going to do that. It's a long process. And in fact, we started this year the process for the missions that we want to fly in the 2050s. So the ones that I will never operate, and maybe my children, or actually exploit them scientifically, probably my grandchildren. But we are paving the ground today. So it's all very important work that we're doing there. If we would not be doing it today, then the next generation or the generation after that would not actually get all this wonderful data from the universe. So it's a long process. Okay, so that was to set the scene. I hope that you actually get now an idea of how massive the ESA science program is, how much money it takes, how much time it takes to actually develop all of that, how much support we need. So let's see a little bit what comes out of it. And I'll talk a little bit about Science missions, then about planetary missions, and then I'll finish with astrophysics missions. And I'm conscious that you had a full day yesterday of talking about the sun, and you got a very full talk about Solar Orbiter and how exciting that mission is. And it's really probably one of the most spectacular missions we're flying to study the sun. Why study the sun? Why is it so important? I think I have a background, I should say. I'm also an associate professor in Munich for astrobiology. And if you look at that from an astrobiological point of view, all the life, or almost all the life that we know on Earth, is dependent on the sun as an energy source. So obviously, at some point, life evolved to understand how to use solar energy, some 2.5 or 3 billion years ago. And the moment it did that, life exploded, and it was such a cheap and efficient source of energy that life diversified, exploded, etc. And all the way up to today, most of the living organisms use the sun as a primary energy source. And if the organisms don't, then they actually essentially eat the people that have the sun as an energy source. So you are, if maybe you're a vegetarian, then you eat people who actually had absorbed the sun as an energy source. If you're not vegetarian, you certainly eat vegetarians. So you are 2 steps away from eating the energy of the sun. So understanding the sun as a star, as the star we can study best, is what all these Science missions are about. And since you've heard so much about it yesterday, I'll just leave it at that and move forward to planetary missions. But before I do that, I wanted to actually show you, because we have these nice orbits, what you were seeing moving there, and also the timeline for Solar Orbiter. Really, when we send out a spacecraft, typically we are very limited in mass, and what that means is we try to pack as much scientific instruments on top of a spacecraft. We can only transport a limited amount of fuel. So we cannot just, a la Star Wars, just fly through the solar system. We rely on small corrections, on very small corrections to our orbit, and slowly actually getting where we want to go. In the case of Solar Orbiter, I'm sure, I think Zanika explained that yesterday, we want to actually look also at the sun on the poles. And to actually incline that orbit, we're not relying on just the spacecraft doing it. We're really relying on passing by planets and using the gravitational pull of the planets to actually send us exactly in the right direction, to start inclining this orbit, getting out of the plane of the ecliptic and slowly moving to an inclined orbit to actually be able to look at the sun from above and below. So that's what all these flybys are. And I find it always fascinating that we have such a good understanding of celestial mechanics these days that 10 years in advance we can predict, in fact, probably to close to a few milliseconds, when the spacecraft is going to pass by the planets, and then how we're going to swing it such that it gets into the orbit we want. So that's one of the things I wanted to highlight here, beside the the science. Planetary missions. So I wanted to give you a little bit of an overview of the planetary missions that we are running, and let me start with this graph, which is I'll come back to this a few times to show you a little bit where we are cruising in the solar system. So I won't talk about all the missions. I said that I picked a few which I thought are very representative for the type of science we try to do and the questions we're trying to answer. Fundamentally, what we want to actually understand in the solar system is questions of how did the solar system form in general. So how did all these planets assemble? How did we get to have the telluric planets close to the sun? How did we get to have the gas giants and the ice giants further away? What are they composed of? Where did the water come from? Where did liquid water come from on Earth? What was the solar system composed of to start with? Could we explain was that the origin of life? So these are the big questions we're trying to actually answer. And Rosetta was a very important mission in that. Rosetta is just in what we call post-operation phase. So we're still operating it in the sense that we're actually nurturing the archive. We are preparing the data for this to be a legacy for humankind. All the data are, of course, available through the archive since a long time, but we're trying to really make it sure that in 50 and 100 years, if you want, like good librarians, these data are still available for the future generations. So Rosetta was really an amazing mission because it operated for, if you want, 12 years, but really 10 of these years were just to get where they wanted to actually get, and that was to the comet 67P, and including a landing. So let me play you a movie. I hope that is going to play over the remote. But really, the mission started in 2004 and was launched from Earth, and you see here the trajectory that it took. And it was cleverly done. So it was, it had one of these gravity assists to actually swing it onto the orbit that we wanted. We knew where the comet 67P would actually be in 10 years, right? Then it swing by Mars to actually get in a more elliptical orbit, and by Earth. And on the way to the comet, which was really the goal, we had seen that it could fly by two asteroids, the asteroid Steins, and it did just fly by there. And then by having a third gravity assist on Earth, it could also fly by a second asteroid, Lutetia, in 2010. And after that, so that's when it did some science, it went into a hibernation phase. So we put the spacecraft almost dormant to actually just check every week on it, and let it fly then for another 3 years until 2014, when it came out of hibernation, and then we started the rendezvous maneuver. And so we wanted to bring this spacecraft into orbit around a comet. We knew roughly the size of the comet. We didn't exactly know the shape. We didn't know the gravitational field. And yet you want to actually bring a spacecraft, lower the velocity such that it can actually be captured and actually start to orbit around the comet, right? So it's phenomenal in terms of space flight, which we call the flight dynamics people who calculate all these orbits. It was amazing. And then we managed to actually stay there, study in orbit the comet, and eventually even drop a lander, Philae. I'm sure you've heard about it and read about it in the news at that time. It was really the first time this was attempted, and it was, I think, a great success, despite the fact that, in fact, the little probe that was sent down bounced. I'll show you a movie in a second. And really again, to stress the timelines, the conception that we should, that it's so important to understand pristine material in the solar system. If we want to understand our solar system, if we want to understand the origin of life, we need to understand the pristine composition of the solar system, and comets are carrying that pristine material. So it was really a concept in the 70s, which was developed. It was approved, this mission, in 93, and then 10 years later it was launched. And as I showed you, it took about 10 years to get to that comet. So really, we wanted to actually understand the coldest parts, the remnants of this coldest part of the solar system, understand the origin of the solar system, and really also whether these comets, there's a big water reservoir out there in this in the outer solar system, because we know that in the inner parts of the solar system where Earth is, the water should have evaporated with the temperature of the sun during the formation of the solar system. Liquid water was not possible there at the beginning, and we need to understand how did the water come onto the surface, and especially where it came from. So it really helped us to study this comet, and I think the most spectacular part of this was really the fact this is an animation. It's not real. We didn't have a second satellite to film this, but it gives you an idea of the sizes. If you ever have a chance to come to ESAC on site near Madrid, we have actually models of this, so you can actually get a feel for the relative size of each. And that was a spectacular attempt to actually drop Philae, the lander, onto the comet. To once we had actually studied it in orbit, understand where a good landing spot would be, and then drop it there. And it did. This is really a pack of dirty ice, right? This comet. It's not rock. It's not solid rock as you imagine it. It's really dust-packed, cold, dirty ice. So we knew that when it was going to land, it was going to bounce. So it had almost little harpoons to actually really block itself, and that mechanism didn't function as well as we expected it. But eventually it did transmit data, and we got actually very nice science out of that mission. And it was really paving the way to now similar missions which are happening. I mean, I think a couple of days ago you probably saw that NASA and the ORISIS-REx mission tried something similar, where they extended, they went outer space and tried to collect the sample by sucking it from ground. But I want to talk a little bit about the Mars. I know that you had a Mars day yesterday, so you probably heard a lot about this mission. So I'm going to just flash a few results up. But really, Mars has become a primary target for the exploration of the solar system. I think it goes back to a century ago when really the first science fiction ideas came up, and all the way to Schiaparelli, actually, who in Italian astronomers who thought he had seen canals on Mars and projected this idea that Mars could be inhabited, which was all these hypes, the Viking missions in the 70s to go to Mars to actually try to find life. We were absolutely sure that it was just as easy as landing there to immediately find life. So the Viking missions were the first ones in the 70s to transport an astrobiological payload to actually try to hope discovering Mars. Then they landed there, they didn't discover anything, which was kind of a bit of a setback, but and certainly told us it's a lot more complicated to study these planets than just flying there, landing and looking around. But it became extremely attractive, and we have sent, for example, more missions to Mars now. Humankind has sent more missions to Mars than we have sent, for example, in the Mariana Trench to explore the deepest ocean parts. So we know Mars better than we know the deepest ocean, which is phenomenal in a sense. So in terms of ESA missions, of missions from the European Space Agency, we had sent Mars Express towards in 2003 already. So it's been there and it's still working since 17 years now. More recently, in 2016, we sent the first of the ExoMars, the Trace Gas Orbiter. So it's an orbiter around Mars. It will actually, it orbits Mars, does a lot of science, especially looking at trace gases, very precise measurement of the thin atmosphere that Mars has. It comes with a second mission, which will be launched. It was due to be launched this year, but then it was slightly delayed, and the pandemic didn't help in catching up with the delay. So it will be launched in 2 years, because you know that Mars has a 2-year orbit around the Sun. So every 2 years we are back from Earth in close range. So the journey can be made in 6 to 8 months. So the second ExoMars will land a rover and a surface platform. And I'm very excited about that, because that's really the rover is gonna drill several meters to the ground. We will really be able to actually understand what the soil potentially actually be able to understand the soil composition, and whether we have a chance to find life in subsurface. This being said, there were a dozen or so attempts, a little less than, to land on Mars, and only every second one was successful. Right, all space agencies taking part. So it's not easy to land on Mars, and fingers crossed that it will happen. And then finally, we have this super ambitious plan with NASA together to return a sample from Mars, and I'll talk to you a little bit about that. Let me first show you a few of the amazing pictures really of Mars. If you imagine this is another planet, right? So it's in our solar system, but we actually can get there and can get this type of spectacular pictures from the Mars surface. We have now essentially cartographed the whole surface of Mars, and some of the people working in my department are geologists. And I remember meeting the first one. I said, like, what the hell? You're a geologist. You're in the wrong department. I said, no. I'm actually the geologist studying Mars, and I apply the same techniques as on Earth. And we're looking at habitability, climate changes, because we've been for so long now looking at studying Mars. We know how the weather changes in the 2-year cycle. We know where humidity is as a function of seasons, whether it's near the equator, what happens at the poles, how the ice melts, and what the liquid flows are, etc. And we have images like this, which clearly gave us hints that that there were flows of temperatures. Of course, you probably heard yesterday that the atmosphere of Mars is 100 times less dense than on Earth, right? Mars is only a third of the size of Earth, so the gravity is only a tenth, roughly. So it cannot retain really an atmosphere. A lot of the atmosphere was sputtered away by the solar wind. Very thin atmosphere. Given that there's such a low pressure, the triple point of water is, if you look where water is solid, liquid, and in vapor form, the range of temperature is a few degrees there, and so you can have at the pressures on Mars, water would go from a solid state, from an ice state, almost immediately away to a vapor state in most cases. So getting liquid water on the surface with the current atmosphere is almost impossible. But underground, liquid water has recently been reconfirmed, although it's a kilometer underground, but there's liquid water there. Now, the Trace Gas Orbiter, which is the other mission, which is more recent from 2016, produces less spectacular images, but not less spectacular results. That's the one which actually, by looking through the atmosphere of Mars, can really define what the composition of the atmosphere is. And we were hoping, we are learning an immense lot from this. As you know, probably the Earth atmosphere is a very good tracer of whether there's life or not on Earth. Right? The fact that oxygen is so plentiful in the Earth atmosphere is only due to the fact that life is so ubiquitous on the surface. And there are other gases that you can trace to actually understand whether there's some kind of a metabolism on the surface. Methane was one, so there's still a big debate about whether methane is present or not in the Mars atmosphere, and if so, what the source is. Methane can be biological, but methane can also be geological. But the Trace Gas Orbiter is one which delivers at the moment most of these data to actually understand the composition of the Earth's atmosphere and help us understand how it changes with seasons, and what the geological phenomena are, and potentially whether there's a chance for biological phenomena as well. But the most spectacular mission is certainly the Mars sample return mission. I don't know if you've talked about it yesterday. I want to just flash it up very quickly, because really the idea there is multiple spacecraft flying and a whole suite of things happening. So on the left, there's a rover which drills and which needs to actually find samples. And in the middle, there's a rover which actually then will fetch these samples. And at the end, you need to return these samples to Earth. So here's the rover which is underway. So that's Mars 2020. So it's going to be landing in early next year, and will actually roll through and drill and put samples in tubes. You see the tubes here on the ground. Then there's going to be a second mission, which is going to land a rover developed by ESA, which is the Fetch rover. So that rover is going to collect these little tubes and bring them back. And it will have to actually store them in a rocket. And that rocket is going to be launched again. So you have to actually bring the rocket as well. And the mission is going to bring the rocket as well. And the rocket is going to launch the container in the orbit of Mars. And then you need a third mission, which is going to come and collect these samples in orbit, and then from there fly back to Earth. Right? And so it's underway. So we've built half of the components. We continue to actually develop this, and between now and 2026, we think we can actually execute all this suite. And the first mission, the one to drill and to put the samples into tubes, is, as I said, is underway. It was launched earlier this year. So amazing mission, and that's a collaboration between NASA and ESA. And that's the type of things we're doing in the solar system. The last one I wanted to show you in the solar system is one of my favorites, really. It's and the solar system here is not to scale. So Saturn is really, really far away from us, right? So what I showed you so far was within a few astronomical units of the sun, so not too far from Earth. But there was this super spectacular mission, Cassini and Huygens, which Cassini was then again a collaboration with NASA in this case, where Cassini did fly to study the Saturn and the Saturn moons, and ESA led the Huygens probe. And the Huygens probe was on board of Cassini and was dropped onto Titan. Titan is one of the 60 moons of Saturn. It's a huge moon. It's size of Mercury near, and it's one of the few objects in the solar system, with Venus, with Earth, with Mars, which has an atmosphere. In fact, Titan has a much thicker atmosphere than Mars, and we wanted to study that atmosphere to understand what is it. It's mostly it's nitrogen. There's a lot of ethane and methane, and this is a movie which is going to show how. So you have on the left, right, you have the altitude of Huygens, 10,000 kilometers going down, still with a 20,000 kilometer per hour speed. It was really free fall at that stage. And it opened the parachute, then dropped to velocities of only 300 kilometers an hour, now 80 kilometers above the ground. And it did actually, these are real images. So we took images while we landed. It was amazing. So not only could we actually study the entire atmosphere while we actually passed the atmosphere of Titan, but something which I think nobody really had hoped for is that we could actually cross that atmosphere without actually damage, and then eventually land. And we saw as we dropped on Titan, we saw that there are lakes there. So there's a real landscape. There are lakes. Of course, the lakes are not liquid water. You're so far out in the solar system, the temperatures are so low that water would be frozen. But there are ethane and methane lakes. So there's a whole weather system in the atmosphere, not with water, but with liquid ethane and methane. And that, of course, led people to spin. Okay, so could there be life there? There's a liquid, there's a solvent, there are organics, but that life would not use water as a primary solvent, but would use ethane and methane. So, amazing sights, and something that there are lots of now ideas on how to get back to Titan, what to take on board to actually see whether there's life on Titan, understand whether these lakes could host any form of life completely different than we know it on Earth. Right? While on Mars we might be looking for life which resembles Earth, also life based on water. Here we would be looking at life completely different from life on Earth. So I'll move on from this, but these are the images that we brought back, including the final landing, or maybe let me actually just go all the way up to the end of this, but including the landing on the surface of Titan. So that's the furthest object where humans have ever landed. That's Titan, the moon of Saturn, and that was a European Space Agency lander. So very spectacular. So let me finish with a few astronomy missions. So certainly, we talked about helio science, we talked about planetary science, and now these are the astronomy missions. And they are the ones where my field, where I come from. So again, I try to not talk for hours. The one I didn't want to miss very often because it's associated with NASA, but there's a huge contribution from ESA, and in fact, half of the publications coming from the Hubble Space Telescope at the moment have European first authors. So the Europeans are using this very extensively. I wanted to show you the 30th anniversary image because Hubble celebrated its 30th anniversary in orbit this year. So Hubble delivered, I'm sure you know that, and it's fantastic material. If you want to inspire people in public talks, if you want to inspire your students, Hubble delivers the images which are just mind-blowing about the universe. But the mission I want to talk a little bit about is in fact this one. It's Gaia. Gaia is still operating. It passed its nominal five-year lifetime, and it's entering its next 5 years. And what Gaia does is it measures billions of stars, actually 1.7 billion of stars in the Milky Way. So it's remeasuring the positions and the velocities of kind of 10% of the stars in the Milky Way. So there are a lot of stars in the Milky Way. Measuring 10% of them is just amazing. And it produces these kind of maps. So that's a picture. It's not as if somebody has sent a satellite somewhere and took a picture of our Milky Way. That's the Milky Way in the middle here. Really, this picture is composed that every pixel you see is a dot, is a star which was measured, not only the precise position, but also the precise velocity by Gaia. So we have actually now a complete map of our Milky Way. And Gaia became, in a few years, the missions which actually, which most of the publications in astrophysics are based on. So it is now over 4,000 papers have been written with data from Gaia. It's a kind of support mission. So the other missions, like the Hubble Space Telescope, astronomers have an idea, they propose, and they get a few hours or a few orbits actually of measurement time. They can do what they want. Here, the approach was very different. We said we're going to measure the entire sky, we're going to build a catalog, and we're going to release that catalog as one, and people can do science on that catalog. So it's really opening the astrophysics to big data, to actually processing, looking at massive amounts of data and getting the information out of it. And it was spectacular. I mean, it's really used in astrophysics, but also to understand things like here, what's happening around our Milky Way, in particular, Sagittarius, which was a dwarf galaxy, which was in the vicinity of the Milky Way. We could reconstruct, like here in the movie, the lifetime, and especially the encounters. And when a smaller body encounters the Milky Way, it creates a density wave, it creates star formation. And in fact, we could actually see that one of the encounters was coinciding in time with the formation of the solar system. So we could reconstruct what could have probably triggered the formation of our solar system. And that was the encounter with a dwarf galaxy. Of course, once you have the data for all of these, you can also precisely understand what the gravitational field of the Milky Way is, understand much more about the dark matter which is surrounding the structure of the Milky Way, and understanding how this luminous matter are embedded in the dark matter in the solar system. But as I said, also the spectacular thing here is that once you have precise distances for all of these stars, you can start to make precision astrophysics. I mean, when you just see a light blob far away, you don't know exactly whether it's big, it's small, etc., as long as you don't know the distance. Once you know the distance, then you can actually derive all the physical parameters. And that's what Gaia allowed us to do. So let me finish with just one mission here, which is XMM-NEWTON, to give you an example of a high energy mission. Again, one of our flagships. One of the missions has been operating for 20 years. And that's really why do we go to X-rays, because we are interested in understanding all of the universe, especially the most spectacular phenomena, which are black holes, among others. And black holes, you can't see them, but they massively attract all the matters around them. They accelerate the matter around them. Then you have actually synchrotron radiation, which is emitted through this acceleration. And that's one of the best places to observe them is in the X-ray wavelength range. And the Nobel Prize, of course, this year was given to people who are studying these phenomena. So it's a field of astrophysics that this X-ray is opened. But not only that, you can actually look through the entire universe. So you take a background source, like here quasar, for example, or an AGN, and the light between that source and the XMM Space Telescope is absorbed by all the material between Earth and this faraway source. And you can, by studying this absorption, you can really look at the composition of the entire universe, especially the warm universe between us and the source that you're looking at. So I'd like to finish here. I hope I convinced you that the European Space Agency has a very broad and very diverse range of science missions. I put them all down here. It's a lot of fun to operate all of them. It's fantastic to see all the science coming out of it. and we're very proud of it, and we'll continue for many years. I mean, we're planning, as you see, 20, 30 years into the future to actually continue to deliver this to the science community and for humankind, really. So that's my presentation. Thank you very much.
Yeah, many thanks, Markus. Very, very nice in 1 hour, compact, a good summary of all the missions. This is our clock. You just managed on time. Very good. And do you have time for some questions, or you have to run to the next meeting?
No, I have time for some questions. I have another meeting, but it's that person can wait.
Okay, good. Because in the chat we have several questions. The first one was, where can we get all these nice videos and animations from? So will you give? Can you provide your presentation in PowerPoint?
I can provide my presentation, but really, if you go onto our main website, so just www.esa.int, and I think on the first page you will see a button called videos and a button called images, and you have all of them. So I took them from there. So everything I got is from there, and you'll find there not only what I showed you, but a lot more. So if you want to take spectacular images, I think the easiest is to use the search box. What we haven't, I regret a little bit that we haven't managed to classify them to make a nice gallery, right? The other site which I like to use is for Hubble is a site called spacetoLescope.org. So if you type in one word spacetoLescope.org, you'll find all the spectacular images from Hubble. Very nice sites, very nicely organized. But for all the videos I got are from esa.int, and videos, or search for, if you want solar orbiter video, and you'll find a suite of them. So they're all available there. You can download them all free. But I'm very happy to actually provide my presentation. It's a keynote presentation, and so I know that many people use PowerPoint as well. I don't know if it's easy to extract the video from one presentation or not, but the source really esa.int.
Okay, many thanks. Markus, can you see the chat window, or should I read the question to you?
But I would need to scroll up if you wanted to see all the questions. I don't know if there's somebody filtering. And thanks to David for putting the links in there. Yeah.
So there's just a big block. There are two big blocks of questions, if you see. And the other one from Diego. So it's a fascinating presentation. If it takes 10 years or so between missions design and launch, does that mean that there's always something of a technology lag?
Yes. So very good question. Thank you very much. Yes, there is always a technology lag for two reasons. Because of course we try to actually incorporate the technology developments. Sometimes we have to develop the technology ourselves, and of course, then we need to actually. A space mission is very expensive, so the planning is we do that very careful. We have something that we call the technology readiness level. So understanding whether technology is developed is one. If you can make a prototype, that's great. Making it reliably working, that's the second step. Making it reliably working in space, that is, very cold conditions, vacuum, or if you're close to the sun, extremely hot conditions, etc. That's yet another step. So we really need to actually take all these steps in technology development to then get ready to actually fly a mission. And it's true that very often we fly technology which is maybe 10 years older than the technology which exists today, but at least in these 10 years we could prove that it will work reliably in space. It's nothing more embarrassing than flying something all the way to a comet or to a planet and then realizing that it jams or it doesn't work. So yes, it's something we have to live with, we know that. But when we develop these technologies, they're often forefront. I mean, we're developing them, or the industry is developing them for us. By the time we're flying them, they're a little bit obsolete, but they're super reliable. Sorry, and then there was another question. I'm trying to.
There was another block of several questions. One was about extraordinary how to collect the samples from Mars. Really interesting. The life in Titan could be geothermal life, picking the energy from continuous activity because the sun is a bit far. So
they all good questions. So I don't know what was the question about the sample. No, the samples from Mars is no question. Titan, life on Titan. Well, it's the introductory course that I give at university is 30 hours. So I'll try to condense that in 30 seconds. But yes, life. We're looking for So all life on Earth is the same kind. Okay, so that's something which people often don't realize. They think that they are very different from a piece of grass or a mushroom. You're not. Okay, the cells are exactly the same. You use exactly the same 20 amino acids to build proteins, and you store the information about how your genetic information. You store it exactly the same way as a mushroom does. It's the same DNA structure. The cell, the lipids you use for the cells are very similar, etc. So we know one occurrence of life on Earth, and that's water-based. Water as a solvent is what allows all the chemistry in a cell. And we have a certain way to storing things as in a DNA and a certain way to do metabolism. And that's what our definition of life is, because we only know one occurrence, right? So we say it needs, it does a metabolism, needs to be able to replicate, and it needs to undergo some evolution so that you can multiple forms. So when you look for life elsewhere, like and different than the life as we know it, you still make assumptions. Okay, so there's still a metabolism, so there's still a source of energy. So if it's not the sun, as for most organisms on Earth, it can be thermal energy, it can be chemical energy. So these are the kind of two other sources. In fact, we think that life on Earth started with thermal energy near hydrothermal vents and deep in the ocean. It could have been also chemical energy. So these are two sources of energy that could be used in Titan. It's also when we look at life, for example, on moons of Jupiter, like Enceladus or others, we're looking at thermal energy there because you're so far from the sun that life takes what it gets. Okay, so if you're far from the sun and the solar power is not there, you'll use another source of energy, thermal or chemical. And then you need other ingredients. So you need another solvent. If you're at very cold temperature, water is not a good solvent because it's frozen. But liquid methane or ethane could play the role that water plays. It has different chemical properties. So then you start to understand, okay, so how does chemistry work? Carbon bonds, which are very solid, why our organic chemistry is based on carbon, are great at our temperatures. At much lower temperatures, if you want to do chemistry, I mean, really making different reactions, carbon is too strong. You need to go to something in the periodic table which has the same properties but has weaker bonds. So that's silicon, for example, which is just below carbon in the periodic table. And so you can actually, that's how these ideas of silicon life developed and so on. So yeah, as I said, it's a 30-hour lecture to get the introduction to this, so I won't do justice to it in 30 seconds. But you get a little bit the ideas that are behind this astrobiology, looking for life in our solar system. So I see that silicon based on carbon. Could it be true? Is it science fiction? No, it could be true. So I mean, the main message I always pass to my student is be open-minded when it comes to actually look for life. Since we know only one occurrence on Earth, we might. I'm sure that when we discover life elsewhere, it will be very different, yet very similar to what we see. But you need to be super open-minded. Otherwise, we will miss it. We will look for one thing, and we will completely miss the obvious in our face. So yeah.
Okay, so if there are no more questions, then again, many thanks, Marcus, for taking your time. I know you're extremely busy.
It's always a pleasure. I'm happy to share the excitement. We do exciting things, and I'm very happy to actually share them.
Okay, many thanks. So, your presentation will be available afterwards. So, okay, I'll tell you back.
Thanks to everyone for listening this morning. Bye-bye.
Thanks. Okay, so we go to the next point, and we come to another very exciting point. Now it's time to work yourself a little bit. So we have Beatrice again, and she will introduce you to the mysteries of the universe with one of the best tools that were ever designed, I think, to really explore the universe yourself. It's called ESASky, and it's, in my opinion, one of the major tools or projects that are really helping the public, and not only the scientists, because it was developed originally for scientists, but it can really also help the public to just go out there and explore the universe. And Bear will now tell you in the next 50 minutes about this tool.
Okay. Hello, good morning. I wanted also to present to you a scientific challenge that we have done in the CSR team. As you know, we use as much as possible real data, real scientific data, and in this one, we are going to use the data from the archives, from the scientific missions that were introduced before by Marcus. So I'm going to, as I want to follow the same logic as I was doing these days, so I'm going to share my screen. And first of all, I would like to ask you, what do you know about the astronomical objects and the light? And then we will go through some basic definitions, and then we go to ESASky. So if you go to, I'm going to share my screen, as I said. So if you go to the mystery of the universe.
Yeah, your sound is a little low. Can you turn up?
Okay, sorry. I will check. Thank you, David. I will check why. Where? Sorry, at the top part. So mute the opposite. So my sound more switch. What should I do? What should I need to define which is my what I am using for listening. So I'm going to the main properties, and I'm going to define. Sorry for the delay. I'm using the headphones, so I will try to speak louder. Maybe it's me. Not much energetic today. Okay. Isn't it better? No? If I speak louder?
Okay. Try to speak louder.
Do I speak louder? But do you hear me well, or what should I do, David? Tell me.
I can hear well.
Okay, so I don't want to lose more time. I will speak louder. Thanks a lot. So I would like, if you don't mind, to come back to the GRASP virtual campus, and let's go to the Mentimeter first. So if you click on the Mentimeter, you will have something like this. And I would like, if you can pay 2 minutes, because it's not more, to see what do all we know about light, about missions, space missions, and about objects in the universe. So I don't know whether you start already. I don't see the chat. Did you start already? It is better now. Okay, thank you. So I'm going to put, you have it in the virtual campus here, but you can also have it. I'm going to put it here in the chat, so you can do it yourself. This way, as I said, the Mentimeter, the code only lasts 2 days, so with this link, it will always work. And we can go through that together. So are you doing that? Maybe if you are replying to the Mentimeter, you cannot reply to the chat, but just to be sure that you are with me here on GRASP. Nobody, yes, thank you, Diego. I thought maybe you also needed a coffee as myself. So we will see together what do we know and what we don't know about the universe in general. One more minute and we go. Okay. So the Mentimeter was defined for you to work alone. if you are using Mentimeter yourself, you would need to customize this. Click. So you don't show the image and we can see the answers. Okay, so I'm going to go one by one so we can do all together. Most probably you are familiar with the Mentimeter, but so you have the two options, this audience space, that is the one that I was defining. And then you have also the present. So I'm going to, with the same one, you can do this in your class. So your students can answer, this is the idea. Your students can answer themselves, and then you can check all together the results before starting the class. So it's an initial evaluation, an anonymous initial evaluation. So, okay, what is light? It's both a wave and a particle. Yes. It's an electromagnetic wave that covers visible and invisible light. Yes. So let's see. So correct? It's an electrostatic, no, electromagnetic. So it's not an electrostatic. It's only the visible. No, it covers the visible and the invisible. Super. So I start from the basic, as you see. So the type of light from the lowest to the highest frequency. So it's radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. So here you swap. Okay. What else? The missions of the European Space Agency study the light from the entire electromagnetic range. Yes, has, unlike Gaia, study the Earth. This was a false answer because Gaia is used. It has been called sometimes Earth, but Gaia, as it was mentioned by Marcus, is observing, is doing a census of our galaxy, so detecting the locations of all the stars in our galaxy. So it's not studying the Earth. What else? Stars are large gas balls in a plasma state. Okay, all of us, most of us agree. So this is the real answer. Have chemical but non-nuclear reactions in the core. We saw yesterday with the sun that it was not real, and are very stable and do not present great changes in life. We saw that they are evolving in life, and depending on the mass, they will evolve one way more dramatically, or with a supernova, as a supernova at the end, or less dramatically as our sun. Which of the stars in the Orion constellation has highest temperature considering their color? So here you had the 5 stars in Orion. This is one of our activity, and by color you identify which is the one that has highest temperature. Is bluer. So yes. So correct, perfect. So you already know that is a relationship between colors and the temperature. So very good. A star like our sun will evolve in 5 million years into a white dwarf. It won't end as a supernova and then a neutron star or a black hole, but it's a medium-sized star, so it will evolve as a white dwarf and a planetary nebula for the outside part, the outer part. Super. Good. What are the phases for star formation? So it goes from a diffuse cloud to a dense cloud to a protostar, a star, and then a death star that ejects the material to the outside back to the diffuse cloud, and other stars will start their formation. So yeah, very good. And what else? Galaxies are all similar to the Milky Way, do have several shapes and sizes, are formed by stars, and matter among them, that is called interstellar matter, join gravitationally. So yeah, you're doing very well. The interstellar medium are dust particles that have regular and large shapes. It has an average temperature of 1000 Kelvin, consists of 99% of gas, and 1% of dust. So yes, you know very well. Okay, so we have finished with this Mentimeter. And so this gives me some hints, and I'm going then fast through the first part of the presentation. And because what is important here is to talk about ESASky. That is the scientific-driven portal that the ESA archive team has developed for all of us access to the real scientific data from the space missions described by Marcus. So I'm going to move the chat here. Okay, so this is discovering the mystery of the universe, or revealing the mysteries of the universe. And how do we present this? This challenge is not only superheroes are able to see the invisible. Here we have one detecting X-rays, another infrared, but also ESA missions. So we ask them which one are observing what do you know about the missions? So this way we introduce about the visible colors and also the ESA missions. This is the same as today's teamwork and 14 to 18. I won't go through this because we don't have much time, and this is what we already did. And we already want to spend really the time in the ESASky. So 5 more minutes and we go to ESASky. So as you mentioned before, the light has several colors and can be divided in several wavelengths, the electromagnetic spectrum, and you already know that the ones that has the longer wavelengths is radio, and the ones that has the shortest is gamma, of course. And here, what is important is for we to know that this we will put it later again, because you're going to do an exercise with ESASky, one of the activities that we have, and is to see that for the different temperatures, you don't see this well, but anyway, for the different temperatures, what can you see in an image? So when you observe the universe in gamma rays, that for that we need satellites, as it was mentioned during several days, we observe objects or processes that are emitting at temperatures of 10 to the 8 kelvins. And this is matter falling into the black holes. As Marcus mentioned, we don't see the black holes themselves, but we can see the matter that is falling down, and in this friction is arriving to very high temperatures of 10 to the 8 kelvins. Then we have the X-rays for XMM-NEWTON, for example, and what it observes are processes from 10 to the 6 to 10 to the 8 kelvins. And what are these? This is the gas among the cluster of galaxies. Cluster, we call clusters when they are together several objects, so it's a cluster of stars or cluster of galaxies. And in this case, X-rays observe the gas among the galaxies, the cluster of galaxies. Also the hot gas, when a supernova explodes, these remnants, what we said, the remnants of the star, are hot. We can see them in X-rays. The corona of the sun, we already saw it yesterday, and also neutron stars. We said that when a very massive star died, it will end up in a black hole or in a neutron star. What do we see in the ultraviolet? I will put this table later on for your exercise, but so in general terms, we see very hot stars, or hot gas in the supernova as well. For the visible, we see stars, and we see also clouds that has a hot gas. At the infrared, we see cold stars and also planets that they are emitting with the low temperature that they have. They emit. They are not as the stars that they have nuclear reactors inside, but because of the temperature, they emit in infrared. Also, we see cold clouds of dust. We were saying before that in the clouds, interstellar matter that is formed by dust and gas is where stars get formed. So we can see that in infrared and microwave and radio. So the dust is visible at the infrared, and the gas is visible at microwave and radio. Okay. So we saw yesterday that the sun can be observed in different wavelengths, and all the objects in the universe may emit at different wavelengths, and for that we were saying that some of them can be observed from ground and others in the visible, but the rest need to be observed from the universe. And then let's go quickly about stars. So for that, I want to tell you about the sun that we already knew yesterday, and I want to compare other stars with the star. So with the sun, other stars with the sun that we know is already familiar to us. So we said that more or less 1 million or 1.3 million Earths would fit into the sun. But if you compare with other stars, the sun is this size. So it's not even if for us it's a very big star, it's not the biggest one, as you knew. So what else? The mass of the star, of the sun, the mass of the star is like 336,060 Earth. But there are more massive stars that can be 120 times the mass of the sun, this big one. And there are less massive ones that can be 0.08 times the mass of the sun. So for you to have some reference. The temperature of the sun. When we talk about the temperature of the sun, we don't tend to talk about what is happening in the nucleus, where there are these reactions that we mentioned yesterday from hydrogen to helium, because it's in the main sequence phase. But we tend to talk about the superficial temperature or the black body temperature. So the sun is here. You can see that we mentioned it yesterday, about 5,500 centigrade. So when the difference is, 273 between kelvins and centigrades, no, degrees. Yeah, centigrade. I don't know now the word in English. So yeah, centigrades. No? But what I want to show here is that really the sun, compared to other massive stars, is 10 times less temperature. And you also have others that are quite lower. So we have a variety of stars, and the colors are giving us, similar to the balls, to the bulbs, are giving us the temperatures of those objects. We have also another activity of this within what we are giving to you as the CISAR activity. What else? The age of the star is halfway through its life. We were saying yesterday it's 4.6 billion years, and it will evolve. Here is the sun. As you were saying, it will evolve in a red giant, planetary nebula, and finally a white dwarf. You see that very massive stars like these blue supergiants will evolve more dramatically, and others will just. Brown dwarfs are not even stars; they are failures because they don't have enough mass to start at their nuclear this nuclear reaction from hydrogen to helium. But so you have some reference. You can read this later. You have some reference about how they will evolve depending on the mass. And this is more in detail. So we say that stars, as humans, have a birth moment, a main sequence, then they get old, finally they die, and then there are some remnants. So depending on the mass, they will evolve in one way or another, but they are not stable during their life. Also, I wouldn't go through that, but we also study the stars through their emission. So we can see radiation emitted due to the energetic transition of an electron. So we can see an overlap spectrum. So when we observe a star, we see all the components that they have in one go. Later on, we compare with what we know, with lamps that we know, and we also have an exercise of this in CISAR. You compare so you can identify what are the elements, but you have something like this for emission lights, the same for absorption lights. So here you can compare the spectrum of the sun that has helium, hydrogen. Another thing, classification of stars. As we were saying, stars can be classified in colors. So here you have the different colors. And if you go here is the surface temperature, no? What we are talking about. Also, they can be classified by the spectral type that is given mainly by the spectrum that we saw before, and also by the luminosity. So this is like a picture at the moment of the stars. The light that we have is how we see them at the moment. And for example, the sun is currently in the main sequence, what we mentioned, but it will evolve, it will become bigger to a giant, and then it will finally come back here to a white dwarf. So it's better if you see this with this nice tool that is a star in a box. So you also have access to this in our guides. So you can study with your students how much would it take for a star, depending on its mass, to evolve and the different phases that they pass through. So it's quite interesting as well. Apart from the stars, we have the star clusters that they can be globular clusters if the stars are old and is very dense and very much joined, no? They are very much joined. Or they can be also open clusters that are clusters, so let's say stars together that are joined gravitationally. But for the open stars, they are bluer because they are more young, and also they are more gravitationally, they are looser, in the sense that they are not so much packed, not so much dense, the clusters. Then we have the next step is the interstellar medium, and you see here the contribution of interstellar dust, and the rest is the gas, as we were saying, 99% gas and 1% dust. And here is, at the right part, is like the size of a dust piece, let's say, of a dust grain. And later on, we will see in ESASky how this may be blocking the light and making that it could be a hole, but it's not indeed a hole. Is that the size is matched with the size of that wavelength of the light at that wavelength, and is blocking the light to pass through. But we may see it at a different wavelength. We will see it later. So this is the matter that is among the stars, that is not vacuum, within a galaxy, for example. So the effects, as we were saying, is optical extinction, that the light may not be seen, or may be seen less bright, or may even be redder than what is in reality when it passed through this cloudy matter, the interstellar matter. So here we may think that there are empty space, but when we look at a different wavelength, we see this region. So it's not empty, just block at this wavelength that I think is optical, because of the size of the wavelength is similar to the size of the grain, the dust grain. And then we go to the galaxies. We have here what is a representation of our Milky Way. This is how we think it is. We have never gone out from our Milky Way, as you know. And the sun is around this part. This is a spiral galaxy. So galaxies like our galaxy has a disk. It has in the middle a bulge. The sun is here in the disk. It has a big stellar halo where a lot of dark matter is considered to be, because some studies made by Vera Rubins and other scientists. And you see that all the stars go to the outside part, that is the globular cluster, and the brightest stars, the bright clusters, tend to be close to the disk, where stars get formed mainly. All this is interesting because when you're going to observe later on the galaxies in ESASky, you may see these things, so you can get the output out of it. Otherwise, you only get the colors. Also, we have several shapes for the galaxies. This is the Tannin fork diagram. We also have an activity of this type where the students need to characterize the galaxies that they see. We give them a list and the shapes, so they know, they identify them by these names, or before by names that they imagine themselves. And this is how Hubble thought the stars were evolving. However, I'm not going through this, but the latest studies seems that the stars are not, the galaxies are not evolving that way. They don't evolve from a spiral to elliptical, the eldest one, but it depends on whether they evolve isolated or they are merged interactions, and then they form elliptical galaxies. But I'm not going through this now. So let's start with the challenge. For that, we were saying that we go through ESASky, that really this is the important part, to let you know how ESASky is. So I have ESASky here, open. But you can do it if you go straight away to Google and you say ESASky. So you can go to that link. The first thing that you get is ESASky. So it's a free access to all the scientific archive from ESA. So it's amazing. All the data has very, very well packed. It's very nicely explained. What is it? Not the details of the different wavelengths or the catalogs. That's why I'm explaining you this a bit. But when you open, you may see any picture from the background. Not always should be this, but you will see something like this. So I would like that you do this with me. Otherwise, you won't remember maybe how to do this. So I want to see in the chat whether you are following me and you have access to ESASky. So you saw that I did it as easily as coming to Google and typing ESASky. I will do it again. So it's not something that you need to remember deeply. How was this, the web? I didn't remember. I would never go back. No, it's just ESASky, European Space and Astronomy, European Space Agency, and Sky. So only that, and it will go. I wait for you here. I don't see the chat. Yes, I'm there. Okay, okay, I find it. Okay, super. So then I will continue. When you go in, the first thing that you may see is whether you want it in English, in Spanish, or in Chinese. So this is quite amazing. And then we are going to use the English. By default, it's like this. Then you cannot do anything if you don't define whether you want to be a scientist or you want to be an explorer. I recommend that for starting, you be an explorer. So ESASky is an application that allows you to visualize and download public astronomical data. So I'm going to be an explorer. Okay, so I get used to ESASky with less options. What do we see here? So if I go here, you see the coordinates of where I'm pointing in the sky. So it's reading where I'm moving. So this is triad ascension and declination. It's the way that astronomers tend to define a position of an object in the sky, and this was explained yesterday. So this is the field of view, what you see here, and if you go out, you zoom out, you see that it increased to 1 degree, and if I zoom in, I go to 32 minutes by 17 minutes. This is the DSS is the Digital Sky Survey, where this data has been, it is a network of telescopes on ground that has observed this part of the universe, and it comes from this catalog, from DSS2 color, this catalog. Okay, what else do we have here? This is what we selected before. We wanted to be explorers. Okay, so let's keep being explorers, scientific mode. And then what do we have here? We can put a grid here where we can see the right ascension and declination we set. For the time being, we are going to remove this. What is this? This is very nice. So because if you do activities with your students, you may want they to find something and then they put it in a document and explain to you. So with this, you can make a snapshot of what is here. So you just can download this picture. Good. With this, you can share, and this is used among the scientists as well. So when you are observing, for example, a satellite has observed a region in the universe, and suddenly it's a very bright line or something that was not planned by the astronomer at that wavelength because they wanted to observe the universe in X-rays, and suddenly something not expected or in optical or whatever. So I have seen scientists going to ESASky to go through we will do it later, to go through the different filters to see what is affecting that image. And then with this link, you can share, copy the URL. So if I come here, or you can send this in an email to another colleague. Please have a look at this because we have found something unexpected in these coordinates here. What else? These are questions and feedback. And this is very important because later on, when you do the exercise that we propose to you for this course, you will type here the object that you are going to observe. So I can go to one of them, and it's telling me M1, really? Yes. So wow, I go to the crab. Amazing. Okay, so these are the icons that we have here and the options that we can have with them. And then we go to these three options. This one is very interesting because the team of the ESA archives team made very simple to go from one mission to another mission to observe the same target. You don't need, as in the past, you need to access one by one to each of the archives of the missions, and then you need to find your target. You need to see whether the size of your image is as you want it, or just you download the raw image or the process without any option. And then yourself, you need to align all of them when you wanted to combine them. So it's very nice, all this work done by the teams of ESA Archive that make us life very easy. So we're going to go through this object as the different missions have shown it. So for some of the images or for some of the objects, you may not have that wavelength because this has been done the other way around. So all the images from all the scientific missions has been collected and then are shown here for us, but not all the objects have been observed in all wavelengths. So the real thing was, a scientist really want to identify something new, or they think it's worth to spend some time on a satellite, of a satellite that is very expensive to observe something because of this supernova, or because whatever, any flare, anything that is not known. So they get the time at the mission, and then this data is given to them. For some time it's private, and then later on it's made public to everyone. So because this is the logic, not all the universe has been observed in all wavelengths. That was not the purpose. But as soon as we have the ESA archive have new data, they link it to here, so you can go through that. So we are going through this object, the crab, that is the remnant of a supernova, very massive star, and we are going to see it in different wavelengths. So let's go to the soft X-rays. Wow, this is very different. So what do we see here? We see something very saturated. What we see here as well is the shape that the camera, this is we hear XMM-NEWTON epic color. So epic color that to be done together by, combining the three cameras that XMM-NEWTON has on board. And there are two small and one epic. So what do we see in reality is a very, very bright object in the center that, as we know, is a neutron star because it's the final moment of a very massive star. And then we don't see the outer part. We see the bright stars in the center. Let's go to the, do you see what does the difference with it's the same object in the optical, not in the visible. And if you go to X-rays, oh, it's a bit slow, sorry. It's a bit slow. Okay, you saw how I did it. So I didn't change the shape. So the field of view is the same. So I continue, and I'm going to add also the image from the near infrared, for example. And this is a 2 mass color. So also 2 mass is 2 micron. We can find it here, the name of 2 mass. 2 mass is a 2 micron all sky survey. And this is how the universe is, the universe, in this case, the Crab nebula is seen in this catalog. So it's similar. We don't see these nice filaments that we can see in the optical one. So very well defined when we go to the near infrared. But here we can see also that is some the stars. The stars not, because this is the added star. We can see the outer part that is has red color because the light from the inside is being remitted as well. So we see here in red. And then if we go, for example, to far infrared, we see this. In this case, the contrast is not that good. But what do we see in the far infrared? We were saying that we see the gas, no, the gas of the remnant of the outer part, and it looks quite similar in shape than the optical. Okay, so let's go to the next one. Later on, you're going to do this in the activity, or at least this is an activity that we propose you to do until tomorrow or afterwards. And I don't want to take more time because ESASky has many things. So this second icon is where you can select the target list. You can upload one that you may have, but for the time being you don't. Or you can take one of the selected target lists. So all these lists has been collected by the ESASky team, that is the team of the ESA archives here that are located at ESAC. And here we have 3 of them, 3 of these lists that has been made together with us, because the activities that we do, most of them are done together with them, that are the experts in ESASky. So there is a selection of objects in the interstellar that are interstellar medium, yes, that are clouds. So we can observe the interstellar medium with it. For example, is the Horse Nebula. This is also a very famous one, and maybe you are not familiar with this image, because what do we see here? As the last filter that I was selecting was far infrared, what you see here, sorry, is indeed the dust emitting. So, or the gas, no? The infrared is the gas, and we were saying that the radio was the dust. So what do we see is how it is emitting the cloud. However, you're more familiar with this image because it's where the area is dark because the cloud, as we were saying before, is blocking the light from behind. So the dust grains are blocking the visible light. And if we go to soft X-ray, it's low. Okay, it doesn't matter. You can do it yourself because it's also part of the activity. What else do we have here? Apart from the selection of target lists done for us, the galaxies, so you can classify as Hubble did in size some galaxies and this is the interstellar matter, also the colors of the universe. They have created many lists and they are associated by type, let's say. No? So these are spiral galaxies. You can go through them and you can see them. And this is amazing, M51. I mean, the soft X-ray didn't work well, but I am really in the optical, but you can go also to see them in the near infrared. And then you can close all these options. And then we come back here and we continue observing there in the near infrared. What else do we have here? We can also observe bright nebula. We have dark nebula and bright nebula. We already saw before. Globular clusters. Globular clusters are all stars, cluster of stars. As Rosa was mentioning yesterday, the universe, most of it is black and white. So what you are seeing here are fake colors for you to see the contrast or for you to see the difference wavelength, the invisible colors. So as we were saying, globular clusters tend to be are clusters of all stars. Here they are representing it sort of violet, but in reality they would be redder. So just these are not the real colors. And this is real problem on when you have some bright star here or here, depending how it's reading, that is saturating the image. So it has been as much as clean as possible, the image collected by the satellites, but it brings still the reality because it's scientific data for you to observe, only color it. So most probably when you see some of these images on the web, you will see that they look much nicer, but it's because there is a lot of Photoshop. This is the scientific archive. Interacting galaxies. We have here the Wilbur galaxy. So here is the second one. So galaxies that are slowly interacting to each other. Messier 60. Here we also see, this is quite nice as well because we are at the moment at the near infrared. If we go to the optical, we also see the two. If we go to soft X-rays, for some reason, soft X-rays is not working well today. We also have Chandra. Sorry. If we go to the far infrared, we only see one of them. Do you remember there were two? Why? Because one of them is not emitting in infrared. Infrared, we were saying it was low temperature, so they are is where they are old. If you have old stars or cold dust, you will see this in infrared. But so this means that this galaxy is quite young, and that's why we don't see it in infrared. But we see it very well in optical or soft X-rays. So what else do we have here? So here you can yourself, and we also in our activities propose you to go through to do a trip through the universe together with ESASky, supernova remnants as well. We don't see much of a remnant here because we are in soft X-ray is not working well. In the optical, when I'm in this case today, I mean, ESASky works perfectly, but today for some reason this is a bit stuck. So maybe I better remove it. Yeah. So when I add it late again, maybe it was stuck. Yes. Oh, amazing. What was it? This is a the outer part of a supernova. We were saying it's the end part of the end life, no? The last time that the star, how to say this, is when the star die, no? When the star die itself is a death star, and the outer part is showing this in X-rays. We saw this before, that we were expecting higher temperatures in X-rays for dead stars, supermassive stars. If we come to the optical, we don't see anything because it's not emitting, no? This process, neither the brighter object in the center, the neutron star, nor the outer part that is very hot is emitting optical. So here we don't see anything. We see another star close by that is quite bright, but nothing else. If we go to the far infrared, I'm going to close. Look, this is what I was telling you before. At the moment in the far infrared, there is nothing in this area. Maybe ESASky is still populating the archive and they have images, but they haven't been uploaded yet and fixed to this position, but there is not in the far infrared, but we can go to the near infrared. Also similar to the visible, there is no how to say, any hint that it may be something here like a dead star. We don't see anything. We just see a field, plenty of stars, very nicely, different colors, fake colors again, but they tend to, the way that they have defined it in general is that the blue are the hottest one and the red are the coldest one. So let's try to find whether in the mid-infrared it is something. No, nothing. So similar. It's like you don't realize it's a dead star here. That's why it's important to observe the universe in all the wavelengths, because otherwise you don't get the picture of what is really happening. It is a pity that we don't see here, because in the far infrared, we would also see, as we were saying, let's go to the radio is not very well. The size is not very well, the resolution is not very good in radios. But it's a pity that we don't sub-millimeter, that we don't have an image now about this, because you would also see the same shape or quite similar to X-rays. Okay, because it's the outer part of the, you will see then the dust itself of this explosion. Okay, so apart from this, that we really encourage you to go through this, and in our activity, you can do it with some logic, with quite some logic. You have here, if you just want to play on a rainy day, to discover the universe. So anything that appears is always, you could check here what is the filter that you're having. And I decide I'm going to change to far infrared. And then again, it's nothing obviously here. But if I click, I can continue. Okay, here it is, the Tycho supernova. So the Tycho supernova in the mid-infrared. And if we go to the soft X-rays. Okay, this now here you see what I was telling you before in the other target, that in the soft X-rays, the X-rays by XMM-NEWTON, and in the sub-millimeter taken by, sorry, in the mid-infrared, here you don't see much. With Herschel, you don't see much, no. But with the mid-infrared, you see also the bubble in this case. So it's the outer part of the very massive star that has died and is still giving this shape around. And in the center, if we go, yeah, we wouldn't see the center in this case. This is a Tycho supernova that was detected by the first time in the 16th centuries by naked eye, that suddenly it was seen as bright in the sky as if it were a planet. So you can also give to your students not only the physics behind, but also you can explain in some part of this of the history of how they were detected. And here ESASky gives you some hints so you can look for it. In our guide, we also have a description of what is every object, also with some history. Okay, so what else? We finished to be explorers in ESASky. So I'm going to change it to be now scientists ourselves, and then you see that we don't have the diets because scientists don't play like, I mean, they play on a raining day, as I said, and then you can go to the Explorer. But for the daily work, they really need to go to the objects and to the data that they need to analyze. So here we continue having these different filters. And again, this Tycho star, this supernova remnant is not visible in optical. And here we can go straight to the data. As we were saying, ESASky is not only for showing, but also for downloading data. So if I want to know what images do I have for this region, I can go here, I click here, and it will plot the images or the field of view of the the field of view of this region in the sky observed by Hubble in the optical. If I go here, Herschel, we will have the region observed by the Herschel instruments, in this case the cameras, because we are in image part. So I want to download this part, this one. And then when you click here, I already closed it, you have here several catalogs that you can go through them. Once that you click one area, it will tell you what observation is this. So not always is clear what they are telling to you, but you can have a look closer to it. These are the coordinates of the region. Target name any, because apparently this one was not on purpose to observe Tycho. However, this one named Tycho, let's go to this. This one that is clicking here, so you can do also the other way around. This one was an observation requested for the Hubble telescope to observe specifically Tycho by a group of astronomers. However, this other one that we selected, it doesn't have a name because it's a field of view, a region for a field of view for some scientific studies, but they didn't give the name clearly. Sometimes scientists, when they ask for something, until they don't have the results, they don't really tell to the community, so they don't give the names. And this is information in the archives that scientists are giving to the teams, to the space teams that are defining and planning the observations and taking them. That's why you may or not have a name here. Okay, so coming back to this, we were saying to this, to the any. Okay, so here, if I click here, I can see bigger that region. And we see here some trails, like some cosmic particles passing by or some, during the time that the images were observing. This is real data itself. These are bright stars. There's an empty region here. So maybe some bright object passed by quickly. Oh. We don't have here information about the flux itself. But we have an initial visibility. If we come here, we can download ourselves the image. Okay. Keep. And you already see that it's star, so it's compressed. So it's downloading this here, and I hope later we can see it. Okay, so you can do this with any part of the universe that has been observed by ESA. So you type here your target. We were in with the crab, but you can go to M31, and you can do the same with this nice galaxy as well. You click here, and you see what has. You can identify the regions that has been observed. For example, let's go to Akari. And this has been observed. And again, I want to go here, click to this one. Have I clicked? Yeah, click here. And again, I can download it here as well. Okay, this is information from the catalog that you can see. So there are not many observations from Akari in this region. Let's see about HST, near infrared. There you have quite many. Also, you can see here the field of view of the cameras, no? Whether you have a very small field of view and maybe more resolution or wider field of view. It's not related, but it's the field of view of the instrument. XMM, for example, has a very wide field of view, as you saw before. So in a single image, you may take almost 1/3 of the galaxy itself. Okay, so this is this one. No, we were saying that you can access straight away to the images of the archives. Just clicking here very nicely and downloading them. You can look at this bigger and then you can download it here. Okay, let's go to the next one. This one are the catalogs. So I'm going to clean this because otherwise it will be a bit messy. Click. If I come here, I want to see, for example, Gaia, the Gaia catalog, what parts of this total amount of objects is, wow, is very, as I said, Gaia is sampling the universe is different to, will show the objects. Okay, so it's not as other missions that are like telescopes on ground that are observing regions that has been requested by astronomers and has passed a big committee of experts and given the time, but it's doing a survey, so it's continually turning around and taking images of the universe. Also, because this is the reason that we have that many images of the galaxy and the outer part of the galaxy, because it's another one by Gaia. So in this case, there are too many. And let's see whether I can zoom in and do this again and try to get less, because it detects the ones in the field of view. Gaia. Okay, this is the time. Okay, so you can go through the different catalogs, and then you can look at the different regions in the universe. Again, it's 5,001. So I'm going to use very quickly, Michael, a very a smaller catalog. I'm going to stop so you can understand what I wanted to tell you. And for example, Thomas, even if it has many, tend to have less. So I want to observe. I want to know, not to observe. Sorry, I want to know what is this target about. So for this, we have straight access to ESASky. It has always no, it has all been coded very nicely and all together. So you just have to click. It gives you the possibility to download the images or to identify in the catalog what it is. And it connects, if you right click, to the different database in BAT. So what is this? Because I want to know, wow, because it's a big region, it may be any of these ones. No? So there are quite some. So let's reduce the size. We close. Here you can define, I don't know, 1 arc minute submit query. So then it reduces what can be seen in this field of view. This doesn't work well. Okay, so I don't want to go into detail. This is a catalog that we really use, the SIMBAD catalog. Each time that we identify something in the sky, we put the coordinates and SIMBAD tell us what is it. So just to know that you have direct access from ESASky to it, also to the net that is more for galaxies, but also is a catalog of this type. To be shared, that is a complete set of catalogs. And all this just by clicking on a nice image. So here you can have access, as scientists do, to all the details of that object and the name, the coordinates, and the magnitude that you will see later on with Naira and Fraser. The magnitude, because these objects are not nice objects that have been identifying coordinates, but many things about it has already been studied. And so you have access to this magnitude, depending on the depending on the satellite, it has been observed in VR. You can observe this in optical from Earth. You can also observe it from Earth, but tend to be more for the infrared. So you have access to all the catalogs. And in our activity, we also show you how accessing to some nice looking images, and clicking here, you can also plot the black hole. Sorry, the black body, excuse me. You can plot the black body because just reading from the data already taken by other missions that are within this catalog. Okay, and if we come here, we also have this the spectra, not only the images, so you can also download it here, and also here. It's not you can also here the other way around. You want to plan your observation, and you want to see how would it be, and you can define here. So the James Webb Space Telescope that is going to be launched soon, and it's a collaboration between NASA and ESA. You will see if I was pointing to these coordinates, what would I see in the sky? So, and here is super interesting. You have access to the real scientists, the real papers that has been published for each of the targets observing the universe. So the ESA archive team has done a huge work and keep doing that, updating it, collecting in a very nice image that you can see in many places, all the information that is the scientific information of it in a very nice way. So as I know I'm out of time, so I just tell you, when you have the time, please try to fill this table. You can do that following our activities that are here at the bottom part. We have several ones, but that one can be done here in revealing the mysteries of the universe that we again have just cooked for you. So thanks a lot. Sorry, I'm very late, Michael.
Many thanks, Bear. No, it's not that bad. 4 minutes is okay. 4 minutes extra. No, I think, as you have seen, it's an enormously powerful tool. You can do a lot of things. You can do real science. You can just do demos for your students. It's really a super tool to use. Are there questions for Bear? No, I don't see any questions. I just see the people are very happy and very impressed by the tool. Yes, it is really good. Yeah. So let's have a short coffee break until 12:15 Central European Summertime. So let's have 10 minutes and then we are back at 12:15 for another very interesting subject.
Michael, one small thing, if
Yeah.
you don't mind. I'm going to put in the chat, for those that have the coffee in front of the computer, the link of a survey that yesterday I was showing in advance, but it was not finished. So during these 2 days, if they can fill it during coffee or any other moment, I will put it in the chat now. Okay, thank you.
Very good. So talk to you in 10 minutes.
Perfect, thank you.
So hello, welcome back. So in the course, if you remember, in the announcement, we promised you access to data from spacecraft, from real spacecraft. But even better, we promised you also that you can take your own data with telescopes directly. And so today we have here our colleague Fraser Lewis from the Faulkes telescope project and also the National Schools Observatory. And he will show you that it is possible to take your own pictures even if you don't have your own telescope. And how to do this, he will explain us now.
In 1 hour. Okay. You hear me okay?
Yes, a little bit low.
A little bit low. Okay, I can probably change my microphone settings a tiny bit. So that maybe is a bit better. And I'll try and... Okay, good. Okay, and I shall share my screen. So... so you see my slides?
Yes. Perfect.
Great. Good. Okay. So my computer's now telling me to turn off my background. I probably better do that, otherwise things will probably go horribly wrong. So I apologize. I'm going to disappear from space and reappear in my own living room. There you go. It's not quite as interesting. So yeah, as Michael said, I'm from the Faulkes Telescope Project and the National Schools Observatory. And I also work for the Open University. So I'll explain a little bit about what they are. And I'll explain a little bit about robotic telescopes as well. So I'm based in Cardiff in Wales, the very recently declared Republic of Wales. I don't know if you knew that, but it appeared on the news yesterday, so we were all a bit surprised. It's a dangerous place, Wales. As you can see, we have Daleks on the main high street. It's where Doctor Who's filmed, if you've ever followed Doctor Who or Torchwood. They're both filmed in and around Cardiff. So I've got a few little interactive questions for you just to check that you didn't fall asleep during the beautiful music, just to check you didn't fall asleep after your coffee. So Michael or Bea or whoever else is from the team, maybe you can just keep an eye on the chat. Does anybody have any ideas what I mean or what we mean when we say a robotic telescope? What does the word robotic mean there? I can kind of see some chat things flashing up on the screen. They don't stay long, but if I see them.
So two people say yes.
Oh, okay, that doesn't quite answer the question. So it's remotely controlled. Okay, yeah. So there's an element of automatic. There's an element of remoteness about them. Yeah, that's probably true. Okay. Right. So here's what I've got. I've got one that isn't being controlled directly by a person. So yeah, as Anna says, they're controlled from any place. So often we control these robotic telescopes that are on, other parts of the world. I'm in Cardiff. It's not always particularly beautiful, particularly sunny. It is today, funnily enough, but our weather is not great. So what we can try and do is take advantage of the places in the world where the weather is a lot nicer, sadly, without being able to go to them. So a robotic telescope has often a degree of independence. So what I mean by that is that the robotic telescope might be working during the night, wherever night is on the planet, but I don't actually have to be sitting at my screen watching it do my observations. There's some sort of way of scheduling, of requesting observations and seeing them come back. So that takes us on to the third point, that it has a schedule, it has a plan of observations, and maybe it knows something about the local weather. It knows what to do if the weather is bad, and it knows when it's dark. Those are reasonably important things for a telescope that is somewhere else on the planet other than outside my door. Okay, try this question then. It's all about you. The first 5 minutes or so is all about you, and then you can calm down and I'll do the rest of the work from there. Can anyone name any robotic telescopes? And I appreciate there is a very wide range of answers. Liverpool, yeah. Anna, that's cheating. That's cheating. That was in the title. But okay. Aristarchus, I don't know. Hubble. So yeah, Raphael says Hubble. Yeah, that's very true. There's nobody actually sitting on Hubble at Hubble. And yeah, there's the micro observatory, as Rosa points out as well. Rosa's very good. She's learning very, very quickly. Yeah, with any luck, Michael's observatory in ESAC in Madrid, near Madrid as well. Okay, good. SLU, yeah, absolutely. Pants up. Right, now we're cooking. Okay, everybody's throwing in answers. Okay, great. That's a really good selection. I've got that list. So somebody mentioned Hubble. I think it's fair to say all spacecraft that are telescopes are in some way robotic and clearly remote. Of course, they're not worried about the weather in space, but they are worried about other things such as communicating back with the Earth. So things like Hubble, Chandra, XMM-NEWTON that we heard about earlier, Gaia that we heard about earlier, Spitzer, which was in the infrared. There are a couple of telescopes, or there are many, many telescopes, in fact, but there are a couple of telescopes up at the top of Mount Tady called Pirate and Coast, and you may hear a little bit more about those from Naira later today. And yes, somebody mentioned the Liverpool telescope as well, which is in La Palma, so also in the Canary Islands. Okay, I think if I remember my slides correctly, I think this is the final question for you. So, why would we want to use robotic telescopes? What do you think are the advantages of using robotic telescopes? Dave, yeah, I suspect you're in the UK, so yeah, get away from the clouds. That's probably a fair comment. Yeah. Anything else? Anyone else? There was something about they all flash through too quickly. Systematic control of the observation. Yeah, there's an element of control when we give our lives to computers. There's an element of control that we lose, but maybe we gain something in terms of computers being a little bit cleverer. So yes, and I think Rosa put something in there as well about schools and schools being able to use them and taking advantage of time zones. That's a very, very good point. I've got that list there, most of which I think are good. You'll probably see the one that isn't so good towards the bottom of the list. But yeah, I mean, with all these telescopes, they have a limited resource. There is a limited amount of time available. And many telescopes, certainly things like Hubble, there are probably 5, 8, 10 times as many requests to use Hubble as Hubble has time to do. So the most efficient way of moving your telescope across the sky is very, very useful. If you take humans out of the equation, then you take humans out of the fact that I'm making a cup of coffee when it was my turn to make a decision, or I've gone to answer the door, or what are all the things that humans do that stop them functioning 24 hours a day, 7 days a week. It also allows us to respond to what we call targets of opportunity. Objects change in the night sky. We know that galaxies will be the same. We know our sun has lived about 5 billion years. We think it will live another 5 billion years or so. But there are objects in our night sky that change from one day to the next, from 1 minute to the next. And having robotic telescopes is a really useful way of being able to sort of program ahead of time what you will do when these opportunities arise. So you don't have to think too much. I don't receive an email that it's inconvenient for me to respond to, but the telescopes simply take over at that point. It provides access to students and teachers, such as yourselves. Potentially, and I think somebody mentioned SLU as an example of this, potentially it's a way of selling time on telescopes to amateur astronomers. And sadly, it stops us flying off to sunny places. You can argue that's a good thing, maybe in terms of cost and in terms of carbon footprint and flying around the planet. These are all good things. And clearly the last 8-9 months has shown us that being able to use online facilities is an advantage over having to travel to places when we're not actually allowed to do that. Good, okay. So that's a reasonable sort of introduction there to why robotic telescopes would be useful. There are, as with all telescopes, the size of the aperture, the size of the mirror at the back of the telescope starts to determine how good the science is that you can do. Now, it's not a one-to-one relationship. There is some very, very good science done on quite small objects. If you actually look at the collecting mirror, for example, of Hubble, it's not that big. If you put Hubble as a spacecraft, as a telescope on Earth, it would not be in the top 100 largest telescopes in the world. But its position in space clearly gives it an advantage in a different way. So in a sense, the bigger the telescope, the better the sciences you can do, or certainly maybe more flexible the sciences that you can do. There are 3 telescopes in the world that are 2-meter aperture, and I'm talking here almost entirely about optical. So that tiny little bit of visible light that we know of from red through to blue. We don't really deal with anything else in the electromagnetic spectrum in our projects, sadly. One of those telescopes is the Liverpool telescope, which is the one marked with the yellow dot. As you probably spotted, it's not in Liverpool. The weather in Liverpool is not particularly good for observing the night sky, not every night of the year for sure. There are also 2 red dots on this map that represent the Faulkes telescopes. So these are the other 2 telescopes I have access to, or you in fact have access to as well. And one of those is over here in Hawaii at about 3,000 meters above sea level. And the other one is down here in Australia in Siding Spring at about 1,000 meters above sea level. So we have 3 telescopes that we have access to. There is a range of more telescopes than that, in fact, that we have access to as well. This is an image of the Faulkes Telescope North. This is the one in Hawaii, and it's this little image, it's this little pair of buildings here at the bottom of the image. That's the 2-meter telescope. The rest of this facility is owned by the US military, so we don't talk too much about that. But this is our telescope here, right up at the top of a dormant volcano in Hawaii. You see a difference here with Faulkes Telescope South, which is in Australia. And again, this is our image, our telescope in the background here. This is the Anglo-Australian Observatory telescope. And this is, as you see, a slightly different environment, but again, a research quality site. This is where high quality research grade telescopes are based. Liverpool telescope, as I mentioned before, it's not in Liverpool. The city centre wouldn't be a great place for a telescope for many reasons. There is a lot of vibration, there is a lot of light pollution, there is a lot of chemical pollution. Putting telescopes in places like La Palma in the Canary Islands is a huge advantage for astronomers, as you might imagine. On top of the 2-meter telescopes, the Faulkes Telescope project that I work for has access via a group called the Las Cumbres Observatory, which are based over in California, to the Las Cumbres network. And we have about 1,000 hours of telescope time per year that we give away free of charge to educators, teachers, students throughout the world. Our project was started to work with UK and Ireland schools. We've worked with groups such as Rosa's group in Nucleo for more years than I remember, probably 7 or 8 years, I think it is by now. And through the European projects that we've worked with Rosa and others, we've provided telescope time to other interested groups within Europe. And we don't stop at that point. We're quite happy to try and take over the world, as you might imagine. So Las Cumbres Observatory have the 2-meter telescopes I mentioned before. But in addition to that, they've built a series of 1-meter telescopes. So there are 2 1-meter telescopes here in Australia. There are 3 1-meter telescopes here in South Africa and a further 3 in Chile. There's also one in the USA. There is one in Israel. And I think there are plans for another 4. There are another 2 that are going into Tenerife and another 2 that will go into Tibet or China in the next few years or so. So what Las Cumbres Observatory are doing here is they're being clever about where they put their telescopes. One thing that they have immediately by putting telescopes across the 3 landmasses in the southern hemisphere is that there is always at least one of those telescope sites that is dark. So we mentioned about these objects that change very, very rapidly, what we call transient objects. Right now it is dark in Australia, just about. Actually, it's Australian summer, so maybe not quite, but it's going to be what, about 9 p.m. in Australia, something like that. So yeah, it's kind of getting dark there if it's not already dark. In South Africa, clearly that's roughly the same time zone as Europe, so that's midday or so. And Chile is about 5 hours behind us, so it's just about getting light there. So at any given point, there are telescopes in the network that are in darkness. And of course, by putting telescopes in different places, you get around the problem that, you know, even good places have bad weather from time to time. So we have all these different resources dotted around the world that are used by the network. Here's a range of images of the 1 meter enclosures. So here are the 2 1 meter telescopes in Australia next to Faulkes Telescope South. I can try to see if I can try and remember these. I always get this wrong. This one top right is McDonald Observatory in Texas. This one top left, the 3 observatories in Chile and Cerro Tololo. And this one bottom right are the 3 observatories, or the 3 telescopes in Sutherland Observatory in South Africa. If you didn't think however many telescopes that was, 13 telescopes was enough, we also have a range of 0.4 meter telescopes. So 0.4 meter is, you know, it's about that big. Okay, the actual back of the telescope is about that long. You probably can't quite see my hands, but you get the idea. These telescopes are similar to the telescopes that amateur astronomers would use. However, these are still at research grade sites, and these have research grade cameras on the back. So we can do some nice science and pictures with these as well. So there's a range of these 0.4 meter telescopes around the world as well. With those telescopes, we can start to take some pretty pictures. This is a black and white image, as you can see, of an object. We could do the quiz. We probably don't have time to quite do the quiz right now, but I think many of you will recognize that image as M16, or also known as the Eagle Nebula or the Pillars of Creation. It's a star-forming region, and you can see these amazing pillars of clouds of gas. Okay, on top of that, that is our color image. So you've already had a play around with Salsa J. I don't think you do color imaging in this particular course, but we provide ideas of how to do color imaging, and you can create from individual black and white images taken with different filters. You can provide, you can create images such as this image here. So this is our version of the Pillars of Creation in color. That is Hubble Space Telescope's version of the Pillars of Creation in color. So you can see our image is not bad. It's not too far away from what Hubble is creating, and clearly we are providing telescope time for you to go off and take images like this yourselves. Moving on, this is another nice, pretty picture image. So we do enjoy taking pretty pictures. We think that pretty pictures are often what opens the door into astronomy for a lot of people. So you see an image, but there's some questions in there. What do the colors represent? What do the shapes represent? You know, what's going on in this image? So we can actually pull in a bit of science. Again, many of you may recognize this image or this object. This is M1, or the Crab Nebula. So this is the result of an explosion of a star. So a star went and became a supernova around about 1,000 years ago. It was seen by Chinese astronomers in their daytime sky because it was that bright. And so we can date this object back to nearly 1,000 years ago, and we can measure something about the size of these strands of material that are coming out from the central object. So the central object in this instance is a neutron star, which is an object that is very extreme, even by astronomical terms. Neutron star is an object that weighs about the same as the sun, but it has a size about the size of a city. So it's about 10 or 20 kilometers across, but it weighs the same as our sun. And these objects spin very, very rapidly, maybe 30 or even 100 or even more times per second. And they have crazy, crazy, crazy magnetic fields attached to them as well. So neutron stars are very, very interesting to scientists for lots of different reasons. And it's certainly something I've been studying for many years now. And there is one right in the center of this beautiful picture. We can zoom out a little bit more into the universe and take images like this. This is almost a zoomed in image of the center of a galaxy called M51, the Whirlpool Nebula. And we think this looks a little bit like the way our Milky Way looks. And we saw some great images before of Gaia, or from Gaia, of the distribution of stars in our own galaxy, but it's very hard to understand exactly what our galaxy looks like because we're actually in it. But we think it looks a little bit like this. So if you imagine the sun would be maybe down here in one of these spiral arms. So this is a color image. It's a red, green, and blue image. And then we've added pink on top of that again. It's actually a 4-color image. And the pink in this image represents collections of hydrogen. It's what's called hydrogen alpha. So this is hydrogen that is being excited in some way or other by material around it, by photons. And these hydrogen blobs, these pink blobs, represent areas where new stars are forming in this galaxy. So it tells us something about spiral galaxies, these images. From that, we can go even further away in our universe, and we start to look at objects such as the one which is towards the right-hand side of this image, which is Centaurus A. This is a very well-known galaxy to astronomers. It's a very bright object, not just in the optical, but it's a very active object. It's very well known to X-ray astronomers, and it's very well known to radio astronomers. So there's some really interesting science that goes on. This is a massive galaxy. I think it's about 1,000 times the mass of our galaxy, and I think the black hole in the center of this galaxy is also about 1,000 times more massive than the one in the center of our galaxy. So this is a really well-known object called Centaurus A, and a few years ago, 4 years ago now, a supernova exploded. So another one of these massive stars exploded in this galaxy, and you can just about see it. So again, I don't know how well you can see this on your screens, but there is a brightish star there just where my cursor is. And then up at a diagonal, so up at about 10 or 11 o'clock on a clock face to that, there is a little fainter star. That's the star we're interested in. That's the star that scientists got excited about. And in this case, this image was taken by a very regular user of Faulkes telescope, a friend of mine and certainly a friend of Rosa's as well. So this is Álvaro Faulkes, who is a Portuguese astronomer. There you go, and a colleague of Anna's as well. And we were very, very pleased because this is an example of not just me coming along to a conference and showing you the pictures I took, but this is me showing you pictures that the teachers took. And that is a much, much better advertisement of what we can do than me sitting here and telling you all the great things that I can do with my telescope. It's what you can do with my telescope that is more important. It's not just my telescope, but you know what I mean. So leading on from that, this is the one that Rosa gets angry about, and I keep it in every presentation just because I know it makes Rosa angry. We probably know this. Those of you that teach physics, teach astronomy, those of you that are interested in astronomy, depending on where you are in the world, it's not always the case that astronomy is taught in mainstream. It's not always taught in great detail to lots of students. It's often taught as part of physics, or it becomes a little project that they can do, or a little additional piece of physics that they do. So what we try and do is think about all the different aspects of the curriculum. And again, we deal with the curriculum in our country, and that's a confused picture anyway, before we start thinking about the curriculum in Portugal or in Greece or in Croatia or wherever else in the world. But we know that we teach maths, and we know that we teach IT or computer science, or we teach people how to find their way around Excel. We talk about chemistry, we can talk about biology. We can actually, if we think about our solar system, we can start to think about geology and geography as well. So there's lots of different ways of trying to put astronomy into the curriculum, or put astronomy into our students' minds. And one really good thing that we like to do, and we're very keen to do, is to get schools and teachers to talk to each other and to talk, if we can do that internationally, then that would be even better. I sort of hinted at it in the previous slide, this idea of STEM, that education these days follows this idea of STEM, science, technology, engineering, and mathematics. And we've now added A for arts. I think we've added R for writing, which worries me a little bit, but never mind, we can worry about that at a different time. But we've added A for arts. And this is an example of where we took some really nice color images of objects and we gave them to students. And I don't think these students were too worried about the science. I don't think they were really bothered about neutron stars and planetary nebulae and star forming regions, but they knew their way around Photoshop. So they took these original images and they put all the crazy filters that you can put on using Photoshop. And obviously there are other different packages you can use as well to do that. And they created these objects. So we ended up with sort of an arts project coming out of it. So you can say there's very little science in these objects. There's nothing you can do scientifically with these objects now with the way these images show on the screen. But the kids had fun. They enjoyed it. They learned maybe a tiny bit about space and about how to play around with images. They found their way around Photoshop. So, you know, that's a winning situation as well. So, tell you a little bit about the Faulkes telescope project itself. Let me start with a quiz. So again, just to check you are all awake, can anyone see? Now, some of you may have seen this presentation before. You may have seen this in Jihu. You may have seen this in GTT, the one I did in the summer, the one we did in the summer in the Canary Islands. Can anyone see an asteroid in this particular image? Bearing in mind, it probably is a trick question. Okay, it's gone quiet. That suggests to me that maybe you can't see an asteroid. You're looking at a set of stars. Each of these white circles represents, white dots represents a star. It's the one near the star. Thanks, Dave. Yeah, great. It's the one in the triangle. Yeah, all of that. There is an argument that says, or there is often a thought that says the object that you've pointed the telescope at will probably be in the middle because that's where you pointed the telescope at. That may or may not be true in this case. What we do find as astronomers is it's often easier to look at black stars on a white background. So all I've done here is flip the image in terms of color just to see if that helps me. Sometimes when you're looking at lots of images, it's easier to do it this way. I'm still hearing nothing, so I don't think anyone's seen the asteroid. How about now? It's not working, is it? Okay, you probably saw the little red oval that gave it away, but can you see an object moving in that field? Tell me you can. I can see it on my screen. Great, good. Yep, yes, it's fantastic. Loads of yeses, great. If you can't, it's probably time to pop to your opticians and just check with them that your eyesight's okay. The object that we're looking for is the one that is in that red oval. So it's one, it looks like a star. It looks like all the other objects in the field, but it's moving. So you have a fixed background of stars and you have one object that is moving across the field of view, and that is your asteroid. So that's a lump of rock that's moving through our solar system, and that's discovered or just observed in this case by just taking a handful of images, maybe a couple of minutes apart. Okay, what you probably didn't see is there's another one down here. And that's often the case with these objects. When you take an image of something, you find something else in the image. So maybe you can just about make out a second one down towards the right-hand side of the image here. So yeah, sometimes with science, you actually get more than you hoped for rather than less, which is always good to know. In this case, this is an asteroid. So again, this is quite a long exposure, maybe a couple of 100 seconds. And when you take a long exposure, if you imagine standing by a motorway at night and taking photos of the cars, but leaving the camera open for 100 seconds, you see all those red tail lights going past. So that's what you see here. This is an asteroid that is going across the screen, either from left to right or from right to left. It's hard to tell from this one single image, but we believe it to be making about traveling about 1,000 miles through space. And we actually know something about the amount of time that it took to take this image, so we can actually start to do a little bit of maths, a bit of trigonometry. And we also know that this thing is spinning. The reason we know it's spinning is because here on the left it's quite bright, and here it's quite faint, and here it's a bit brighter again. And that's the signature, if you like, of a rotating or a spinning object. So this is an asteroid that's tumbling through space. and we took multiple images of this object. And that's what we see here. Now I'm going to start to show you in the remaining half of this talk some of these light curves. You'll see a lot of these today between myself and Naira, so I'll sort of set it up gently for you now. Generally, when you see what we call a light curve on the x-axis, so on the horizontal axis here, there is something to do with time. So time might be in hours, might be in seconds, it might be in minutes, it might be in years. It depends on what the object is. So this is something to do with time. And this on the y-axis, the vertical axis, is something to do with brightness, how bright the object appears to us. And generally, bright objects are at the top and faint objects are at the bottom. So you can see here that this object is changing in brightness from the point at which we started taking images to here, and then it fades, and then it gets brighter again, and then it fades. This hopefully looks a little bit like a sine wave to you, regular sine wave. To an astronomer, this is a sine wave. To a physicist or a mathematician, they look and they go, "Ooh, that's really messy. There's very, very big error bars in there, very big uncertainties." But to an astronomer, that is a perfect sine wave because we work with a different range of parameters, I guess. So whenever we see a sine wave, that's an indication of either an object that is spinning or a pair of objects that are orbiting a common center of mass. In this case, it's a spinning object. And by taking lots of observations of it, we were able to determine that this object was spinning on its axis every 42 and a bit seconds. So this is an object that weighs about 5,000 tons. So it weighs, what does a bus weigh? 30, 40 tons? So it weighs about the same as 100 buses. It weighs, it measures about the size, I guess, of a tennis court, and it spins on its axis every 42 seconds. So these were observations taken by a British amateur astronomer that we work with, and it was part of a group of observations. We have this data that we can share with you, and that's something I think it's important to mention at this point while I remember it. Our project is not just about giving you telescope time and allowing you to look at objects. It's also about finding interesting data sets that are out there that we've already got and sharing them with you and allowing you to explore those data sets. So those of you that don't want to use the telescope but want to play around with data, we have that covered as well. Okay, we have access. This is a question I always get asked, and I will try and answer it before I get asked it this time. Both our 2 meter and 1 meter telescopes have spectrographs on them. However, those spectrographs are designed by scientists for scientists. So using them and working out what the data tells you is not easy. It's on my to-do list, but my to-do list is about this long and it's about there. So at some point, I promise, and this is being recorded and there are 50 or 60 of you there, I promise to work on spectra and try and do something, because I think spectra chemistry is a really useful thing we can do with astronomy. It's just not that easy to do. So we will try and do some stuff with this. If any of you have a real desire to do spectroscopy and have maybe some experience, then get in touch and we can certainly work with you. It's definitely something that I need to spend time learning how to do. And I also, there was another point I was going to make. I can't remember what it was. But yeah, spectra are very, very interesting, very useful for scientists, and we need to find ways of trying to do that. So we will work on that. They are available, but we can't really help you much because we don't know much about how they work ourselves. So let me go back again to light curves. Again, we'll keep this subject going for a little while. This is a few years ago now. This is 8 years ago. We had a grant from the Comenius project, and it allowed a set of schools from around Europe to work together, and they met up on Skype. And again, 8 years ago, that wasn't as easy as it is right now with WebEx and Zoom and so on. And they collected data. They took images of an asteroid and they used SALSA J to produce a light curve, and then they analyzed the light curve. Now you're getting good at this because you've already had an opportunity to do this. So we won't play Spot the Asteroid, but I hope you can see that it's around about, where's my cursor? It's around about there. Okay, it's that bright object that is moving through the field. But here's a weird thing. We got another asteroid for free. I can't promise you this. I can't promise that this happens, but here are two examples where we go to find an asteroid and we find a second one free of charge, which is really strange. Again, this is a light curve. This now represents time in hours, so from 10 a.m. to 3 p.m. And again, brightness from bright to faint. And again, every astronomer in the world will tell you that that's a perfect sine wave. What's interesting, this is again the idea of collaborative nature of science. Each of the schools took their own data. And if you imagine that each of these schools took their own data and then just held their own data to themselves and didn't share it with anyone, not many of them would have found anything. The Polish school wouldn't have any conclusions from this bit of data. The UK school probably has something here because it sees a change. The Portuguese school sees a linear fade. The French school sees this. It's only the idea of those schools coming together and actually sharing their data that allows us to see the big picture. I know that sounds a bit philosophical and a bit sort of, metaphysical in that sense, but it's a very good lesson. It's something that scientists will always tell you, that the collaborative nature of science clearly makes it fun, but also makes it useful for all. So I think that's a nice lesson to learn there. Sticking on the asteroid theme, we had a work experience student came to work with us, I think 2011. So this is a very old slide again. And this was a 17 or an 18-year-old student in Cardiff who came to work with us when we were working together in the university. And we gave her access to the telescope over a 6-week period. And she went and discovered 22 asteroids. So these things are out there. They are able to be discovered if you have time and a bit of an idea of what you're trying to achieve, and a bit of luck and some good guidance along the way. So it is certainly possible to do that, and these asteroids are useful. It is not just it's one of the parts of science, one of the parts of astronomy that does affect us. Finding out where asteroids are in our solar system is actually quite important. You'll know this from the likes of Chelyabinsk a few years ago, and if you've studied anything about Tunguska 100 years or so ago, or something about the death of the dinosaur 60 something million years or so ago, these we think are all associated with asteroids. So it is important to know where these objects are in our sky. What we do about them once we found them is a different question, of course, but we'll revisit that this afternoon. I'll be talking a little bit more about some of these other projects this afternoon, and we'll have a look at that again. So again, apologies, another light curve, but it's a different type of object. This is the Uranus system. So this really big blob here is Uranus. These two white blobs here represent a couple of the moons that orbit Uranus. So again, going back a few years now, we took some data where two of the moons, one of them was going to eclipse, one of them was going to pass in front of the other one. And these moons passing in front of the other meant that the amount of light coming from the pair of moons dropped and then restored. So this is a little bit like, we've heard it mentioned a few times this week, exoplanets. The idea of an exoplanet passing in front of the face of its parent star. We talked also about Venus and Mercury transiting our sun. It's the same idea. We lose a tiny percentage of light, and that can tell us something. And in this case, it told us something about the system, because the timing of these events wasn't quite when the astronomers predicted. It was out by a few minutes, and that meant that they had to go away and recalculate their sums, their theories. And for an astronomical or an observational astronomer, when you can send the theorists back to work things out again, that's a really, really good day. We worked a few years ago with some local students again, so based in Cardiff. These were 17-year-old students, and we provided them with instructions on where existing known exoplanets were and how bright they were and how visible they were. And these guys went off. They found one that was going to be visible, one of these transits where the planet passes in front of the star in a few days' time. They programmed the telescope, they collected the data, they analyzed the data, and using Excel, they produced a graph. And again, you can probably see here that this is a fairly obvious blip. So here's what the scientists, or here's what the artists think an exoplanet transit looks like. It looks very, very neat and tidy, and real data looks a bit more like that. And that's another useful lesson for astronomers to have. There are other things we can do with the telescope. Again, we're using all the time, we're using a principle called photometry. So we're using free software to measure the brightness of stars and to create the graphs from them. In this case, this is a star called RR Lyrae. Sorry, I beg pardon. This is a star called LT Carina, which is an RR Lyrae type star. If you've come across the idea of Cepheid variable stars, then this is a similar type of beast to one of those. And what this object says, what this graph says, is that this object is very blue. So we've changed the axes a little bit here, and we're now talking about the color of the star from blue on the left to red on the right. But we're still talking about the brightness from bright at the top to faint at the bottom. And what we see here, lots and lots of observations of one star at different points, at different times. And we see that it's very blue when it's bright, and it's very red when it's faint. And that starts to tell us about Wien's law. I know you've heard the term black body again earlier today. So black body emitters, objects that behave as black bodies, follow what we call Wien's law. The hotter they are, the brighter they are, and the hotter they are, the bluer they are. So this star is blue when it's hot and red when it's cool. And that tells us something about what's going on with this star. In the bottom observation, we see again another one of these sine waves. This is a very, very neat sine wave. It has a period of about, I can't remember how many it was, a few hours or so. And this is an eclipsing binary system. So this is a pair of stars that are orbiting a common center of mass and eclipsing each other. So one passes in front of the other. And that's what we see with this light curve here. So there's lots of really nice science we can do with this. Like I say, all these data sets exist, and we're always keen to think about how we can collect more data on these objects. One of the really great things, one of the really good things we can do is, and this doesn't happen very often, I'll show you a few examples today, is that we have schools that work on collecting data with us, and for some reason scientists are already interested in that data. So maybe a scientist comes to us and says, can you image this object? And we get the schools to do that for us, and we can then put the schools in the acknowledgements of papers. So these are monthly notices of the Royal Astronomical Society, Astronomy and Astrophysics. These are peer-reviewed journals that astronomers use for passing their information around. And here we're actually mentioning schools by name in the acknowledgements. We also have a set of teachers and students that we're working with in Germany, and one of them won first place in his regional competition for discovering an asteroid. That's him there with the certificate, and you can see the asteroid in the object here. It's the one in the images here. It's the one object that changes from one image to the other. So again, the idea of using asteroids to get these really instant pieces of science. Again, I will mention this one a little bit more in depth this afternoon. I think Rosa has already mentioned the project generally, but Rosa and I have been working for a few years now on a project called Black Holes in My School, which we need to do more work on. We need to make it a little bit easier. We need to find some more data, and we need to just decide quite how we present it. But this is a project that I know Rosa has presented to many schools already. And again, we see the sine wave, and that's a signature here of a binary system. But in this case, it's a very, very strange binary system. It's not a pair of stars as we imagine a pair of stars orbiting a common center of mass. Here, one of those stars is a black hole. Okay, it's a small black hole in our galaxy that is taking matter off the other star. So that's what we see with the artist's impression at the top left. Again, I'll talk a little bit more about the process behind that this afternoon, but just to sort of mention this idea of black holes in my school. If you're interested, let me put that a different way. If your kids aren't interested in black holes, yeah, there's something strange going on, because generally they're pretty switched on at that point. From that project, we worked a couple of years ago with a school teacher, very, very good school teacher, and a couple of his pupils in Lausanne in Switzerland. And they got a little bit tired of waiting for me to respond to their emails. And they were saying, we want to find a target, we want to image a target, can you tell us a target? And 27 other things to do. So I didn't respond to them as quickly as I could. And they went off into the literature and they found an object, and they started taking images of this particular object without me really helping them as much as I should have. It just happened that that object was changing in brightness very dramatically, that other astronomers were already looking at this object in lots of different wavelengths, such as with XMM, such as with Chandra, the two X-rays, the really famous X-ray observatories. And these guys, Philip Cobel, who's the teacher, Danae Perez, who's the student, and Rosa, and in fact myself, I'm in there as well. We all were listed as authors on this paper. So this paper came out a few years ago in Astrophysical Journal. So we're really, really pleased with that. I think I have 13 minutes or so left, and then the big bell goes and I've got to stop. So we'll revisit this
Yes, correct.
idea of Gaia again. Say again, Michal?
No, yes, you're right. You're right.
Okay. I just had a horrible thought I was supposed to finish at 12.
No, you have until 1:15.
Yeah, that's fine. That's fine. I realize that. Okay, good. So you've already heard about Gaia this morning. You've probably heard about it previously this week, but I know it was mentioned this morning. And Gaia's main mission, its main science goal, is to map the Milky Way, to understand something about the structure of our Milky Way, and to understand something about where stars are and how they travel about within our Milky Way. But Gaia does more than that. Gaia has a camera that scans the night sky in our galaxy every few days. And as a result, it builds up a really good picture, very, very accurate picture of where stars and objects are in our galaxy. However, it also spots when objects have changed. So it looks at a particular part of the night sky and it says, you know what? I looked at this object 2 days ago and it's changed. It's moved or it's changed in brightness. And it produces what's called a set of alerts. It's called an alerts index. So it produces that. You can actually access this. The web link at the bottom is there. This is publicly available. And it lists objects, about 5 or 10 per day, that have changed. And it gives them maybe an idea of a classification of what that object might be. And objects change in brightness in our galaxy for lots and lots of different reasons. In fact, in other galaxies as well. So there is an alerts index, and we've kind of tapped into that. So again, you've already heard quite a bit about Gaia today, and the idea that my understanding is this phrase is 1 billion stars with a 1 billion pixel camera for 1 billion euros. There are some really, really nice education resources. Again, clearly the Gaia sites themselves have that, but the UK people that have been involved in Gaia, in the data processing and in making with the camera, also have their own website, which again, freely available without password, called gaia.ac.uk. And there are education resources and some really nice sort of captions and cartoons on there that you may want to have a look at. As part of the work that we did with the Gaia scientists, we created a series of worksheets on the background material. So something about what Gaia does and some sort of questions that you can give to your students. So there are teacher versions of these activities and student versions. Sadly, it's all in English, I'm afraid, but hopefully that isn't too much of a problem for you. And again, the web links for these are at the bottom of the page. As a result of that, and you can see this is almost hot off the press. This is only a few weeks ago we discovered this. Gaia discovered a symbiotic star. I don't have time to explain what that is right now. It's a very strange set of stars, pair of stars again, where one is kind of in the act of killing the other one. Again, we had students that were looking at this object. So there's me in here, at the top here, and Megan and Jorgen are a teacher and a student that were based at a school in the UK. So we're going to try and write a news article about this and publicize this a little bit more. But again, it's an example of where a legitimate astronomical paper comes out that has teachers and students involvement credited. The one thing I would say, the one disappointment with all these things, this was discovered in 2018. The paper came out in 2020. So this isn't an instant response. To contact the student now and say, do you remember 2 years ago you did this, blah, blah, blah. They remember, but it doesn't have quite that same, oh my God, look what you discovered last week, look what you discovered last month. It's not quite at that level of excitement, but it's still pretty cool, pretty neat. On top of that, our involvement with Gaia means that we created worksheets on the cameras themselves. We talked about how the launch was made. We talk about where the orbit is of Gaia, because it's in a particular orbit within our solar system. We talk about the scientific instruments that Gaia has, and we talk about how it powers, how it uses the solar panels to power itself, how much data it produces, and so on. Gaia, sadly, as with all space missions, will stop one day. It's already survived longer than we hoped it would. And sadly, in a year or 2 or 4 or 5, it will stop working. It will run out of fuel, or will run out of funding to keep it under control, as it were. But that's not the end of the story. Even though we look at Gaia alerts and we use these as an understanding of what objects are out there that we might want to follow up. So we're not just taking pretty pictures, but we're taking science data. There is an observatory currently being built in Chile, in Cerro Pachón, and this is going to be the largest survey telescope in the world. It is going to be a 10-year survey starting in 2 years' time. I wouldn't recommend downloading it, especially if you are at home, because we believe it's going to produce about 1 petabyte of data per year, which is 1,000 terabytes or 1 million gigabytes. So the data that comes from the telescope, which again is doing a survey of the night sky, in itself is going to be too big. But this observatory is going to produce an alert stream, and it's going to produce an alert stream that's updated daily. And it says, okay, since yesterday, we've discovered however many objects. I think they think it's in the order of thousands of new objects per day. So it becomes a very difficult task to know which one to go after. But if it's finding 1,000 new objects per day, there are going to be 4 or 5 or 10 or 20 that are very, very interesting. And what you need is telescopes such as the Faulkes telescope, such as the Liverpool telescope, to follow these up, not just to put them down and go, okay, well, yeah, we found some stuff, we don't know what it is. Because if you don't look at that data, you get the same amount of new objects tomorrow. You get the same amount of new objects on Saturday. So somewhere along the line, we're going to have to sort of pick and choose interesting objects. Right, let me come on, because this is like the really important part. I've already mentioned that you control these telescopes. I mentioned that you can control them, hopefully over the internet. It's all free of charge. There are different modes of observing. We provide all the instructions on how to program the telescope. From the work you did with Rosa the other day on Stellarium, you have a feel perhaps from the night sky, from the objects that you've seen pretty pictures of, or from something like Gaia alerts, you can have a look at the types of objects you might want to image. You can then take data using the telescopes, download the data, use SalsaJ to look at the data. So we're hopefully, between us, we're providing all the steps along the way to do science projects. What sort of object you want to image? Where is it? How do I observe it? What do I do with the data? You know, and reaching conclusions. So there are different modes of operation. You can request targets. So you can say to the telescope, I would like an image of the Crab Nebula, and I would like it in the next 3 days or the next week. There is a separate way of driving the telescope, which is called real time, where you are given the telescope for 30 minutes at a time, and you drive the telescope around the night sky. We don't provide you with an astronomer to talk you through that process. We provide you with instructions, but ultimately it's up to you to choose your targets for that 30-minute session, which is in either Hawaii or Australia. Now, already as we know, Hawaii is about 10 hours behind us. Australia is about 10 hours ahead of us. So these sessions are tailored for the European school day between 3 p.m. in Europe. The other two telescopes, these telescopes are in darkness. So there is that way of using the telescopes as well. I have 5 minutes left, so I need to speed up a little bit. One of the other projects I mentioned very briefly, and again, Naira may mention these because these are on Teide in Tenerife, are a pair of telescopes owned by the Open University. Now, the Open University is a distance learning provider. It sells educational degrees, or it sells you the ability to do a degree, and large percentage of that degree can be in astronomy. However, the OU also provides what are called MOOCs, or what are they called? Massive open online courses. So they're little tasters in astronomy. Those are free. So if you go to open.ac.uk, you will find lots of information there about these little taster courses in astronomy that you can do. That they don't give you a degree, they don't give you points towards a degree, but they are university-led projects. The other project that I need to tell you about really quickly, and again, I'll revisit this in a little bit more detail this afternoon when we look a little bit more at the resources themselves, is the National Schools Observatory. This is part of the Liverpool Telescope, so part of Liverpool John Moores University. They provide lots of resources on their website about observing. And hopefully, as you've already seen with the Faulkes telescope, and I haven't really made the point specifically, but let me say it right now, both Faulkes telescope and National Schools Observatory, I believe, are more than just telescopes. It's more than just logging on, using the telescope and going away. There are lots and lots and lots of resources. I'll leave you my email address at the end, and if you come to me and say you have nothing on your website about spectra, you have nothing on your website about galaxies, then we can work with you and try and change that and point you in the right direction. So there are lots of resources you can use within both projects. The National Schools Observatory is very, very good at producing these resources. And again, Naira will talk more about the access for Spanish teachers in Spanish schools. But National Schools Observatory, the web links are at the bottom there. I will make sure that all these slides go up onto the GRASP page at some point this afternoon as well. So be aware of Schools Observatory. And again, it's not limited to just UK and Ireland. It's not limited to just schools that are based in Spain. They will look after you wherever you're from in the world. There is an example here of some of the projects that are available via the National Schools Observatory, and they are written with the age group in mind. They are written with the time of the activity, and they will tell you a little bit about what the activity is. And like I say, not all of these are related to actually driving the telescope. Some of them are about images of the moon, some of them are about, you know, the activity in the sun, different types of galaxies. So there's lots of different things that you can jump into and have a look at here. I'll talk again more about this one this afternoon because this is one of my projects, but I've been developing things called inquiry-based, so projects in astronomy that are designed around the inquiry-based model. So we talk about them being teacher-free, if that makes sense. We don't want the teachers, or we don't need the teachers to be driving this activity with the school or with their class. But if you have students that are interested in doing work about the main sequence of stars or understanding more about exoplanets, we can give you the opening page of these activities and they can work them through. It's a little bit like the way you find Wikipedia. You don't follow from page 1 of Wikipedia to page 2 to page 3. You just go where you feel. So it's a little bit more open-ended than a very, you know, structured environment, but it allows them to explore, hopefully, some interesting objects and to play around with some real data and come up with some nice conclusions as well. I'm on about my last slide pretty much. I think this is pretty much where I'm finished. So again, the registration information is here. Mikhail, I can see you there. You're going to make me stop any second now. My email is at the bottom. Like I say, if you're interested in anything that I've spoken about, just email me and we can go through this in a more leisurely fashion, but we'll certainly be speaking to you again this afternoon about some of these projects. That is it from me. I thank you very much for listening. I know it's lunchtime. I don't want to be the guy that stops you having lunch, so I will leave it there, but I'm happy to answer questions.
Yes, I think, Fraser, there's a question that says, can you copy the link for the MOOCs?
I will find it. I will find it, and I'm talking again this afternoon, so I'll put it on the slide when I load the slide up. But yes, the MOOCs for the Open University, yeah, no problem.
And the other question was, what software are you using for the robotic observatories?
The software that Las Cumbres Observatory use and that Liverpool use is purposely written by the people that run the telescopes. So it's not commercially available software in that sense.
Okay. And I think these are all the questions for the moment. So really, many thanks, Fraser. As usual, a very interesting talk. We will continue on the same subject, as Fraser said. So after the lunch break, we will come back and we have another colleague from the Instituto Astrofísica de Canarios who will tell you more about a robotic telescope and how to use them. And then we're going also into a little bit more exercises, I think, no? Or practical stuff. Okay, so then for the moment, many thanks. Have a good lunch, and we're all coming back at 14:30 Central European Summertime. So I apologize for I always say the Central European Summertime because it is where I'm sitting. So you have to translate this into your time zone, please. So you have.
Also,
anyway,
we are going to open the breakout sessions with 10 people in each session. Perhaps the teachers want to speak on each other.
The breakout sessions. Yeah, many thanks, David. And perhaps David, you can also tell us how's it going with the recordings on the YouTube channels.
Yes, we have 2 days ready, Monday and Tuesday, and we are uploading Wednesday. So this afternoon we will have 3 days recorded, and you can see there in YouTube.
So excellent. So if you missed some of the talks because you were busy or you had to give classes or you could not connect, then you can go to the link. It's in GRASP. If you go in GRASP into the material, at the bottom you have a section which is called recordings, and there you have the link to the recorded days, Monday and Tuesday, which are there already. So many thanks. Have a good lunch, and see you in a little bit more than 1 hour.
Michael, I want to remind people that if they can feel the Mentimeter, only 5 people did it during the lunch.
So hello, welcome to the afternoon session. We are back and we are continuing with telescopes. So we have here Naira Rodriguez from the Instituto Astrofísica de Canarias. So as we said in the beginning of the workshop, all those courses, we are very happy to have the Instituto Astrofísica de Canarias in the group because they have excellent educational programs. You have seen already an introduction from Sandra Benitez. I think it was the first or second day. I don't remember now. First day, don't remember now. And now we are continuing with the telescopes. So after the introduction from Fraser Lewis, hello Rosa.
I was just reminding you. You are forgetting the warm up.
No, sorry, you're absolutely right. We have to do it. I forgot the warm-up.
Yeah, you forgot the warm-up.
You can
so
you know, yes.
I know you are on the side of all the lazy people that didn't put their marks on the Google group on the Google Maps. That's why you forgot, huh?
No, I put.
I know. I'm teasing you.
Okay. No, I put my favorite place in the world. Huh? So
did you put something else, Michael? Did you do something else from yesterday to today?
No. Yesterday I put the favorite place, my favorite place of the world. So if you want, you can show it.
You did. Okay.
Yes.
So what is the name?
It's Michel Breitfellner's favorite place.
So, did you discover if we can put this in alphabetic order?
Yeah, this would be nice.
No, I think you have to scroll it. It takes
because I just find one, Michel. So, Michel, you added to the pin that you already had with your name.
No, it's a different pin because it's a different place.
Okay.
So it's a little bit further down because it's later. So it's called Michel Breitfellner's.
Okay. Let me share my screen.
And Rosa, I'm already there now.
Aha! Now you're ready. Okay. Some people are not sleeping. Okay.
Unfortunately, I didn't find a very good picture very fast. So but if you put it up.
Okay, I refreshed Google Earth because it's not, it was not showing me. So let's see. And who else? Let me open the chat. Okay, let me go here. I'm getting used to using this thing. Okay. Okay, I just see okay, there's the link from Beatriz, and there is a hello from Natividade. Hello, Natividade. Welcome back. And Google Earth is not loading, so okay, now it's here. And I'm going to try and find the alter ego of Michel. So I have one here. But Michel Breitfellner's favorite place. Okay. Let's see.
So you will see. So this is my hometown in Austria, where my mother is still living, and
it's not this one. Wait.
No.
Okay. The computer is doing something. Okay. Now it's coming. Michel. Michel. Oh, nice.
And this is in the fields. It's in a valley between two mountain ranges. And if you look at the map, you see this is my, how to say this, my hobby is flying remote-controlled model planes. So this is the association's flying field.
Okay. Oh, that's really nice. So you like that? You have that as a hobby as well?
Sorry?
You have that as a hobby?
Yes. So I fly model planes. Yeah.
Okay, that's very nice. Who else wants to share their favorite place? Okay, while you are writing there, I am going to find one because I didn't add it to mine. Yesterday, I showed you one of my favorite places. Okay. But today I'm going to add another one that I thought that I forgot it. I don't really understand how I could forget it. I don't find my name. I'm pretty sure they allow you to make it in alphabetic order, because that makes life so much easier. Okay, so that was my favorite energizer. That was my favorite place in Portugal. But now I'm going to add it. I click on edit here. And I'm going to ask Google again to help me. I have added Guincho. It's another favorite place in Portugal. But there is one that is my favorite place in the planet. And let me help. Okay, and this is Príncipe Island. And let's hope that Google will help me find it. Okay, it's more or less, yeah, I think this one. So there is an island called Príncipe Island. It's in the west coast of Africa. And I have had the privilege of, okay, let me save it. I have had oh, I don't have to save it, it's there, right? It's there already? Ah, but then the pin is in the wrong place. Let's see. It's in the west coast of Africa, and it's a place that is a worldwide heritage for biodiversity. And the island is amazing. There isn't many people. They are about 7,000 people, half of which are kids. And I visited several places, and you find this often. I'm not sure if we're going to find this forever, but there, you are on the top of a cliff, and you can hear the sounds of nature. I think it was the most overwhelming feeling I've ever had. It's that smell, that sound of earth, alive. It's unique. I don't think that most people in the world know what's the meaning of that. It's a place that is preserved. There is no much constructions, and capitalism didn't invade the island yet. So it's really, really very nice. So I invite you to see and maybe one day travel there. Okay, who else? Let me see. Nobody wrote here. Hello, how I couldn't finish the task from yesterday because I just recovered internet late. Okay, so you are forgiven. Panagiotis, you said you have it. You guys have to give me the name of the place that you have added, otherwise. So if Michelle is saying that it's the last one, let's go from the last one to the top. This is Anastasia, who has added something. Greece, beautiful, beautiful, beautiful. Mornos Lake, okay, you have a good taste. I like that. And I bet you have visited it. Okay. Teresa, you are here, indeed. Let's see. What's Teresa's favorite place? Praia do Guincho. Yeah, I'm with you, Teresa. That's really very nice. And this is a place you have to visit one day when you come visit me. And we can take you to eat pastéis de Belém, another unique pastry in Portugal.
I have a picture of pastéis de Belém. If you
so
slide,
yes, you do. Okay,
you have to slide the pictures.
Okay, let's do it. Sorry, I didn't know that. Okay, so Guincho. This is Cascais, very nice. It's not Cascais, yeah, it is, yeah. Aha, Teresa, the good one, pastéis de Belém. You're my best friend, I love it. Okay, good. This is unique pastry. It's really delicious, crispy and creamy, it's delicious. What else Teresa has here? What is this one, Teresa?
It's Guincho, it's photo took by me. Okay. And this is Cabo da Roca.
Cabo da Roca.
And this one is from the lighthouse in Cascais.
Okay. Very nice. Thank you, Teresa. That was very nice. Then there is one from the Philippines, a place I've never been. Let's see how it looks like. Okay, this is the favorite chicken pesto. Okay, I can go for that one. Although I tend to be vegetarian, but I can go for that one. And Hiltepan Sagada. Okay. This is a very nice sunset, I guess. Seems like a very beautiful place to visit. Very nice. Thank you for this.
You are welcome.
So Daria. Okay. And this is in Pakistan. Aha, near the beach, near the ocean. Okay. Seems like a very nice place to be as well. Okay. And we have Mirwat, Islamabad. Okay. This is also Pakistan, I guess. Oh, there is nothing there. Okay, so is that it, guys? Really? Are you all sleeping or lazy or? Come on, guys. We're supposed to get to know each other. So you now know a lot about Portugal and Cascais. You know a lot about ESAC and Observatory and what Michel's personal taste is. But I want to know more. You guys are the last active group since summer we ever had. So you should be ashamed of yourself. Go there. Put your pins there so we can, get to know more about the planet. This is the good thing about being online. We get to know each other and share with each other. So for tomorrow, it's a new task. Okay, I've done mine already. It's Principe Island. You have to put a pin, but I didn't put a pin there. You have to put a pin in your favorite place in the planet. Okay? So this is the homework for tomorrow. And those who don't fulfill this mission will not receive a certificate. I'm joking.
Yes.
Yes, we can say yes. Good. I love it. Okay, Michel, back to you.
Okay, so many thanks also for the warm-up. And so let's go to the next session. So we started in the morning with robotic telescopes, and we will continue now with robotic telescopes. So I'm really happy to hand over to Naira Rodriguez. She's working at the Instituto de Astrofísica de Canarias, and she's leading there the project of the robotic telescopes.
Thanks a lot, Michel, and hi to everyone, because I haven't been in the course as much as I would like, because I'm also preparing some exams that I have those days. So very happy to be here. Thanks a lot for inviting me and to have the opportunity to present the participants this other project that is aimed mainly for Spanish schools, but is also open to international schools, to schools everywhere that want to collaborate with Spanish schools in scientific projects. As Fraser told us this morning, that an important part of this kind of projects is interaction and collaboration, as the science, the professional science is made of big collaborations. Every year, the collaborations are bigger and bigger, sometimes with more than 1,000 collaborators, scientific collaborators all around the world. So our idea is also to have schools working together to produce science and to be involved in research. Okay, so I will share my slides. Okay, please let me know if you can see it.
We can see it, Naira, perfectly.
Thanks a lot. Okay, so Fraser presented this morning several amazing tools and research projects in the framework of two educational projects, the Las Cumbres Observatory, the Faulkes telescope project, and also the National Schools Observatory. And he also presented us a lot of things, very interesting things that we can do with robotic telescopes. And he also did the good job of presenting why robotic telescopes are so interesting for education. So it's going to be very easy for me to continue from that point. I will comment again some of the things he presented us, but I'm going very quickly to present you Peter, which is the project that I coordinate. But before, I would like to give some context, and for this, I'm going to start introducing a bit the wonderful place in which I live. I haven't had time to put my favorite place or the place where I am in the Google Earth, but I will share some images of the place with you. So I start to introducing you this. Let's see if I can move. Yeah. So these are the Canary Islands. I was born here on these islands in the Atlantic Ocean near Africa. They are the Canary Islands, and their climate and geographical location ensure that the summits of the highest islands enjoy most of the year a clean atmosphere that is stabilized by the ocean. And these natural conditions, together with a pioneering law of sky protection, make them a paradise for astronomy, and one of the 3 best skies in the world for the observation of the universe. And this is why the Canary Islands house 2 of the best observatories in the world, the Teide Observatory on the island of Tenerife and the Roque de los Muchachos Observatory on La Palma, which together they have more than 50 telescopic installations from 27 countries, more or less. So they house some of the most powerful facilities present. And for example, look at those images. So this on the top is Teide Observatory, and the other one, the lower one, is sunset at the Roque de los Muchachos Observatory. And here we have the Gran Telescopio Canarias, which is the largest optical telescope in the world at the moment, and is located at the Roque de los Muchachos Observatory on the island of La Palma. So this is one of the largest ones, but we also have telescopes that observe in the gamma rays, the most energetic part of the spectrum, also in the microwaves, studying the cosmic microwave background, that is the relic radiation from the Big Bang. So we have a large set of telescopes and instruments to observe the universe, the different objects in the universe. So the observatories are run by the IAC, the Instituto de Astrofísica de Canarias, that is a research and technological development center of international relevance, which also has 2 headquarters, one on Tenerife and the other one on La Palma, and has recently set up a technology transfer center called IAC Tech, that you can see here also here. Okay, so about 450 people work at the IAC, including myself and Sandra, and the 2 of us, we both work on the outreach and communication unit or department of the IAC, and specialize on educational projects and public outreach. Okay, so once we know a bit more of the place where I am, not now, but where I work, and the very good observatories that we have here, I will move to a challenge that probably all of us here wants to deal with. That is how to engage students, especially girls, but also boys, how to engage them in STEM, also the arts part related to science and technology. So I'm going a step further. So one of the things is how to engage them, how to have them interested in STEM. And going a bit further, we also want to encourage them to acquire STEM skills and for some of them to develop their future careers in those fields. So a study carried out on more than 2,500 Spanish secondary school students on their scientific vocations shows that they attribute their lack of interest in STEM studies to these 3 points here. The way these subjects are taught in schools. Don't kill me, but this is the first answer. The second one is the complexity of these studies. And the third one is the apparent lack of enough attractive professional opportunities in these careers. Okay, so the challenge is not only to engage the students, but also you to engage the teachers and the families or the society in general. And why? I'm sure that you know very well, and in case you have doubts, Rosa's sessions, probably Rosa commented probably on her sessions about this and repeated this a lot. You, the teachers, have an essential role in the perception of the students about these topics, because it's you who normally introduce them to them for the first time. And on the other hand, the families can also play an influential role in supporting or discouraging the STEM vocations of their children. Okay, so how to face this challenge? So in the IAC, in our department, in the outreach department of the IAC, we try to meet this challenge from different approaches. And one of them is that of educational projects, which include these 3 aspects that we have here. Initiatives that engage students with interesting and motivating real science experiences, which involve you, the teachers, as key players. And for this, we provide resources, as we are going to see in a moment, and tools that could help you to develop a more appealing and stimulating STEM education, as well as training, as we are doing now, and support. And we also want to contribute to changing the social stereotypes of scientists and science itself. And for this, we include, when possible, activities and interaction with ISC researchers, women and men. Okay, so I'm going to present you now Peter, which stands for Educational Project with Robotic Telescopes in Spanish. And Peter is an online lab that dedicates observing time with professional robotic telescopes to activities and research projects aimed at students. Normally, the ages are from 6 to 18. And primary, secondary, and vocational training schools in Spain, over 20 non-formal schools like science clubs, camps, after-school centers, and so on, and about 25 amateur astronomer associations. And as I said, the project is also open to schools from other countries, which are developing collaborations with Spanish schools. And at this point, I don't know if any of the participants were also in the Canary Island course, and I received many requests to participate on Peter and to have collaborations with the Spanish schools. But please give me some more time. I will finish the exams that I'm doing tomorrow, and by Monday I will start to replay all the pending things from the Canary Islands course. Okay, so you can register. I will tell you later how you can register to Peter, and give me some time because it's only me on the project, and I have to check that you are the people working on the schools that you are saying on the application. But for sure, I will give you access to collaborate with Spanish schools. And as Fraser said this morning, you also have the opportunity to use the telescopes that I'm going to present also through the National Schools Observatory or other projects in your countries with the Las Cumbres Observatory. So just this brief comment, I will tell this again later. So let's go again to Peter, and which are the goals of the project. So the first one is to engage students in science through their active participation in real research projects, while also contributing to the diffusion of astronomy and astrophysics. The next one is to stimulate the scientific interest and vocations among students, and to train teachers on astronomy and on inquiry-based learning methods, as we are doing during this week. And as Fraser said this morning, why we use robotic telescopes. So there are other reasons that we were discussing this morning, but for us, there are mainly these three here. So the first one is that they can be used as online labs, and they are a very convenient tool for bringing science to non-professional users, since they can be operated in an autonomous way. You don't have to be at the telescope to use it. With the pandemic situation that we have, or if we want to reduce the carbon footprint, there are many reasons for having robotic telescopes working, not only for education, but for the astronomical community in general. Another reason is that they are accessible to anyone with an internet connection. And nowadays, most of the people around the world have an internet connection, maybe not at home, everyone, but on the schools, they have at least a couple of laptops with internet connection that they can use. And the third one is that they are collective. So each night, the telescope can be used by multiple observers all around the world if we want. So the time is very well used in that manner with the different software that the telescopes have. Okay, so which are the robots? Which are the robotic telescopes that we have that we can use on Peter? So the project started in 2005 following the installation of the 2-meter Liverpool telescope at the Roque de los Muchachos Observatory, which is the largest fully autonomous robotic telescope in the world today, together with the Faulkes telescopes that Fraser presented this morning. The Liverpool telescope is owned and operated by the Astrophysics Research Institute of the Liverpool John Moores University, and they decided to devote 5% of the observing time with this telescope to astronomy education and outreach in the UK. And for that, they created the National Schools Observatory that Fraser presented this morning. So here at the IAC, the IAC also decided they made a major commitment to science education in Spain when the telescope was installed here in one of our observatories. And they decided to set aside another 5% for the same purpose, which this means 25% of the total Spanish time on this telescope. So it's a big amount of time compared to the time we have on that telescope. So the robots that the Spanish schools can use for studying the universe, one of them, the largest one, is this one, the Liverpool telescope. What we can do with it? So we can do imaging, photometry, also spectroscopy, with the limitations Fraser told us this morning, in which we will continue working. And I hope this year or the next one, we can offer you some tools for also doing spectroscopy in an easy way and analyze the spectra. You can obtain images not only in the visible range of the spectrum, but also in the infrared. And as I said, we have a lot of time for the Peter users, and also so we have a lot of time for education through Peter and through the National School Observatory on this telescope. Other telescopes that we have been added lately to the project are those belonging to Las Cumbres Observatory, that also Fraser commented this morning. And at the moment, there are 2 telescopes 40 centimeters operating in the Teide Observatory here in Tenerife, and 16 more in different observatories all around the globe. I think a couple more were added in the last month. And also, as Fraser said, they are installing other telescopes of 1 meter, also here in Tenerife. I think I don't know if before the end of this year, but probably during the beginning of the next year. So as an educational partner of the LCO, Peter users can not only observe with the telescopes located at the Teide Observatory, but also with any other of the 40 centimeter telescopes that of the network that they are they are located also in the southern hemisphere. So you also will have access to observations of the southern hemisphere. And if you are in the southern hemisphere, you can also have access to the sky that we see from the northern hemisphere. Because we have the observatories, they are on the Teide Observatories, as I said, Siding Spring in Australia, Cerro Tololo in Chile, McDonald Observatory in Texas, and Haleakala in Hawaii. Okay. So now, other telescopes that also Fraser commented this morning are those belonging to the Open University. They are called Pirate and Coast, and they have been installed recently. I think it was 3 years ago, 3 years ago, at the Teide Observatory. With them, they are 40, 50 centimeters also in diameter, and with them you can do also imaging and photometry, as well as with the LCO, with Las Cumbres Observatory telescopes. Okay, so these are our robots. These are the telescopes that we can use for studying or obtaining beautiful images of the universe. But what can we do with them? They are fantastic ones, they are great tools, but what can we do with them? So the first thing that we can do is to approach experiencing real science through what we call the learning scenarios, in which we introduce several concepts about one topic on astronomy, and we also provide one or more practical activities which make use of real astronomical images obtained with the Peters telescopes. So the project also includes a student-friendly software that is called PeterSoft, that we are not going to use in this course because it mainly does the same as SalsaJ. So we don't want you to have a lot of software running on your heads. We did it in the Canary Islands, but not this time. But it's also interesting that you know that there is another piece of software that you can use for visualizing and analyzing the astronomical images. And this is also in Spanish and English. And the software allows you measuring sizes, distances, and also brightness, as the SalsaJ software allows. And also doing, brightness, doing aperture photometry. That is one of the things that we are going to see later. Okay, other things that you can do is that you can complement the scientific process requesting new observations with the telescopes of the objects in which you are interested. For this, you can use predefined observations of selected objects like the moon, planets, different types of nebula, galaxies, and so on. Or another option is to develop research projects, either those proposed by us or designed by the schools, by you with your students. So with this approach, students can experience the scientific method, the whole process of the scientific, all the steps of the scientific method, from deciding what to investigate, to prepare and request observations, and finally to analyze the data and draw the conclusions. So we provide orientation in the form of educational materials and technical and scientific advice during the whole process, and also the collaboration with other education institutions and the IAC researchers is very important for the design of some of the projects, and also for being, how do you say this? Like being, I forgot the word. Okay, but to help you during the process of the research project. And also the collaboration among schools is very important, as Fraser also mentioned this morning. Examples of scientific projects that you can do. All the projects that Fraser mentioned are also possible to do them with the telescopes that we have on the Peter project. But I want to mention that you can also do projects in primary school. So this one is one of the examples done by 6th graders. So they are 11, 12 years old students. And the project consisted of studying what are the Messier objects. They are bright nebula and galaxies that are included in what we call the Messier catalog. So they selected the objects they wanted to observe, taking into account when they wanted to observe them and with which telescope. Then they requested the images in 3 different filters to obtain 3 different colors of the object. They analyze the images separately, and then finally combine them to produce a real color image. And I have here one video that I would like to show you, but I will finish the presentation, and then before moving to the Peter website, I will show you this video. Because here you can see it's a summary of the research project they did, and it's just for you to see that it's possible to do scientific projects in astronomy, also using the robotic telescopes, also in primary school. Okay. A bit more complex projects are those ones that I'm going to show you. This one, for example, is a project that was born as a collaboration with an amateur association, the CIDAM, Centro de Investigación y Divulgación Astronómica del Mediterráneo, and that was developed by the high school La Devesa de Elche with the guidance of the association and myself. And the project consisted of selecting an exoplanet candidate from one list of candidates that there are several lists in which you can try to find candidates of exoplanets. We have now more than 4,000, I don't remember the latest number, but it's more than 4,000 exoplanets that we have discovered in the last 25 years, more or less. So there are plenty of opportunities to observe them also with the robotic telescopes. So they selected a candidate that could be observed with the Liverpool telescope, which we could observe one transit, that is the path. I think Bea also explained this this morning, but a transit is the path of the planet in front of the star as seen from the Earth. So the planet blocks some of the light coming from the star, and they selected the candidate that we could observe in a certain month with the Liverpool telescope. They planned the observations. We obtained the observations with the Liverpool telescope, and they for all the transit, and we obtained several images to cover all the transit. They did what we are going to do later, what we call differential photometry, to measure the brightness of the star during the transit. And they represented and characterized the corresponding light curve that we are also seeing later. What is the light curve? Also, Fraser mentioned this morning. And then they analyze the curve, the light curve, with freely available internet tools. So they obtain this light curve here, and with those internet tools, they were able to obtain the parameters of the star and the planet, the exoplanet. So this project has this is the pilot project that we did, and then this has been reproduced by many other high schools, many other students at high school, doing the same process. They were the first ones, so they won the first prize in the category Adopt a Star in the international competition called Science on Stage, that Rosa and also a lot of my colleagues here know very well. And they won the prize in 2014, and among 400 other participants on that category. And another project, another example that was developed by a math teacher who attended our first astronomy adventure in the Canary Islands in 2015. And he, together with his 13 years old students, they developed this project in collaboration with me and also with another amateur astronomy association, the one in Gran Canaria, in another island of the Canary Islands. And the project consisted of looking for new variable stars. They selected 2 fields in the sky that were visible during 1 month, and they took several observations during different nights with 2 telescopes of Las Cumbres Observatory, and also with an amateur telescope of the Amateur Association in Gran Canaria. And they combined this data with a catalog, with the Northern Sky Variable Survey catalog. So they obtain a lot of different images. They measure the brightness of all the stars in the field, and they look for stars for which the brightness varies during the time. And they were very lucky. They found 2 stars of these types. We can see here what we call the light curve, that is the variation of the brightness with time. And these are the beautiful light curves that they found. They analyzed those curves with mathematical tools. They were doing this project in the math subject, and they discovered that those variable stars were not 1 star, but 2 stars. They were in what we call a binary system. 2 stars that are orbiting each other, and they eclipse each other on our line of sight. So they analyze those data, and they send the data, the light curves, to the APSO, that is the American Astronomical Association of Variable Star Observers, I think. And they are in charge of having an archive of all the new and old variable stars that are discovered. And this association told them that these 2 stars were the first time that someone discovered the variability. So they are the discoverers of those new variable stars. And they have their certificate And we also prepare a press release and send it to the media. They were on TV, on radio, and on many newspapers. So this is also important for the third part of the tripod, that is the society, the families. It's very important for the society to know that science is an accessible thing. It's also funny. It's also a motivating thing, and there is an important career that the new generations can have on science and technology. Okay, and then we move to you, and the third part that, or the second part, that are teachers. And we also organize several teacher trainings with local teachers here in the Canary Islands. We have a collaboration with the Department of Education of the local government, and we are running courses all along the year. We also have, since 2 years now, I think, we also have a collaboration with the CESAR team, and to reach teachers also on mainland Spain. And we also want the Canary Island teachers to have access to the training that the ESA organizes. So we are trying to have this bigger collaboration in Spain. And a very important one with Núcleo, with the FTP, National Schools Observatory, also with CESAR, organizing these GTTP courses that are really, really interesting, and I think important for connecting teachers from very different locations all around the world, to have a common sense and to share the experiences and to be in contact for future projects. Okay, so now I have presented you all the things, or many of the things you can do with this project, but I'm going to move to the website, because Peter is a web-based project, and I will show you where are most of the things that I've been presenting, where you can find them. And an important thing is that, so before I move away from the presentation, but you have this also on, so this is my email, this is the Peter website, but you also have this on Grasp, on the virtual campus, so I can stop sharing. And what I was going to comment is that one of the important things I wanted to comment is that I'm working on you know that internet is always, you have to always update things. So I'm working on an update of the Peter website. And one of the things I have on my list is to include the learning scenarios in English, because I have some of them already translated into English, and the idea is to have all of them, and also the research projects that are going to be on the website on the next few months, to have them in English and in Spanish, to allow also schools from abroad to, or from not Spanish speaking schools, to have also access to the resources. Okay, so now this is the Peter website, and it's going to change a bit, not much, but it's going to change a bit on the next few months. So this is the home, but the most important thing, if you want to participate on the project, obtaining your own observations, is to go here. I'm sorry because it's on Spanish, but I will try to do my best to translate it as we are navigating it. Okay, so the first thing is to go to participate. And here you have registered the fourth option. Centro is register your school. So
Mayra,
you click.
You're not sharing, sorry.
Oh, yes. Thank you. Thanks a lot. Yeah, I'm sorry. Okay. Yes, because I was not sharing my complete screen, just the presentation. Sorry. Okay, can you see it now?
Yes.
Okay, thanks a lot. Okay, so this is the Peter website, and here the second tab is participate, and the fourth option is register your school, registra tu centro. So by clicking here, you have an application form where you need to fill those fields here. The first ones are about it's your name, your surname, your email address, and if you are a teacher, if you are the director of the school, whatever you want to put here is your what you do at the school or at the association. And then it's about the school or the center itself. So it's the name of the school, where is it? This is, if you are not a Spanish school, so please, in province, not put the country, okay? So it's easier for me to locate you. And here in observations, you can tell me, so you have here some ranges. They are not perfect because you can use Peter with students from 10 to 14, for example, but it's just to have a sense of the group of students that you are going to use Peter with. And in observations, observaciones, if you are not a Spanish school, please tell me that you are attending this course and you are willing to collaborate with Spanish schools in research project. So I will put you in a list where Spanish schools with your data, but not your email, just the range of the ages of your students. And if you want to say, this school year, we are going to work on this, and for me, it could be very interesting, or my students are very interested in this type of objects, so we are very interested in work on this type of objects. So I will share that information with the Spanish schools that are registered on Peter, and I put you in contact with them to collaborate together and to be able to obtain your own images and work on that research project together. Okay, so this is the first step, to register. And I was saying, I have to check this. It's not an automatic thing. I have to check this one by one, and also to give you access to the observation portals that I'm going to show you now. So it's not an automatic thing. It can take me a while, so please be patient, and I will try to reply as soon as possible, starting next week, okay? Okay, so the next thing is the third tab, Observa, it's Observe, and you have here the telescopes that we have at the moment on available on Peter. I will add here the Open University telescopes that were not before. So this is one of the things on the updating of the website. You also have here how to request information on how to request images with the Liverpool telescope, with Las Cumbres Observatory, and I'm going to show you both very quickly because we don't have much time. I think I have 20 minutes more. Is that okay?
Yes.
Okay, thanks a lot. So I'm going to show you that for the Liverpool telescope, we have two options. One option is that I commented before on pre-designed observations. So these are the most easy or the easiest observations that we can obtain, because we just need to select the object. So let's go there. I'm going to remain here also. So here you have the instructions on how to use this interface with the Liverpool telescope. And if you go here to Quiero observar, I want to observe, and you click here, you are going to be redirected to the National Schools Observatory website, but to a different part, not the English part, but the part in Spanish for the Spanish schools, okay? So here at the top, you have to put the username that I'm going to give you. And your password that I will give you in the welcome email. And you access this main web page where you can select the type of object that you want to observe. So is anyone wanting to obtain an image of any of those objects? Here we have galaxies, we have the moon, the planets that are visible at this moment, stars and groups of stars. And then we also have advanced options for different research projects. Here we have the observations. I will come to this later. I will open this later. Here we have, if we requested some observations, is here in My Observations, where you can find if the images are already taken by the telescope. You can also check the meteorological conditions on the observatory during the night that your image was taken, or you can also do research projects about meteorological conditions in the Canary Islands, for example, compared to the place where you live using the data here. And here, I will also show this later, you have the archive data of the Liverpool telescope, where you can find previous images that could serve you for doing several research projects, as we are going to see later with the supernova, with the supernovae research. So, is anyone? I see something that I can read it because I think it's Greek or something like that. Anyone want to select one object? Anyone awake? Jupiter. Okay, let's see if we can observe Jupiter during the next days. I think so, but let's check. Okay, so I will, you just need to click here, but I want this, this also open, so I'm going to, no, okay, so I have to click here. And we click on Observe a Planet, Observa un Planeta. You see that you had different options, and what you are going to see is a color code on the about saying the visibility of the objects. So we have Mars that it's visible now, and it's a very good moment to observe Mars because it's very close to the Earth. We can also observe Uranus. Jupiter is, okay, so white or white-blue, it's the best, it's excellent observation. And dark or black is poor observation. And Mercury is not observable. You have not observable here because it's always very low, very near the horizon, and the Liverpool telescope cannot observe below a certain altitude, that is 35 degrees, I think. So Mercury is always below the limit of the Liverpool telescope to be observed. But Jupiter is still observable. So I click here on Jupiter, and let's see how easy it is. So we have selected for you the best instrument in the Liverpool telescope, attached to the Liverpool telescope, to obtain an image of Jupiter like this one, for example. And we have also selected the combination of filters that allows you to obtain a good image of Jupiter. That is the V band, the visible band, and also a neutral density filter that cut some of the light coming to the telescope, to the detector, not to the telescope, but to the detector, because as the Liverpool telescope is a 2-meter one, and Jupiter is very bright, so we need to put a filter to cut the amount of light reaching the detector, okay? We also have selected the exposure time needed to obtain a good image of Jupiter. So all you need to do is to click here on request observations. And now your request, our request, has been assigned a code. This is this number here. So when we go to look for these observations, if they have been done by the Liverpool telescope or not, we need to remember this number, or just look for the name of the object, that in our case is Jupiter. Is very easy to find it on our list of observations, okay? Okay, so this is one of the easiest ways to obtain our own images of objects in the universe. For example, you can do this to observe. You can request different images of Jupiter to see how the moons, how the Galilean moons, Galilean satellites move around Jupiter. As I think you also did this activity with Stellarium, and you can do this again with real images, with your own real images. You can see the phases of Venus, how they change. And there is an activity on the Peter website that I'm going to show you now, where we have obtained several images of Venus in different phases, but you can add your own images obtained during the month or the weeks in which you are doing this research project. You can add also new images that you have obtained. So there are a lot of different projects, easy projects that can be done even in primary with these tools. Okay, so this is how how do you call this? The observing portal of the Liverpool telescope works. You can also request different observations with different filters, with different times with the Liverpool telescope. But to do that with the Liverpool telescope, you need to send me a proposal of a research project. And it's me who is going to use the professional interface that communicates with the telescope. And because this is a more complex one, and I will request those images for you. But you can do this also with Las Cumbres Observatory by yourselves without my intervention. So let's go. Also, I think we were here. So, okay, before I move from here, I'm going to show you. Here is where my observations are. The list of observations is, so you can see here my observations that we see before. And here you can see that the image that I have just requested is this one. And it's saying that those observations has been sent to the list of observations of the telescope. So maybe tonight or tomorrow or during this week or next week, when the telescope has a time, it only needs like 4 seconds or so. It's going to obtain the image that I have requested. And once it's obtained, it's going to appear something like this. It's ready to download the image. So this one, I requested it on July. So if you click here, you can see this is a pre-visualization of the image. If you click here, you can just download the image. I'm not going to do it now. But you also have a lot of things that you can do here. For example, here it's going to show you the information on how to use another piece of software. That is the one that is being used by the National Schools Observatory, that is called LT-Image, that is very similar also to SalsaJ and to Petersoft. I don't want to do this. Let me check where I have back. Here. This is very interesting. Is conditions during the observation. And you can see here when the observation was took, the moon phase during that night. You have also here a whole sky view. So it's an image with a whole sky, obtained with a whole sky camera. You can see here the beautiful Milky Way on the sky of La Palma Island. And yeah, so this is, you should be seeing here stars, but probably the observation took more than, this observation took more than 1 minute maybe or so, so no more. So you can see the stars traces, I think, I hope this is the English word. So the stars moving along the sky with the camera on the same position. So they are not tracking in this image. I don't know why. Normally you see here stars in a larger field of view in which you have your observation, okay? This is probably Jupiter and other stars and stars on the field. Okay, and here you can see the part of the sky. This is again the whole sky. It's like a stellarium, and you can see here where Jupiter was during the observation, and again here the sky cams of the Liverpool telescope and the Liverpool telescope where it was pointing when it took the image. Okay, and more information. We have to navigate. Oh, a very important thing. We have to navigate back, because if you navigate on those main tabs, you go to the English part and you school. If you have a National Schools Observatory account, you are going to use the English portal, not the Spanish one. Okay, so you need to navigate back. And we can see also the meteorological conditions during our observation of Jupiter. So you have here humidity was very low. This is very good for astronomical observations. You don't have clouds, and the velocity of the wind Here, it was also very low, so probably very good conditions, as you can see from this image here. And okay, so you have also the temperature during the night. It was July, it was very warm, and so on. So you can do a lot of different things together with not only the research on the images, but also a lot of related research with the conditions of the sky, with where in the sky it was Jupiter, and so on. Okay. Okay, so I move now to the very quickly, because I think I don't have much time. But here is, you can also, as I said, you can also obtain your observations with the 40-centimeter telescopes of Las Cumbres Observatory in the 6 different locations all around the world. And for that, here you have instructions on how to use the observing portal of the LCO. You have also a video explaining how to go through all the steps of requesting the observation. And here you have the access to the observing portal. So I think I don't have time to go through that, but just to say that once you have an account, once you request a Peter account or a LCO account through any other project in your country, for example, there are, I think now we are more than 20 projects in the program called, what's the name? So the LCO has an educational program that give access, as Fraser said this morning, give access to many different projects all around the world to the 40-centimeter telescopes for education. And Peter is one of those projects, but maybe there are other projects near you, on your country or on your region, that also have access to the LCO. So please go to the LCO website in the education part and look if you have a project. I think Mert Kocher, that is also here, he also has a project there or is collaborating in a project. So if you go to the LCO portal to education, you can see the list of projects that have access to the LCO telescopes. So once you have your account, you go to login, you put your username and password, and to submit an observation, you go here to submit. And you, okay, one of the things I have to do is here, profile. I have to change this to the simple interface that is the one that probably you are going to use. And now again, I go to submit observation. And here you will see that you can, this is the name of the observation that you are going to obtain. In propose, those that are Peter users have to select Peter. I think it's the only option you are going to find there. The only instrument you are going to find is the 40-centimeter telescopes. Here in exposure time is the number of seconds that you are going to be summing up light on the detector to obtain the image. No, sorry, the exposure count is how many images you are going to obtain. And exposure time is the time you are going to use. And it's very, very useful that you have, okay, you have here and the exposure time calculator that allows you to find out which is the the best or which is one good exposure time for the object that you want to observe. Okay, so the instructions are on the website, very step by step. So I'm going to finish here with this, and just I will comment this later on the next session that is after the break. So, but one of the things I want to comment, just for those of you who cannot be with us later, here in Discover, you have several activities on different objects. These are the learning scenarios I comment you, and they are from primary to secondary education. And for example, one of them, you have the introduction, where we introduce the astronomical concepts and mathematical concepts that we are going to use. And then you have the activities with the images, the real astronomical images that we are going to use, and a guide to go through all the processes. So we are going to see this later after the break. So I think I can stop here. And because it's time.
Many thanks, Naira. It's just there's no break at the moment. So the break is after the next talk. So in principle, you can continue with Fraser and enter the hands-on session on the Supernovae with robotic telescopes. So if in principle you can continue talking if you want.
Okay, that's true. That's true. Thanks, Michael. Okay, so so I will show you very quickly one of the. I'm still sharing my. Can you? No,
I'm not sharing anymore.
Oh, okay. But I've been sharing for the last 20 minutes. Okay. 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 Can you see the website again?
Yes.
Okay. Thanks a lot. Okay. So this is, for example, an activity about the solar system, the inner and outer planets. And here in the introduction is a PDF file where, as I was saying, you have in Spanish at the moment, but this is going to be also in English. If you are interested to use it, it could take me 1 month or so to do the website update. But if you need it for next week or so, just write me an email and I will send you this in English, okay? So, for example, you have here information about the inner and outer planets, the difference between them, also about transits of the inner planets, and also when you have these things like comments in the text, it's because it's related to some mathematic tools or some mathematic concepts that you need to do the activities, okay? So this is the introduction, and then you have the guide to do the activities. And you have step by step all the process you need to follow. These activities use Petersoft, the software that is specific for this project, but you can also use SalsaJ. It's totally the same as we are going to see in the activity that I'm going to present you now. So step by step, all what you need to do to do the learning scenario, okay? Or the activity. I also have this is what we call a didactic unit, but I also have prepared this as a learning scenario with more like a research project, project in which the students need to think, not only go step by step, but they need to think how they are going to investigate this. And also, if you are interested on this, write me and I will send you the presentation and the tools to work with this, with your students as a learning scenario. Okay. Okay. So now I stop here, and I will start with the second activity, or the second part, that is more a hands-on set. It's a bit also of an introduction, because Fraser is the one who is going to do the more hands-on part, but I also have a bit. So this is this one about supernovae, because supernovae, also Bea mentioned this, I have like an introduction to start, because I was not sure if we were going to have this on the course before my talk. But Bea did it very well this morning, so I'm just going to go very quickly through the concepts that we need for the activity. Okay, so I will start to share again. Okay. Can you see the presentation, Supernovae with robotic telescopes?
Yes.
Thanks a lot. Okay. So, okay. So one of the things, one of the most interesting projects that we can do with robotic telescopes is to measure the brightness of the objects and to see if they change with time. This will allow us to investigate a lot of very interesting objects, like, as I mentioned, exoplanets or supernovae, or variable stars of different kinds, to discover, for example, also to measure the rotation velocity of asteroids. So there are many things, many information that we can obtain measuring the brightness of an object. But before we go to see one of these research projects that is about supernovae, I'm going to present you some concepts that we need to know before doing the activities. So this the activity that I'm going to show you later is the Unit 3 about distances and quasars in the Peter website. So for the Spanish speakers participants, you can already you can go to the Peter website and download everything from there and use it with your students. And for the English speakers, it's on. I put all this information and all the things you need on GRASP, on the virtual campus of the course. Okay. So let's start. And one of the things we can ask ourselves or to the students is, how do we determine distances to objects on Earth? And on this brilliant lesson from Coco, I hope you can see it, because I think I'm sharing in the normal way, not a video, but let's see if you can see it. In this brilliant lesson, Coco from Sesame Street explains the concepts of near and far. So let's see if we can see him and listen to him. Can you hear, Coco?
No.
Oh.
Do you share for video?
Yeah.
Can you stop sharing and share?
And you have to click the button without including audio.
Yeah, okay. The thing is that, let me check, because I'm using the website, not the WebEx app. So let me stop sharing. And again, let me see if I have that option. Optimize, optimize for motion and video. Screen. Oh yes, share audio. Perfect. This one. Okay, let's see if we are lucky now. Okay, let's try.
Hello there.
Can you hear
This is your
now?
old pal Grover. And
Yes.
today I'm going to talk to you about near and far. In fact, I, little furry Grover, am going to show you near and far. Okay, here goes. First, this is near. Right here, near. This is far. This is near. You see?
Okay. So what Coco is trying to teach us, so that he's trying to say that objects of a certain size, when we have them close to us, we see them bigger than when they are far away. And if they emit sound, we can hear it even if it's weak, if the object is close to us, but if the object is far away, the sound it emits must be louder in order for us to perceive it. So, what happens when we observe the cosmos? Do you think will those notions help us to determine the distance at which objects in the universe are found? What do you think? For example, stars and galaxies, the ones that we see here. Can we say which ones are closer to us and which ones are at a higher distance from us? What do you think? Let's see if is anyone saying anything. No? No? Okay. We cannot say at which distance they are just from this image here. No? Okay. Okay. So this is true. Why? Because stars and galaxies have a huge variety of sizes. So how can we know whether a galaxy that we see larger than another one is really larger, or whether we see it larger because it is closer to us? So just from an image, it's very difficult to have a sense of distance on the universe. And if we observe two stars, can we tell how far away they are from each other just from an image like this one? What do you think? We have two stars, star A and star B. Do you think that we can say which one is closer to us? Let's check the chat. Yes, okay, so no, yes, no. So who is Neto? I don't know. So the person who said yes. And another one who said yes. By Redshift, okay. We haven't mentioned this yet, I think, but let's see if we can say which one is closer to us. So, for example, we see that star A is bigger, or it appears. So we see the star A bigger. It appears bigger and brighter than B for us. But this may be because of two things. The first one, star A could be intrinsically, I don't know how to say this, intrinsically brighter. That is, it emits more radiation per second than star B. This is the first option. Or there is another option that star A is closer to us. And because of this, we see it brighter and a bit larger, a bit bigger. Okay, so again, from an image like this one, if we don't have any other information of, for example, of the type of star that we are observing, and for that we will need a spectrum of the star, or at least an image of the star in different colors. If we have some other information about which type of star we are observing, then we could say if a star A is closer or not than star B. But just with an image like this one, it's very difficult to try, or almost impossible to say which one is closer to us. So how have we solved this problem in astronomy? So we have been discovering and proposing new methods to measure distances in the universe, and it's for a long, very long time. And each method has its own limitations. It is useful for measuring the distance to celestial objects within a certain range of distances, but it's not useful outside that range of distances. And this is why we speak of a distance ladder. Each new step in that ladder includes one or more methods that allows us to determine the distance to more distant objects. And normally, each method, each step on that ladder needs to be calibrated with a previous method. And for that, we need to know the distance to an object that we use as a reference through the lower scale. Okay, so one object that we can determine the distance through the next step and through the previous one. Okay, so there are many different methods, and here you have some examples, but we don't have time to go through them. And I'm going just to mention some of them. For example, the parallax one, and I think this one is just this one. Yes, is introduced in the Unit 2 about distances and galaxies on the Peter website. So this method, you can find more information about it on the Unit 2, and also with an activity about galaxies on the Peter website. And the Unit 3 presents methods, the methods used at longer distances, like the Cepheids, and also about the supernovae and the Hubble law that we are going to mention now, and with Fraser you are going to see in greater detail. Okay, so before we go any further, we need to introduce some concepts, and I think probably most of you knows the difference, but I think it's important to have this clear before we continue. And we have several terms to talk about brightness. And we have, in one part, we have what we call luminosity, that is an intrinsic magnitude. It's an intrinsic characteristic of the object. It's the amount of energy, electromagnetic energy or light, or electromagnetic radiation, that the object emits per unit of time. And on the other side, we have what we call the apparent brightness of the object, which is the amount of energy per unit of time that we receive here from on Earth, or where the detector is, if it's on the space, on a space. So luminosity is an intrinsic characteristic, the light that the object emits, and the apparent brightness is the light that we receive from the object. Okay, these are the differences. Luminosity as is energy per unit of time is actually a measure of power, and apparent brightness has units of flux, okay, because it's per unit area, per unit of area also. And okay, so the apparent brightness or flux measures the amount of light we receive from an object per unit area, as I said, and it decreases with the square of the distance to it, because the area where the light is distributed grows as the square of the distance. So we can see it here. The area in which the light is distributed increases as the square of the distance, and therefore the light decreases at the same on the same amount. Okay, so this means that the farther away the object is, the less light we receive from it. If we are here, we receive less light than if we are here. Okay. Therefore, the apparent brightness depends on the distance between the object and the observer. And just to have an idea, just one example. And a star which emits the same amount of light as another star, but is twice as far away, will look 4 times fainter. They have the same luminosity, they have the same intrinsic brightness, but they have very different apparent brightness, the ones that we receive. Okay, so this about luminosity and apparent brightness is one of the concepts. And we have another magnitude, another way to indicate the apparent brightness or flux of a celestial object that is called magnitude. The apparent magnitude of an object is the brightness as it appears in the night sky from Earth. And it can be defined by this equation here, where, so this is the apparent brightness in the X band or in the X filter, and it has this complex form here that is minus 2.5 log of the flux in that band. So Fx is the luminous flux observed in the filter or in the band, and C is a constant. So why this very strange parameter to talk about brightness? So this system for measuring brightness comes from the ancient Greece, about 2,000 years ago, more or less. And its origin lies in the fact that the brightest stars visible with the naked eye were classified as magnitude 1 and the weakest as magnitude 6. So the apparent magnitude increases in the opposite way, in the opposite direction of brightness. The brighter an object is, the smaller its magnitude is. And this is why the minus is here, okay? And this part here is related to the response of the human eye to light. Our response to light is logarithmic, so the scale should be also logarithmic, okay? Okay. And we also have another parameter that is called absolute magnitude, that is related to the intrinsic brightness, to luminosity. Why? Because it's defined as the apparent magnitude that an object would have if it were at a distance of 10 parsec. If all the stars were at the same distance from us, 10 parsecs. We haven't introduced the astronomical distance measurements, but parsec is one way we have to measure distances in the universe, as similar one to as could be the light year, for example. They are defined in different ways, but they are ways we have to measure distances in astronomical scales. Okay, so the absolute magnitude is related to the apparent magnitude with this equation here, and and this equation allows us to determine if we have any method. By any method, we know what the luminosity of an object is. We will know what its absolute magnitude is, and if by any method we can determine this, the luminosity of the object, we can have the absolute magnitude, and measuring the apparent magnitude, the brightness that we receive, we can determine the distance to the object. Many methods on the distance ladder for determining distances in the universe are based on this equation here. And the method that we are going to introduce today uses this equation here. It's based on this equation. Okay, so the method that we are going to explore today is based on supernovae. So let's first see what a supernovae is and what types of supernovae we can find on the universe. Bea introduced this a bit this morning, but I'm going to give you a refreshing time about this. A supernova is a star that dies in a very violent explosion, and supernovae can produce as much energy as an entire galaxy in a very short period of time. Some of them were so bright that they could be seen even in daylight. But however, they are very rare events. It's estimated that only 1 or 2 occur per century in our galaxy, but we can detect them with the telescopes we have nowadays, also in other galaxies. And this is the thing that Fraser is going to tell you later. But first, let's see the different types of supernovae that we can find on the universe. So as Bea also mentioned this morning, stars evolve differently depending on the mass with which they are born. And this largely determines the different phases they go through and the way they end their lives. This diagram here shows how stars evolve over time as a function of their mass. The greater their mass, the greater the mass of the star, the faster it evolves. Here we have the mass, and on the x-axis we have time. So as we can see, the greater the mass of the star when it burns, the faster it evolves and the faster it dies. Okay, so I won't comment much on the evolution of the stars. Bea also comment a bit, but what we are going to focus on how they die, depending on their mass. So let's start with the most massive stars, which are those born with more than 9 times, more or less, the mass of the sun. And these are also the hottest stars. And they end their lives with energetic supernovae explosions. And here is an animation. Let's see if we can see it. Yes. Here is an animation of a supernova explosion. In particular, the one occurred in 1054, which gave rise to the Crab Nebula, if I'm not wrong. Okay, so this, you have seen the explosion of most of the star, the outer layers of the star, or most of the star, as a supernova. And then on the center, the core of the star, so the external shells of the star are ejected in the supernova explosion, while the nucleus collapses and becomes a neutron star for stars up to about 30 solar masses, or they continue collapsing to a black hole for the most massive ones, for those that were born with more than 30 solar masses. So stars that are born with masses between 8-9 times that of the sun, up to 40 times, they end their lives as what we call a type 2 supernova. I think Fraser is going to mention this also, but just to have an idea, the most massive, not the most massive ones, but from about 9 solar masses to 40 solar masses, they end as a supernova of a special type that we call type 2. If they are more massive, if the star was more massive than 40 solar masses, also at the end of their lives, they explode as supernovae, but of a different types, what we call the type 1b and 1c. The types depend on the chemical elements that we can detect on the remnant of the supernova. But I'm not going to enter on those details because we just need to know which supernovae is the one interesting for us. And for this, we are going to concentrate on the brightness, not on the chemical elements, okay? Okay, so we now turn to sun-like stars. They are intermediate mass stars, and they are those born with a mass between half the mass of the sun to about 8 and 9 times of the mass of our star. And those galaxies evolve more, so take more time to evolve. They live longer. And as all other stars, they begin their lives burning hydrogen in the core and converting it to helium. And when the hydrogen at the core is exhausted, it has become all helium. The outer layers of the star expand and cool. And the star then becomes a red giant. That is let me see if I can do it again. To put the animation again. Oops. No. Let me from here. No. Okay. Okay, so if you were lucky, you saw the from here. No. Oops. Okay, now. So the star becomes a red giant there when the hydrogen on the core it's finished and is converted everything into helium, and then the star becomes the red giant, and these phases end when the core that collapses reaches the temperature enough to start burning helium, which becomes the new fuel. But when the helium also is consumed, the star is no longer being able to what's the name? To burn the next element inside on the core of the star, and then the star start to pulsate, and at the end it expulses, it No, this is not the word. So at the end, it, how do you say this? Let me see. Here, no, here. Okay, I don't have the final phase. So in the end, when all the helium is consumed, the star starts to, becomes unstable, and it expelled. Yeah, this is the word, expel the external layers as a planetary nebula, and the core of the star becomes a white dwarf. Okay. Okay, so these types of stars, solar type stars, do not end their lives as supernovae. They end as the outer layers are expelled as a planetary nebula, and the core becomes a white dwarf. But if they are in a binary system formed by two stars of low or intermediate mass, that they are in contact, and this means that the two stars orbiting each other, they are at a very short distance. So when one of them reaches the phase of white dwarf and the companion expands when entering the phase of red giant, the white dwarf can begin to steal material, as we can see here, steal material from the companion, and but it's gaining mass, but it cannot be consuming or stealing mass forever. When there is a critical mass of about 1.44 solar masses, at which it becomes unstable and explodes. And this explosion gives rise to what is called a type 1a supernova. And these are the ones that are going to be interesting for us today, because in these explosions, the amount of energy released is quite uniform. So at the maximum brightness, the maximum intrinsic brightness, that is when they explode, the maximum light that they emit is always the same, because they always explode when they reach the 1.44 mass limit. Okay, so we can know which is that maximum brightness, and therefore we know the absolute magnitude, that is this one here. So the absolute magnitude that is related with the luminosity or intrinsic brightness is known. So what can we do? By measuring the apparent magnitude, that is by measuring the brightness of the supernova that we receive here on Earth, we can calculate its distance using the equation that we saw before, relating the absolute magnitude, the apparent magnitude with the absolute magnitude. Okay? Because of this, they are considered type 1a supernovae are considered standard candles. So let's see an example here. So here we have two images taken by the Hubble Space Telescope, and one was obtained in 1995, this one here, and this one was obtained some years later in 2002. So do you see any difference between them? Let's see if there is any answer. Okay, do you see any difference? Oh yeah, oh, I have to go down. A red dot, yeah. So does anyone want to say where more or less it's that red dot? Red point, red light, yes. Very, very good eyes. More or less at the center, yes, perfect. Yeah, so here there is a very bright red point that is not here. So this was a supernova that exploded in this galaxy here. And this is something to compare, visually compare two images of obtained at different moments on different years is one of the projects that we can do with our students, even on primary school. So we can select a galaxy that is visible during the time that we want to do the project. We can go to the archive that I saw you on the National Schools Observatory website, for example, on the Peter website. There was a tab called Data Archive. So you can go there, look for galaxies that are visible now, look for old images of those galaxies, and request a new image of that galaxy with the same filter, the same exposure time. There is also an archive data of the LCO, of Las Cumbres Observatory. So you can choose the Liverpool Telescope or Las Cumbres Observatory. You go to the data archive, search for a galaxy that is visible now during the month that you want to obtain the observations. Go to the archive, look for an image of that galaxy, and request an observation with the same filter and the same exposure time. You obtain your image and you compare it, as we have done here. You compare your new image with the one in the archive. If you see any bright point, like this one, it could be a supernova. You have to check that it's not a bright point of the detector, so it's better not to take just one image, but to take like several ones. For example, if a cosmic ray has reached the detector in some part of the detector that could be similar to a supernova, but it's one of the easy projects that we can do with our students. And if we are lucky, we could discover a supernova and be in the news. And also, not only be in the news, but to do research about what a supernova is, why we are seeing the supernova in one image and not in the other one.
Estaba ahí en terra. Es un disc tour de estos chicotets.
Hi, Andres. Okay, so this is one of the easy projects I said that we can do. We have another example. Here, one that is more, it was in 2014, it's more recent. So we have those very beautiful and color image of those very well-known galaxies. And in 2014, a supernova was discovered in M82. And we can see here this very, very bright dot there. As we said, the luminosity, the brightness of the supernova can be as high or as high as the luminosity or the brightness of the whole galaxy. Okay, so we have that simple project that is to detect a new supernova, but we are going to move to a more complex one, that is to analyze the light curve, the variation in brightness of a supernova that we have discovered, or that someone else discovered, and we want to measure the change in the brightness. Okay, so how we have two questions here. How do we know what type of supernova is? If we detect one, how do we know what type it is? And as I said, we can obtain a spectrum of it and try to see which chemical elements are on the supernova remnant, but this is a more complex thing. Or we can measure the brightness of the supernova along the time and obtain what we call the light curve, as the ones we have represented there. And the other question is, how do we know what is its maximum brightness? What its maximum brightness is? Because we need the brightness in the maximum. That maximum brightness is the one that we know the absolute magnitude that corresponds to it. So we need to measure also the supernova next to its maximum brightness. So for this again, if we measure the brightness along the time, we are going to see when that brightness peaks. And here we have light curves, that is the variation of brightness. In this case is absolute magnitude, because they are displaying the different types of supernova, the light curves for the different types of supernovae. And on the again, on the x-axis, we have time. And more concepts that we need. What is a light curve? So the light curve of a celestial object is the representation of the variation of the apparent brightness of the object over time. And to determine the brightness of the object, we have to compare the measured brightness with that of a non-variable star, a standard non-variable or standard star. If we use as a reference a non-variable star in the same image as our object is, we call this differential photometry. And if the reference star is not on the same field and is a calibration star or a standard star with known absolute magnitude, or no, not absolute, sorry, with known apparent magnitude in the same filter, we call that flux calibration. So we have two types of techniques, of astronomical techniques to measure the brightness of an object. And what the one we are going to use is what we call differential photometry. And in that technique, we are going to integrate all the light that is inside a circle that we call the aperture. And we also need to extract from our measurement the contribution from the sky around the object. And for this, we construct what we call the sky ring. That is this ring here in which we determine the contribution of the sky that we need to extract from our measurement here, because here we have the light coming from the object, the star or the supernova, but we also have the light coming from the sky. Because of this, we have to remove that contribution. Okay, so now we move to the activity, the practical activity, in which we will learn how to measure the brightness of an object and determine whether its brightness varies over time or not. And this is as I said before, this is the activity in Unit 3 that is called Distances and Quasars in the Peter website. And you can also have this on the virtual campus on GRASP, on the folder called Day 4, I think it's Supernovae with Robotic Telescopes 1. Okay, the second part is that that Fraser is going to show us, but this is 1. Supernovae with robotic telescopes, 1. Okay. So first, I'm going to introduce very quickly, because also Bea mentioned this this morning, at the center of the majority of spiral galaxies, if not all of them, there are several studies saying that in all spiral galaxies, there is a supermassive black hole at the center, at the very center. And in the case of the Milky Way, there is an intense radio source named Sagittarius A, which is likely to be a black hole of about 4 million times the mass of the Sun. And these kind of black holes are found in the center, as I said, of almost all massive galaxies. So in some cases, the center of the galaxies also hosts what we call an active galactic nucleus. It is a compact region at the center of a galaxy that is much brighter than expected for the type of galaxy. And this excess luminosity is not produced by stars. The excess emission has been, it's believed to be the result of accretion of matter by a supermassive black hole at the center of its host galaxy. And AGNs, the active galactic nucleus are called AGNs, are the most luminous persistent sources of electromagnetic in the universe. And this is the reason why we can detect them at very long distances. Okay. And then we have another concept, another type of object, that is the quasar, or quasi-stellar object. This is an active galactic nucleus of very high luminosity. A quasar consists of a supermassive black hole surrounded by an orbiting accretion disk of gas. As gas in the accretion disk falls toward the black hole, energy is released in the form of light, of electromagnetic radiation. And the most powerful quasars have luminosities thousands of times greater than the luminosity of a large galaxy such as the Milky Way. And what else? So let me see if I have more info here. No, okay. So why I'm talking about quasars if we were talking about supernovae? Because the activity that we are going to do it uses real images, real astronomical images of a quasar instead of a supernovae. But the process that we are going to do, we are going to follow, is the same for any type of object for which we want to measure if there is a variation of brightness or not. So imagine we are going to analyze the data of a quasar, but it could be the data of a supernova or of a variable star. The process is the same, okay? So, okay, so here what we see is this is the image of the quasar, and as you can see, with this is an image taken by the Hubble Space Telescope, and it's like a star. It's like a point source. It's very, very similar to a star. But if we, for example, with a coronagraph, we block the quasar's light, then we can see the galaxy that hosts that quasar, that supermassive black hole. Okay, and this is the galaxy around the quasar that is at the center of the galaxy. Okay, so let's move to the activity. And for this, you can do it with the material on the Peter website. Here you have where you can find the activity, or I think it's easier if you go here to GRASP, where you are going to find everything, all the material that we need to analyze the image of the quasar that is called, this number here is 3C454.3. This is our interesting object today, okay? So I'm going to move away from the presentation and I'm going to go to GRASP, okay? And then this is the first step, to go to GRASP and open the folder with the images and everything. And the second thing, I'm going to give you some minutes to open SalsaJ. You can also use Petersoft, that is the piece of software that we use in the activities on Peter, but we can do it also with SalsaJ. And I'm going to center today on SalsaJ because it's the software that you are using on the course. So I stop sharing. Okay. And then please take some minutes. I'm going to, I think it's open here. Okay. I'm opening GRASP. Okay. So I'm going to share my screen. And I'm going to share the complete one. I think you are not, you are not seeing my, okay. Can anyone tell me if you are seeing, or if you are seeing the
No,
WebEx?
we see WebEx.
WebEx. Okay, so it's going to be difficult. Let's stop sharing.
You have to share the full desktop or screen or whatever you're using, Naira.
It's what I did, but as I have two, it's showing you. I was screen two. Let's try that. Okay.
That's okay.
Now it's okay. Perfect. So we go to day 4, discover supernovae, and here you have the presentation that I was presenting you, and here this is for the people who want to install Petersoft, but is not needed for today activity. So the second step is to open SalsaJ, and the third one, or the second B one, is to download the images, the quasar images that you can find here. So please let me know if you are there. I'm going to, in the middle, I'm going to open SalsaJ. Please let me know if you have any question, any problem.
Naira, we should go for coffee break in 1 minute.
Oh my God, 1 minute.
And then you continue to have a session. You can continue. You have 1 more hour after coffee break.
No, but this is Fraser.
Okay.
Yeah, so very quickly. He's going to kill me because he wanted me to introduce differential photometry, but I think more or less you have the concepts, not the practicing, but okay. So in 1 minute, I'm going to do it myself. I'm so sorry that you cannot follow me. But what we have to do is to here, sorry, just 2 minutes, please. I'm going to do it very quickly, so all of you can do it later. So here, what you have is what we call a finding or finder chart or celestial chart. It's an image of the sky centered on the objects that we are interested in. And this is the quasar, the 3C, 4, blah, blah, blah. And we have 2 reference stars on the field because we are going to do differential photometry, star 1 and star 2. So the first thing we have to do once we have opened SalsaJ is to open the file, open the image. You can just leave it here, or you can look for the folder where you have them. I had to close, I have it open, but I had to close because my laptop was doing strange things. Okay, think, web. Okay, and just select one. Just select one of the images. You don't have to open all of them. Just select one image. And as Rosa showed you, you have to work a bit with brightness to see the objects clear. Then the next step is to locate the object. Okay. Okay, I think there. To locate which of the objects is the star and which of the object is the quasar. Be careful because, as you know, sometimes the images don't have the same orientation in the finding chart and in your image. And as you can see, we have 3 stars here, 3 objects there, and like an arc of 3 other objects here. So this arc, I think is this arc here, and these 3 objects are this. Closer to the closer to the arc is the quasar. Okay? So this object here is the quasar. So what we are going to do, you have this on the presentation, all the process, all the steps you have to follow. What we have to do, we need to do is to go to Analyze Photometry and to click. This white window is going to open to do the photometry, and you click on the object. In this case is the quasar, and you obtain the photometry here. Okay, and then you click on the reference star 1 or star 2, that is this one here, and you also obtain the photometry. Okay, so if you are using the Spanish version of SalsaJ, there is a bug here, and this is intensity, not Y. Okay, this is X, this is Y, and this is intensity. Okay, so these are the numbers, the brightness of the object that we are measuring inside the aperture. This is the numbers that we need to introduce them here in the Google spreadsheet, that is this one here. So what we call differential photometry is to compare the brightness of the object in which we are interested. In this case is the quasar, but it could be the supernova. And the brightness, we are going to compare this with the brightness of the reference star on the image, because they are going to be affected by the same conditions, the same amount of, let's say, light from the sky, or more or less, the same extinction, that is the part of the light that is not reaching us because of the atmosphere of the Earth, and so on. So if we divide the brightness of the object that we are interested in by the brightness of a reference star, that its brightness do not vary along the time. We have selected it to have a non-variable star that its brightness is the same, more or less, along the time. So we can see the real variation in the brightness of the quasar or the supernova. Okay, this is what we call differential photometry. I'm sorry we didn't have time to do it together, but if you have some time later, you can do it, and this is for us to work. You can put your numbers here, and we can comment this later or tomorrow at the end on the project exploration, or tomorrow at any break. We can comment on the results we obtain. Okay, thank you so much. I hope Fraser is going to tell you more about this, and I hope you have a clear idea of what differential photometry is with the activity that is coming after the small break, small coffee break. I don't know if there is any question. Fraser is saying that he's rewriting his slides. I'm sorry, Fraser.
Well,
I'm very sorry.
No, but it was a very interesting and complete presentation. I suggested now we give some 10 minutes. David, please restart the counter if you were there, to give 10 minutes to the teachers for a short break. And yeah, thank you very much. So you have 10 minutes. And we are back with Fraser. And all the questions that were to Naira, you just drive them to Fraser. So go get your refreshments, and we are back in 9 minutes and 45, 44, 43. David, you can put the relaxing music, and we all go off for a moment.
Thanks,
Thank you, Naira. That
Thanks,
was superb.
everyone. Thank you.
Managing your project.
So hello. Welcome back after the coffee break. Naira is also back.
Quicker than me.
Yeah.
So
I leave it up to you, Rosa.
well, no, it just we gave them a little bit more, but I think we can go back. Now it's not up to me. Now we have to give the floor to Fraser.
Yes.
Fraser, you there?
I hear you. I hear you. I hear
You
you.
hear me?
Yeah. Do you see my screen okay?
Yes, we do. And we
Okay.
see yourself as well.
Good. So
Okay.
Rosa, Naira, do you know, I'm not angry about you running over. and I'm not angry about you not covering the material you said you'd cover. But then you said, and if you have any questions about my presentation, ask Fraser.
This is my cold revenge to you.
Do you know?
You know what? My camera is not working, so this is the universe telling me you shouldn't have done. Okay, I feel guilty. I'm so sorry.
It's fine. It's fine. It's fine. We'll live with it. So I'm going to show you a handful of slides, and then I'll show you a little bit about the Supernova project that I've got running that really looks a lot like Naira's. There are a lot of nice similarities there. And then I will get you all to do an activity. So rather than just sitting, you're not going to be sitting listening to me for an hour. We'll get you doing a little bit of work. And I'll show you some of the projects we've got going and kind of ask you if they make sense. And if we get time at the end, then ask you what other things you want to see. So I'm just going back for those of you that saw this morning's presentation. It's a while ago now, a long time ago. This is the Gaia Alerts website that you see at the top left of the screen. This is one place to go to find targets if you want to do science. If you want to do pictures of galaxies, pictures of planetary nebulae, supernova remnants with any of the telescope resources we've mentioned today, then that's absolutely fine. But often it's nice to do the science. So this is the Gaia Alerts page. This is the format of how it looks. And then, as I mentioned before, gaia.ac.uk has some really nice 1-minute cartoons that just show a little bit about what Gaia does. So I thought I'd mention those just to start off with. And then show you some light curves. So this is the kind of data that we get, or these are the kinds of numbers. I'm kind of jumping a couple of steps from where Naira got to, but you probably saw where she was taking you with the Excel sheet. And I'll show you a version of that in a minute as well. But these are the kinds of light curves we see from supernovae. So you'll probably recognize there that there are about 15 data points. And I know there were questions in the chat about how many do we do. And in most cases, yeah, the answer is do all, do the work, do the science, the photometry on all the data you can get your hands on. But clearly, if you have students that want to work in pairs, or you want to divide a data set amongst 3 students or 5 students or 2 schools, these are options that are available to you, of course. And I appreciate with some of the data sets, they're very large, and it does drive you a bit mad if you try and do more than 10 or 20 frames at a time. So these are the kinds of results you see, a light curve, a change in brightness of this object over a few days, and then a general fading away of the object. And that's what we expect to see from most of the different types of supernovae. This is a 1C, so this is one of those very massive stars that Naira mentioned towards the beginning of her talk. But the ones that I'm most interested in, I can't remember how many of these are, but we'll come back to that point in a second. The majority of the ones that I'm interested in are the type 1As. So these are the ones that are formed via a different mechanism. They're formed by the idea of just overflowing material onto a star, onto a white dwarf that can't cope with that material, and you end up with an exploding star. But I don't know if that's my microphone or someone else's.
Muted.
Okay, thank you. So you end up with a set of stars, a set of supernovae, all of which you know how bright they actually were. It goes back to Grover and the idea of how far away things are, and that's the determining factor in how bright they appear. So these are different data sets that we have, and you can see this fairly familiar pattern of a peak and a fade away. From that, we can measure how bright this star actually became, and from that, we can start to do something very, very clever indeed. You may have come across it. It's one of the very few things that we see in astronomy that does make it into every curriculum, which is the idea of a Big Bang, the expansion of the universe from a single point, and a feel of how old the universe is right now and how fast it's expanding. That's all driven by work that was done originally in the 20s by Edwin Hubble and his group in Palomar in the USA. And he determined this thing called a Hubble plot, which is what this is a representation of. And this says, in a sense, because it's a linear, there's a linear fit to these data, this says the farther away an object is, the faster it appears to be going away from us. Okay, so the further away we look, the faster things are going. And that isn't related to us on Earth or us in our solar system being in a special place. That appears to be the case throughout all of the universe that we look at. So I know I'm working you hard, and it's getting late in the day, and I'm sort of saying, okay, there's supernova and they're exploding stars. And from exploding stars, you can measure something about the universe and something about how the universe was. And that's true. That's what cosmology is the study of. This work was followed up in the 1990s. There were different groups looking at different types of objects in faraway galaxies, without going too far down the Star Wars line. And in each case, when we look at distant galaxies, we get distance measurements to those galaxies that suggest they are flying away from us. And that tells us something about the expansion of the universe, as I mentioned. And that did go on to win the Nobel Prize for a couple of groups in the early 2000s. You can actually do a fraction of that. You can do some of that science with the data from our telescopes. So what we were doing, and what Naira was showing you before, is the idea you can measure the peak brightness of a type 1a supernovae. If we feed you an extra bit of information, which is how far away is that galaxy from us, or rather how fast is that galaxy moving away from us, you can add your data point to this graph. And that's what we've done with a set of data here. And again, it's this astronomical data that doesn't all quite sit on the line, but it gives you a fair idea. If you measure the trend line, the gradient of this line, you get a value on the top right, which is about 66.7. If any of you have a cosmology background or have looked into the idea of the Hubble parameter, the idea of how fast things are moving away, 66, 68 is about the right number. It's got a set of units that come after it that make it very tricky. Okay, hopefully that makes sense. I know I'm really jumping quite a long way from supernovae to the Hubble plot, but hopefully you can see what I'm sort of suggesting here. And the key, in a sense, is collecting data. Because if you collect data on a brand new supernova and it's a type 1a, you can add the data that you calculated to your own Hubble plot, and you can make a measurement of that value. And I'll just show you an example of that in a second. This is an example, again, Naira sort of showed this quite nicely before as well. These are the kinds of images that you might be playing around with. So the image in the top right shows you a bunch of stars, and where there's a little red circle, there's nothing in the red circle. That's an old image of this particular field. An image that was taken by the telescopes that I work with on the bottom left shows that there is a very obvious dot, or a very, very obvious star that wasn't there in the past. It's in the green circle. I got a little bit carried away. I told you before I have access to all these telescopes. Well, I got a bit carried away, a bit bored one day, and I ended up with 250 images of this one supernova in different filters in the optical band from different telescopes that I and that you have access to. That then allowed me to create these graphs that are very, very straight, very linear graphs, which, again, astronomers get a little bit worried when you see data that seems this well behaved, but this is a really nice example of how far you can go with this project. I wouldn't suggest doing the photometry of 250 images. I think that will drive you a little bit loco, so that's probably not ideal. But you know, if you have 20 students, 10 students, you can do this. It is doable, and we can share these kinds of data sets with you. We worked with a group, I think I mentioned it before with one of the papers, but we worked with a group of students in East London, and when Gaia had one of their press conferences in the Royal Astronomical Society, we dragged the kids along. They were 14, 15, 16-year-old kids, and they spoke to the scientists, and the scientists said, you do this, you do this, you do this, and the students said, well, no, we do it this way, it's much quicker. So it was quite this really nice sort of symbiosis of the kids telling us what to do, and of course, because they're students and because they're in school, they wanted to tweet about it, so they did some really nice Twitter sort of publicity for us. And this is great, this is fantastic stuff, and this is not a school that is in any way in a rich area. This is not a private school or privately funded school in any way. This is an inner city, what we call a comprehensive school. So we were really pleased that we were able to get them involved and drag them along to this event where they were able to meet the press as well. So on the back of the work that we did originally, I've created, I mentioned it this morning with the ESA resources. I mentioned the one that I'll try and show you again later if I get time. But we created a new ESA, and I'll show you through some of the web pages in a second. And this was done to try and look at the linking between ESA, inquiry-based science education, and also citizen science, this idea that we can get members of the public to do some data analysis for us and enjoy the process and understand something of the process. So in this activity, we provide data sets, we provide the files that you would need to be able to do the work, we provide the background material. And this is why it's very difficult for Naira and I to sort of stick to time limits, because there is so much that we want to tell you. And I know Rose is the same. When we get to the black holes in my school and things like that, we want to sit you down for hours, days on end, and we know we only have an hour. So we have to throw this material on the web and hope that you can find it and make progress with it. We give you all the information on how to do photometry, and we use a different package to the one that Naira was mentioning, and a different package to Salsa J. It's called JS9. It's a similar idea. It does many of the same things. It's just a slightly different package. And we provide you with screencasts and instructions, so you can actually see me moving the cursor around the screen and follow that. We provide you, as Naira did with the activity she mentioned, with an Excel sheet that is a template. So you put your data into it and it starts to do some of the work for you. And we provide you with another Excel sheet that does the cosmology side of things for you. And we tell you about Gaia and say, go and take some images, use the telescope and start taking images of supernovae and add those supernovae data to the data that we already have, because that's what science is. Science is not just everybody looking at the data set that already exists. Use the telescopes, go out and find your own data. So let me jump out of that. I'm going to sort of jump into an Excel or into a few different things here. So somebody from the organizing committee may just need to tell me that everything is being shown on the screen okay. So we create for you things like this. So I will share all the web links. Don't worry that you'll miss out on those. Obviously you have the recording. But we may give you a chart. So can you see two charts on the screen? Is that okay? I can't see the chat.
Yes.
So yep, okay, great. So the one on the left is a bit like the one Naira showed. It's what we call a finder chart. So the circle in blue is the supernova, and the other three circles on the screen represent stars that are nearby. And we use those to calibrate the value of our star. Okay, we use it to make sure that the variation we see in the star in the images is solely due to the supernova and its change in brightness, because other things affect that, like cloud, like the behavior of the telescope and so on. But hopefully we come up with an image like the one on the right hand side, which is a light curve. Again, it looks like much the same as all the other ones that we've seen already. It's a change in brightness from quite bright to very bright and then fading away over 30 or so days. And from that, we can take some measurements. Now, again, I'm going to jump again. I hope you're staying with me, and I apologize. I know I'm jumping around, but I've got so much that I want to show you and so little time. But this is the template that we share with you originally. So we share with you about 10 or 15 data files and all the instructions and the screencasts. And you basically fill in the numbers using JS9, using this photometry package, into this spreadsheet. As you fill in numbers here on the left-hand side in these columns, so the right-hand side starts to fill up with numbers that I'm calculating for you in the background, if that makes sense. And it will actually create the graph for you on the screen. So that's what we have here, is a template. So we're not expecting you to start from zero knowledge and zero understanding and have to try and work your way through Excel as well. We're doing some of the background for you. And I think that's the case with all the activities that we try to share with you. Eventually you come across a light curve, or you create a light curve that looks a bit like this one on the right-hand side, and we take a value from that. Now, the value here is different to the value you need, because there's another step in the middle that I don't want to don't want to jump into right now. But you do end up eventually in another spreadsheet. And again, we could share this with you as an Excel, but you could put this into a Google spreadsheet and share it with your students, and they can work collaboratively again. In the case of the supernova that we work with, it turns out the apparent magnitude, the magnitude of how bright this object actually reaches, is 15.9. So I'm going to type that into the spreadsheet on the left-hand side at the top. Hit return. The absolute magnitude is the value that Naira mentioned. These objects always have an absolute magnitude of minus 19.3. That if it's a type 1a supernova, that's how bright it will be. That we know that to be the case. By putting those numbers in, we start to fill this spreadsheet. If I then put a value in for the redshift, so how far away or how fast is this galaxy moving away from us? And again, we go to the literature for this, but in the instance of this, to give you a head start, to give you a chance to do it, we give you the value. You type the value into here, which is 0.025, and we hit return, and it creates a graph. And that graph, that value there at the top right, which is 68.4, it's actually sitting in the spreadsheet as well here, that is the Hubble parameter, or the Hubble constant, based solely on one set of observations of one supernova. And it's about right, it's not far off, it's within about 1% or so. We can actually go further. We can actually use that Hubble parameter and use it to calculate the age of the universe. Initially, we do it in seconds, and then we convert seconds to years. And again, like I say, all of this is filled in the spreadsheet for you. And we come out with a value for the age of the universe of about 14.3 billion years, which again, that's within a few percent, within about 5%. But this is solely from one data set. Now, if you imagine your students could image one supernova each, you might be able to image 4 supernovae over the course of a term or over the course of a year. You would then have 4 data points to put on this graph. And in theory, that will help make things a little bit easier. And it will start to tell you something about the scientific process. What we always hope in science is that more data tells us a clearer picture. That turns out not to be the case all the time. But that's basically the idea of this activity. So let me just go across to the activity itself. So this is the main web link, and again, we'll share all this with you, so it'll be up on Grasp later. But the idea is that we tell you about supernovae. So we start off, and again, this is not something that your students would do in 30 minutes. This is something that your students might do over 4 or 6 or 8 hours. So there's a lot of material here. And we try and give you, it's the case with all these activities, we try and give you all the information we know you'll need, but we try not to give you so much information that it hurts. Okay, so we try and give you everything you need. So we tell you here all about supernovae, the different types of supernovae, and Naira mentioned this before, the idea that there are type 1a supernovae and type 2 supernovae. So we have all this information in here. And we've put it with lots of nice images as well, so it makes it easier for the eye to absorb what's going on. We tell you about how we find supernovae, where we find them in the galaxies, or in galaxies in general. We tell you about the Gaia mission. So again, we're talking about ESA's Gaia mission here. We tell you about the link between supernovae and cosmology, and we tell you about how to do the photometry. So again, hopefully you'll see here there are some little screenshots that are embedded within the activity, but they're available on YouTube, that are just 2-minute videos that just show you all the steps. So again, I haven't shown you the steps today in detail, but they're all linked here in these videos, just to sort of allow you to see what's going on. If you then go to resources, this is where all the downloadable things that you need will be. So this tells you how to go and find the program. It tells you where the data is. It gives you a manual to work with the photometry package, and it gives you the spreadsheet as well, and then there are FAQs. So we hope it's a really nice, fairly well self-contained activity, but one, like I say, that is not for, you know, this is probably for 16-year-olds, 17-year-olds, 18-year-olds, and it's probably something that they would work through in a few hours rather than in a few minutes. So hopefully that gives you an idea of the kinds of activities we've been able to produce. I realize time's moving on, so I'm going to jump across to another activity which is at the opposite end of the astronomical spectrum. So we'll come right in from cosmology, back into our galaxy, and back into our supernovae, back into our solar system even. And I'm going to talk to you a little bit about a program called Down to Earth. Now, again, if you've seen my talks in the summer in the other events that we've been working on, you may have seen some of this already, so I apologize. But Down to Earth looks at things in our solar system that are moving around, these idea of asteroids and meteorites and impact craters on the Earth, the link between that and the death of the dinosaurs, all these things. And kids love that because they love dinosaurs, and they love the idea that all the dinosaurs died because of a big rock. So we're already on good ground. And we have, as part of this activity, again, you'll see the web link there, I'm sure, we have a thing called the impact calculator. And this is the boundary between science and fun. So there is science going on here, but it's also kind of fun. And this is a way of designing your own asteroid and virtually crashing it into Earth and seeing what the consequences of that are. One thing that is really, really useful with this particular activity is it's available in lots and lots of different languages. So I'll just run through these on the right-hand side in case you can't see them. But this is available in English, as you might imagine. It's also available in Welsh, in Danish, in German, Greek, Spanish, Estonian, French, Croatian, Italian, Latvian, Norwegian, Polish, Portuguese, Romanian, and Finnish. If you do not speak any of those languages and you want to have it in your own language, contact me. We can send you a Word file and you fill in the terms in your own language and we can add that onto here. So it's a really nice activity in that sense for lots of different groups of people. We'll look at the Earth. So we're going to crash something into the Earth. We'll click on Start. Now, this is the screen where I get to design my own asteroid. So let's make it quite a large asteroid. I'm going to make it hit the Earth at 90 degrees because that should make quite a decent mess. Let's do it at a reasonable speed. So let's do it at 60 kilometers per second. So not 60 kilometers per hour, as a car would drive at 60 kilometers per second. Let's make this meteorite out of iron and let's crash it into sedimentary rock. Now, as with all experiments, it's safer to stand quite a long way away from things like this. So let's stand 200 kilometers away from where this is going to hit. I promise you this isn't real, so don't panic at this point. You don't need to go hide. And we have a little glitch with Google that we still have to resolve, but basically there are values on the left-hand side that tell you how big this crater is that I've created. Again, hopefully you can see the numbers on your screen. But we have created a crater of about 1,400 meters depth, about 175 kilometers across, and there are other values here. I can superimpose this. I'm not going to do it on Cardiff. I think Cardiff has suffered quite enough of late. I don't know that I want to go into the chat and ask where people want to drop this because we always end up with something politically strange going on. So, And that is the size of crater. So apologies to anyone that lives in central Spain, but I have just caused a reasonable amount of damage to the center of Spain by this crater. I could actually choose different places. New York seems to be quite popular for various reasons. Maybe even Washington would be even more popular. But we can superimpose this crater on different parts of the world, see the size of it. We can also think about the depth of the crater, and we can think about things that we know of, like the Eiffel Tower or the CN Tower in Toronto, and that's the size of the crater that we're creating around this particular object. If you're more interested in the science and more interested in the data, then the numbers are all here. And this is all based on E equals half mv squared. The energy that you create by doing this is driven by the speed that the object hits the Earth, its mass, so what it's made of and how big it is, okay? But there is an IPSY component to this. If you want to change just the mass or just the speed, you can plot the graph that shows you how big the crater is based on the different speeds. So there is some maths in there. There is a bit of an experimentation. The kids kind of enjoy it because it's crashing big heavy rocks into cities and things. And it's also a nice little, well, maybe nice isn't the right word, but there is a list here of what happens to me at 200 kilometers from the center of this impact. And it does get fairly graphic. There's some fairly descriptive text in there that tells you what happens and how bad a day it is. The one thing that if your kids at this stage, and particularly with the younger ones, if they're completely freaking out, you can show them this number here, which is how frequent. And this says, on average, this will happen on Earth every 1.5 billion years. So we probably don't need to worry about it between now and next week or now and next year. I think we've got enough to worry about right now as it is. So rocks of this size will only hit the Earth every 1.5 billion years. But at the same time, they will hit the Earth. We do know that these things happen. We've seen the evidence of these things hitting Earth. So what I think I'd like to do just for 5 minutes or so is I'd like to get you to do a little bit of work. So if I jump across to this slide here, this is the actual web link that you need. Now, I don't know if you can grab that off the screen or whether I need to try and put it in the chat or whether somebody can put it in the chat for me so that people can jump across to that simulator. Is that possible? Is anyone able to put that in the chat?
Just a second, I'm fetching it.
Thank you. Sorry, I should have given you warning, I know.
You were just putting your revenge nice and clear.
Oh, no. That I've not started with that yet.
I don't download exactly the link that you have, but I'm getting there.
Robert beat you to it, I think. I'm not sure. You probably don't need the bit after /planet, actually. I think that's just sort of an additional link. Good. Okay. If you have that.
It's here somewhat. Yeah.
Fantastic. Yeah, I think Robert put it in.
Yeah, thank you very much.
Here's a little bit of a thing you can try doing for the next 5 minutes or so. I'll turn my microphone off, and maybe you can throw up numbers in the chat as you get there. But the challenge I would give to you and to your students, how small a crater can you make, and how large a crater can you make? And you might do that by just playing with the buttons, or you might do that by sitting down and thinking, okay, what do I need to do to create a very large crater? What are the set of parameters that will do the most damage, if you like? So have a play with that. Questions 2 and 3 are sort of linked with that, which is, again, you could have a hunt on Wikipedia or something like that and find out the size of the Chicxulub crater. So this is a crater on the coast of Mexico that we think is tied in. The age seems to tie in with the time at which the dinosaurs died out. So we think Chicxulub and the dinosaurs are related in some way. So maybe you can find the parameters for Chicxulub in terms of its depth and try and reverse engineer, try and think back what size of crater, sorry, what size of object you would need to create Chicxulub. Or again, depending on where you are in the world, you will find there are craters in your country or near your country, and think about how to do that. If you're in Germany, I know there are craters called the Ries crater, the Nördlinger crater, I think. I can't remember where the other really good ones are. Obviously in the USA, we have Barringer or Meteor crater. In Canada, there are craters up in the Shield that are very difficult to see on real maps these days, but we can actually pick out some of the features there. So again, you can bring that back to your students and say, okay, we'll go, let's think about a crater that we know of from our country. And again, these things will exist in most or many countries in the world. There are certainly craters in Northern Africa, and there is a crater called Vredefort, which is in South Africa as well. I'm sure there are craters. What you need is a piece of land where you don't have too much tectonic activity, and these things will survive quite a while. So is anyone making any progress? Anyone getting any numbers? But again, this is something we think that is very open-ended. You know, we think that you can do this with your students. This will work to a degree with quite young kids, because they'll understand almost the game side of it. You can think about the maths and the IT side of it and graph plotting with the older ones. You can do this as part of a geology or a geography assignment. You can think about this in terms of solar system objects and astronomy and the link with asteroids. You can then take it in the direction of thinking, well, if we find an asteroid in our solar system that we think is coming towards Earth, what are the options open to us? Is the only option to send Bruce Willis and his group of astronauts up to destroy it? Or are there other options that we could do that are reasonably clever? And how well could we get the world to communicate and cooperate to be able to do these kinds of things? And how quickly could we turn around the idea of getting rid or losing an asteroid? I think I saw 93 meters. I think somebody threw 93 meters, which sounds quite small. So. $69, okay. So you're probably, I'm guessing here, but you're probably picking a fairly small, or you're making your asteroid fairly small. I'm guessing you're trying to make it come in rather quite slow as well, because again, energy is half mv squared. So you need to reduce m, or you need to reduce v, or a combination of the two. Maybe the angle helps as well. So if you think about an asteroid coming straight down to ground, or an asteroid coming in at a very, what we describe as a shallow angle, that may affect it. Again, I don't really want to, I don't want to try and push you too far into working, you know, into sort of coming up with the answer right now, but hopefully you can see that there is some nice sort of you know, there's some nice real physics that you can do behind that. And hopefully as well, the other thing to mention, the website is more than just the simulator. There's a lot of really nice material on the website about different, you know, the different things in our solar system, comets and asteroids and meteors and meteorites, and all these different terms that we kind of know, we kind of recognize, but it sets them all out for you. So there's some nice material there. Hopefully you can have a play around with. I'm just trying to think, what else do I need to show you about that? So yes, so yeah, we think down to Earth in a sense is a really nice sort of multidisciplinary and IPSI type resource, or you can certainly make it one. And again, mentioned Chelyabinsk before, this was a big event in recent times that made politicians sit up and say, okay, maybe asteroids, maybe meteors, meteorites are a big deal, because this one in Chelyabinsk didn't do that much damage, but had that been in above Moscow or above New York or above Berlin or Paris, would there have been a bigger issue? And then the other thing that politicians wanted to know straight away is, why didn't we know? Why didn't you tell us yesterday that this was going to happen? Why didn't you tell us a year ago that this was going to happen? So there is an aspect of that we need to be aware of as well. And like I say, we've worked with these IBSI type resources a lot. I'll leave this slide up for a couple of minutes again, just because it's got a couple of links at the bottom. Within GRASP, which is the portal that you're using for material on this course, GRASP is linked to a project called GoLab, as you may well be aware. Within GoLab, there are some really nice activities based on this resource, based on this impact calculator. And this is where teachers have just gone away and created their own lesson plans based on using the impact calculator as part of the lesson. These lesson plans are in English, they're in Spanish, in Portuguese, in all sorts of different languages, and they look at different aspects. So teachers have sort of taken the basic idea and said, okay, I know how I can use this in my classroom. So there are two examples there towards the bottom of ones that I've been involved in, but again, please have a look and see what you make of those. I think that's as much as I want to do on the impact calculator, because I have 22 minutes left and then the bell goes. And as we saw with Naira, as soon as the bell goes, you have another 10 minutes and then you've got to stop. So I'm joking. So I'll show you another two of these activities that I've designed. So again, these are things that we're doing. We're taking astronomical data, we're taking real data that astronomers would use. We're taking real data and real skills that astronomers would want, and trying to give them to you and your students in a way that your students can understand. We want students to understand that science is difficult, but we don't want them to think it's impossible. We don't want to stop those kids that want to be scientists at this point. So we want them to understand that it's fun, it's possible, and it's available to all sorts of different groups around the world. So this is why we come up with these different activities. So this is the first one I did. We've not really mentioned this diagram much this week at all. It's one of the key diagrams in astronomy or in astrophysics. It's called the Hertzsprung-Russell diagram. And it shows how stars live their lives. It tells us something about populations of stars and tells us something about what we think our sun will do. And it divides stars into four different populations in a sense: main sequence stars like our sun, giant stars, supergiant stars, which we think are the ones that are going to go supernova, and white dwarfs, which we think are also to do with supernova in a different context. So in this activity, we provide you with all the material to do measurements. Again, like Naira was showing you before, and like I was showing you a little bit as well, we're showing how to do the measurements of a population of stars to create your own HR diagram, your own Hertzsprung-Russell diagram. Now, again, as a teacher, you may have students that are very keen on this, but you think, I don't know the Hertzsprung-Russell diagram. I don't have time to learn and teach my students a photometry package. So we've appreciated that, we've understood that, and we've gone and created the activity for you, hopefully with all those different aspects in it. So this is an activity that shows you explains to you the background of star types, about background of photometry, so you can learn about main sequence stars. And I mentioned red giant stars, so we can learn about red giants. So again, it follows the idea a little bit like Wikipedia, that you just click from one page to the next and it takes you in the route that you're happiest with. We are not telling you, you must read page 1, you must read page 2, you must read page 3. And at the end of the activity, we don't just say on the final screen, the answer is 12. If you got 12, 100%. If you didn't get 12, 0. Science is more subtle than that. There is more going on in science than just getting that single one answer. There's lots of things that we try to do along the way. So we explain lots of things about open clusters, how open clusters work. We explain how to do photometry. So again, Naira will have examples of this on the Peter website as well. but there is a guide here to how to do photometry and what we're doing with photometry. And there are things like a finder chart that shows you how to measure, or which stars you need to measure. So we give you, hopefully, all the different tools along the way. How do I measure the stars? How do I put that data into an Excel spreadsheet? How do I create my graph? How do I interpret that graph? And the final bit that we're still just playing around with and haven't quite got in a format we're happy with just yet is to feed those results back. So it's not just a question of your students sitting there with a piece of paper and saying, I did this, and then they go home, but maybe they can load that Excel sheet or that JPEG into our server and say, this is my version. And another student can come along and say, well, this is my version, and they can compare their results. And that's that sort of collaborative nature. It's also the conclusion part of IBSE. So at the end of every IBSE activity, you want your students to discuss, share results, and make some sort of reflection. And we're trying to build that into these activities. And it's not easy. We're getting there. We're making progress on it, but it's really not easy. So that was another activity I wanted to show you. And I will show you one more thing about this activity just because I really, really like it. And I'm kind of sad that way. Hopefully this will work. Just bear with me 1 second while I find the file. Okay, so hopefully you see a black square with lots of red and blue circles on it. This is about 80%, 90% of the way through the activity. When you've created your Excel spreadsheet with all the data that you've measured this from your stars, you can then upload that data to this page, and this page is giving you a digital representation of your data. So every star that you've measured is represented on this graph in the place it is in the original image. Okay, so it's just taking that original data, the X, Y, and positions of the stars, and it's reproducing them on this graph. But it's doing two more things than that. The larger the circle, the brighter the star. So it feeds the data in from Excel. The brightest stars are represented with large circles. The faint stars are represented with small circles. Okay. The color of the circle, and I'm sure you're ahead of me at this point, the color of the circle represents the color of the star. So again, when we talk very briefly about stars, you've heard this week already, I'm sure, and Fine's law, blue stars are hot, red stars are cool. So where we see these stars here, they are represented as this is a digital representation of the original image based on the data you've taken from it. But we can do one more thing with it, which I think is magic. Probably won't be magic because I've set it up now. That is how we convert the data from positional data from where the stars are in the image to where the stars live on the HR diagram. Okay, so this is the HR diagram that we showed you before in the the very first image. The blue stars are at the top left. These are the hot blue stars. The faint red stars are at the bottom. So we can kind of switch back and forth between the positional data of the stars and where the stars live in the diagram. I love that. I think that's a really fun thing to do, but that probably tells you more about me than anything else. Okay, 14 minutes. So I have one more to show you. And again, this is one you may, if we have a little bit of time, you may be able to just have a quick little play around with this one. We spoke to teachers, and after we did the open cluster activity and we thought about supernovae, and the other thing that teachers and students really want to know about is exoplanets. So we created another one of these IBSE activities around exoplanets. So there is information in here. The first thing you want to know about maybe with exoplanets is an understanding of how our solar system works. It's very hard to understand what is going on with exoplanets if we don't have a very good idea of our own solar system. And from the spacecraft that ESA and NASA and others have sent up, we now have a pretty good idea, a pretty good understanding of the properties of our own solar system. And from that, we start to develop this idea of a habitable zone, where in our solar system would or could life exist. And that's based on distance from the sun. It's based on other things as well, but distance from the sun is the key, I guess, in that respect. we tell you about the history of exoplanets. And in some senses, the history only goes back about 20 or 30 years to the first discoveries in 1992 and 1995. But we've thought about the idea of planets around other stars for a lot longer than that. Bruno was the first person to suggest it in the 17th century, and then it was done again or more thoroughly in the late 19th century and so on. So there is some information there about the history of exoplanets. And what we've done as well is we do provide web links in here that take you to other sites, take you to Wikipedia and so on. So we don't just say, this is all the information you need and please don't go anywhere else. We do encourage you and your students to keep going, to keep looking. So there is lots of information here about exoplanets and the different detection methods. And we spoke earlier, we were talking earlier about the transit method, about how the light from a planet, the light from a star diminishes, it drops because a planet is passing across it. And there is information in here about the different properties that exoplanets would have. So we might talk about an exoplanet's radius, its volume, its mass, its surface temperature, and so on. So there are lots of different things here, but we try and explain them. The activity itself takes you to a different website. So we're not using telescope data here. We're actually using a website called exoplanet.eu, and there are 2 or 3 different websites around that do this, but they track all the data on exoplanets. So this is kept up to date by the people that run the website, and we're just basically using the website to design an activity around. So I can go to that website, and we end up with a plot that starts off looking a little bit like this. It's a bit of a mess, because there's an awful lot of data on here. So each dot here represents a different exoplanet system that we know about. And in this instance, the default for this graph is to plot the planetary mass against the orbital period. And the instruction for this activity, it's quite open-ended. It's very IBSy, it's quite vague. And the instruction is plot something against something else, see what you find, discuss with your colleagues, discuss with your teacher. I know that's not a very exact way of doing things, but it's sometimes the way scientists work. You give them data and they just plot everything against everything else and see what happens, see what comes out in the wash, so to speak. So we could think about planetary mass, so how massive a planet is, and we could plot against that planetary radius. And that starts to show a graph that is a bit interesting. There's a bit of a trend in there from bottom left to top right. There seems to be a rather large group of objects around here, around the top right-hand side, and another group towards the bottom left of the diagram. So again, maybe we want to focus in on that. So there are lots of different things you can do with this graph. You can change the axes by just typing numbers into these boxes, min and max. This is currently plotted in logarithmic scale, so we could switch logarithmic scale off and see what that does to the graph. Well, that doesn't really help us at all, so let's put that back on. So it's almost at the idea of the very first stage of an IBSy activity, an inquiry-based activity, is to devise a hypothesis. And the hypothesis, I think, planetary mass and radius are correlated, are going to be linked in some way. And maybe this data will help prove that or will help disprove that. So it's a nice activity in that sense. One thing we could do, just because we have a few minutes left, and I kind of know it'll work as well, is we can think about where exoplanets are situated in the night sky. So again, somebody might want to type into the chat box. If I look in the night sky, is there a particular direction or set of directions where I might find more of these than anywhere else? And if you've seen this activity before, please don't say. Not sure if anyone's typing. I know it's very nearly food time, so I won't run over, I promise. Okay, so nobody has come back with an answer as yet. So I'm saying Is there a particular direction?
Someone said Via Lactea.
Via Lactea, the Milky Way.
The Milky Way.
I know this. I know that. It's Via Lactea is Spanish, but yeah, I've got that.
Towards east.
Towards the east. Okay. I don't know why that would be, but okay, Via Lactea makes a lot of sense. So if we think of the Milky Way that we see in the sky, that is the plane of our galaxy. So there would be more stars in that. And if planets are randomly distributed around stars, that makes sense. I'm more than happy with that. What we can do is actually plot it rather than theorizing too much about where it might be useful. Let's plot the positions of the stars. Now in astronomy, we tend to use coordinates that are called right angle and declination. These are the astronomical equivalent of latitude and longitude. So this is how we look around our night sky. Now, I'm looking at that and I'm plotting, if you like, latitude and longitude against each other, and I'm not seeing anything that looks like a particular pattern. There's no particular area that is much busier. That looks like a random pattern, apart from an area towards the top right. There's an area around about 270 degrees in RA and about 40 degrees in declination that looks a little bit different to everything else that's going on. So we can actually sort of zoom in on that. So let's pick 260 as a minimum and 320 as a maximum. And then we want to zoom in on that top area, so between maybe 25 and 55. So if we put those values in there, that's a bit odd, isn't it? Wow. So there is a particular part of the sky where we see hundreds and hundreds of exoplanets in squares. And I don't know if that's a bit worrying. Is anyone worried by that? Or is anybody thinking that's okay? Or does anybody have any thoughts about that at all? So the rest of the diagram, if we zoomed out on the diagram, the rest of the diagram just seems to show numbers randomly.
People were saying aliens.
Aliens. I think you're probably right. I think it probably is. As if 2020 cannot get any worse. I think we've just discovered aliens. Yeah, maybe. It's not necessarily aliens. Maybe, I don't know. But there are, there is a random distribution of these things across the sky, apart from this one particular part of the sky we look at, where we see hundreds of these things in almost like there's spaceships coming towards us. If we hover over each of these black dots, it tells us the name of the object. Okay, so again, we're looking at different star systems, and each one of these tells us information. We can actually click on that and it will open another page, tell us more about that particular exoplanet. So if we do that for these, so do you see the square of information that's coming up there? So that's Kepler 1646b. What about this one? That's Kepler 607. That's Kepler 783. That's Kepler 888. And I think Frank has got the answer there by the look of things. So yeah, this is actually the area of the sky that the Kepler mission looked at. So the Kepler mission was up a few years ago, and it was looking for exoplanets by a particular method called the transit method. And it stared at one particular part of the sky. In fact, it stared at an array of about 20 different fields of view within the constellations, think of Cygnus and Lyra. And that's exactly where we're looking here. So we're not seeing more exoplanets because there are more exoplanets in that area. That there might be because of Cygnus, so it is a spiral arm of the galaxy. But we're not seeing more. We're only seeing more exoplanets there because that's where we spent a lot of time looking. Okay, So it's what's known as a selection effect. There's something going on there that says, okay, if you believe this to be true, and if your immediate answer is, well, it's aliens, you know, maybe you missed something. Maybe there's something about the data that is taking you in the wrong direction. The analogy I always give is, you know, if you want to find out how many people in your country enjoy football, standing outside a football ground at 3 p.m. on a Saturday afternoon will not give you a very representative answer, because you're in the wrong place to get a random selection of people, if that makes sense. So it's the same thing going on. So that's really, in a sense, what this activity is all about, is to just explain something about how astronomers view populations of objects, something about how astronomers take those numbers, take that data, and play around with it, and something about how they remove what we call selection effects, things that make them think something's going on that are tricking them, fooling them into the wrong direction. I think with about a minute or 2 minutes to go, I think I'm done. So I'm going to sort of stop sharing, if I may. I'll come back in the room and answer some questions, if you like, for the remaining minute or two. And then I know that Michael is going to ring the bell and you'll have to go off and look at XMM, which I will certainly be doing as well. So if I stop sharing.
Many thanks, Fraser. By the way, the bell is rung by David, not by me.
Oh, is it? Sorry, I beg pardon. I thought you were in charge of that. So, okay, right. Okay.
No, but he does it very well. So, so it will be in a minute.
Yeah, that's fine.
Not this time, because you finished before.
Okay,
you,
yes.
You don't want to know. This is very advanced technology that David is using, and I guess he's not telling us how it's technology. Very, very advanced. I think he learned with the aliens in your image.
It's just that. That's all that's going on. It's nothing clever. There you go. So yeah, just to say thank you very much for listening. I know I kind of took you on a real whistle-stop tour around lots of different activities. And the one question I have open by email or however you choose to contact us is, you know, are these activities useful, and what else would you like us to see us do, given time and budget and so on?
Okay, I see a lot of thank yous. Many thanks, Fraser. And with that, we come to the last point of today. And since now Fraser and also Naira explained you how to deal with supernovae and the data from the supernovae, so there is especially one observatory that is really very good in observing supernovae, and this is XMM-NEWTON. And it was also said in the morning in the talk from Markus Kissler a little bit. He was talking about Mars Express. And we have here now today Maria Santos Leo. She is the Science Operations Manager of XMM-NEWTON since many years. And she will show you around the XMM facilities and tell you a little bit about the operations of the spacecraft. Maria?
You're mute.
Yeah. Can you hear me now?
Yes. We can. Okay. We can also see you. Very good.
Yeah. Okay. So good morning or good afternoon, everybody, depending where you are. And it's my pleasure to introduce you XMM-NEWTON and guide you through the XMM-NEWTON operations room. So before we go to this, I hope you can see what I have in my hands is a little model of the spacecraft I'm going to talk to you about, XMM-NEWTON. This model is 180 scale, so the real spacecraft is 80 times this size. So this tube is 10 meters long, and the solar panels are 16 meters from one side to the other. So it's a big spacecraft that is in orbit around the Earth. Yeah, I hope you can see this Earth that I have here.
Yes, we see it.
Okay, so XMM-NEWTON is flying, so to say, around the Earth, so it makes a very elliptic orbit. The closest is about 10,000 kilometers away on top of North America, more or less. And then it goes around much, much farther away, up to more or less 100,000 kilometers. So more or less, one third of distance from the moon. And when it is farthest away, it is on top of Australia. So, okay, more or less here. So we are going to now to start the virtual tour. Unfortunately, given the circumstances, we cannot, you cannot be here, but let's be optimistic. I guess some of you wouldn't be able to be here, so perhaps we are more people than we would have been if it was a real tour. So let's imagine, as I said, if you were coming here, you were coming to ESAC, to the European Space Astronomy Center, as you
Maria,
have been. Yeah.
Can you press F11?
Yeah, I already did, but
make full screen.
Yeah, now, yes.
Thank you.
I already did, but probably not strong enough, sorry. Okay, yeah. So, yeah, as I said, you have already been introduced to ESAC. So you can imagine coming here and you would enter in the building where the XMM operations room is. Also is the same building of the Mars Express room that you were visiting yesterday with Michael. This is the hall. When you come in, you can see a model of XMM that is hanging up here. And this is the telescopes, the mirrors that are on board. This is one of the instruments that is on board. And now you can see better the model. This model is scale 110, so the real one is again 10 times bigger. So let's go to the room. Was there any question? Feel free to ask questions if you want. So we have gone through this corridor and we enter in a restricted area. It's restricted mainly because it's an operational room where we receive data from the spacecraft. So to avoid making mistakes or whatever. So here we are at the door of the room. Let's go in and you see some consoles, books, documentation. See some pictures of the spacecraft before launch when they were doing some tests, checking if the solar panels could deploy well or not, the integration before it goes into the rocket. And we go in, and these are consoles that as people working there, they see them. Take into account this was recorded during the lockdown, so at this time the activity here was restricted. So this is why these screens, not all of them have the images or the data that usually are when there is no lockdown and people, more people working here. But what is is information about the instruments on board the spacecraft as in real time, so as they are currently. So we receive information about temperatures or voltages of the instruments to verify that everything is going fine. And you can even see a little model here. But what is it about? I've been talking for a while about XMM-NEWTON, and I haven't told you what is indeed XMM-NEWTON. XMM-NEWTON is a space observatory. So it has space telescopes, but are particular as telescopes because they are to observe the universe in X-rays, to capture the X-rays that come from objects in the universe. And why are we interested in X-rays? Michael has told you that we can see supernovas in X-rays. We can see X-rays are a kind of electromagnetic radiation, like the light that we see with our eyes, but much, much more energetic. We cannot see X-rays with our eyes, and we cannot see with instrument X-rays from outside the Earth either while we are on Earth. Why? Because the atmosphere blocks X-rays from outside, and this is very good news for us, for the life on Earth, because X-rays are dangerous for our lives, and therefore we are protected by the Earth atmosphere. But if we want to see X-rays from outside the Earth, we have to go outside the atmosphere. So X-ray astronomy is very, very linked to the space exploration. So we only started to know about the universe in X-rays when we knew how to put rockets or spacecrafts outside the Earth atmosphere. X-ray astronomy then started in the 60s when a rocket was put outside the atmosphere and the X-rays from outside our solar system was first detected. And this was worth a Nobel Prize in 2002 for this opening of a new window in astronomy. A new window that has allowed us to see the most energetic places on the universe, most energetic as the surroundings of black holes or places where stars are exploding as supernovae. And why black holes? Because black holes, we cannot see them. But if there is matter around there, if they capture a gas that is very close, this gas is trapped by the strong gravity and very, very, very quickly falls down, making a disk where the friction of the gas makes, and due to the very, very high velocities, makes this gas very, very hot, tens millions degrees temperature, and then it radiates in X-rays and we can see it. This is shown here, for instance, in one of the pictures that are in this room where we receive the data. This picture is an illustration of a black hole surrounded by gas. This is not a real picture taken by our telescopes. It's an illustration, an artist's illustration, that shows how gas moving very quickly around the black hole can get hot and radiate in X-rays. This picture here, with small dots, this is a real picture taken by XMM-NEWTON, and is a region of the sky where we see X-ray sources shining bright, and these X-ray sources are gas close to black holes in the centers of far distant galaxies. And this gas is shining in X-rays, and we are collecting this X-ray radiation with XMM-NEWTON. This is another picture from XMM-NEWTON, and this is our neighbor galaxy, the Andromeda galaxy. This is seen in X-rays. We can see some places in the Andromeda galaxy where stars are being born or the stars are exploding as nova or supernova and shining in X-rays. And this is another picture of X-rays from distant objects. This is from a cluster of galaxies. Cluster of galaxies is 100 or even 1,000 galaxies kept together by their own gravity. And the gas that fills the space in between these galaxies is a gas that is very, very hot and radiates in X-rays. So all this is X-ray from very, very hot gas. These small points here are distant galaxies, and their nuclei are radiating in X-rays because they have supermassive black holes, very, very giant black holes. So all this X-ray astronomy is about extreme phenomena in close or distant objects in the universe. Here in this room, we receive the data on real time. This means the pictures that the spacecraft, the Space Observatory is taken, we can see them here in this room and check the health of the instruments and if everything is working fine. And then learned a lot about the extreme universe, about black holes that, as you probably know, have been subject of the Physics Nobel Prize this year. Three physicists have got the Nobel Prize this year for theoretical prediction or for finding black holes or for detecting compact objects at the center of our galaxy about the Milky Way. And this is what we are observing with XMM-NEWTON. Yeah, so my time is over. I'm open for questions if you may have any, or I hope you enjoyed this quick tour and visit through XMM-NEWTON room.
Yeah, many thanks, Maria. Questions for Maria for XMM-NEWTON? By the way, I think perhaps it's good to mention that this type of consoles is now something historically, no? Because the new missions, we don't get those nice consoles anymore.
Well, yes, XMM-NEWTON is 20 years old already. Was launched in 1999. It's still working. So it's.
And the consoles were from ISO, no? If I remember correctly.
No, I don't. No.
No, were they
these consoles have been these screens at least have been renewed.
No, but I mean the furniture.
The furniture, yeah, maybe. They are the same design. Whether they were exactly recycled, I'm not sure.
At least they were looking at the same. I just remember from ISO that they had the same yellowish theme and the brown panels. So it's a really nice room to look at. I like it very much. So if you don't have any questions anymore, no, it says there's a question. What does an X-ray telescope look like?
Well, the I showed you the model of the spacecraft. The telescope is not like optical telescopes, because for a telescope you need a mirror, and normal mirrors don't focus X-ray light. The X-ray photons simply pass through the mirrors and are not collected. So we need to have special mirrors that are cylinders, and the inner surface of these cylinders is covered by the reflecting material that is gold in the case of XMM-NEWTON, with a small curvature, so that the way to focus X-ray photons is with incident reflection. The photons come through, and with two reflections we manage to focus them in the focal plane. It's similar like when you throw a stone on the surface of a lake or a water surface, and these stones are reflected. So this is how we build the X-ray telescopes.
Okay. Yeah, many thanks, Maria. And yeah, it has been a long day.
How long it takes to take a picture was another question, and it's a good question as well. It takes a long. The average time that we for a picture is something like 10 hours, and so the exposure time is from 1 hour to 40 hours. In average, something like 10 hours. And the diameter of the cylinder, yeah, I didn't mention that, but XMM has several cylinders, one inside the other, to increase the collective area, to have more sensitivity, to be able to collect more photons, and therefore make pictures of weak sources. The diameter of the bigger, the more external cylinder is about half a meter, and a little bit more than half a meter, and the inner one is 35 centimeters. In between, we have 58 such cylinders, so they are very, very close together, back together. Let me try here the cylinders one inside the other, and this is how XMM-NEWTON has 3 such telescopes, and is how they look in the front. Okay.
Okay. And there was the question. Yeah. What does it take to be successful for a picture which needs 10 hours?
What does it take?
to be successful, to get 10 hours of XMM time?
One of the pictures. This is a galaxy. This is the Cigar galaxy, and that some astronomers know in the optical. This is optical light, so it's a galaxy that has this shape. This is where it gets its name, and this blue image, or this blue, is the X-rays. So what do we learn with X-rays? That this galaxy that looks like a disk seen on their side has a wind of very hot, very energetic gas that is going out the plane of the galaxy. What do we learn? How this wind of gas is produced? One example, and as I showed you, this is another example, the gas that fills the medium in clusters of galaxies. We learned how these big black holes, how big they are. We can learn what is their mass. We can learn how they form, how they get together in the centers of the galaxies, how they impact the medium. So we learn how the universe is formed and how it evolves from the Big Bang to nowadays. We learned about the stars, how they live and how they die. We learn about our universe.
And perhaps the last question is...
You might only collect a few photons per minute. Sorry, I didn't perhaps size.
There was a question which I don't completely understand, which is what kind of a collector plate do you use? Perhaps they think of the CCDs, of the special CCDs.
Probably about the instruments, yes, because I explained the telescope, the mirrors, and then these mirrors have a focal distance of 7.5 meters. So we put the detectors 7.5 meters away. This is why it has a long tube, and on the other side of on one side the telescopes, and on the other side the detectors, the instruments. And these detectors have CCD cameras similar to what we have in our mobile phones. Is cameras that collect the photons and make pictures, with the small difference, small but very important difference with the cameras that we have in our mobile phones. That is the cameras to make pictures with optical light, with visible light, collect all the photons at once. In X-rays, since one X-ray photon is very, very energetic, we collect one by one. So we know when each one of these photons arrive and how energetic this photon was. And this gives us much more information. So this is another value, and this also is another justification for being observing 10 hours to the same place, because we have information about the times when the photons arrived.
Okay. Again, many thanks. I think we have no more questions. Thank you, Maria. And
You're welcome.
We are back tomorrow at 10 Central European Summertime for the last day. And the last day will be, we talk a little bit more about all what we have learned about space and what we investigate about space with our spacecrafts. How does this really impact our daily life? And so we will discuss this tomorrow. So many thanks again, and talk to you tomorrow.
Thank you, Michael. Thank you, everyone. See you all tomorrow.
Thank you.
Hi, thank you. See you tomorrow.